So I'm here with Timo from Arvado, and you saw him actually in the first term of this program. But you're back again for another project where we're working with the same data, but we actually sort of like left a lot of the complexity this time that we removed the first time. Can you talk about the third data set that's introduced, as well as like what's the ending goal that Arvado uses this data for?
Sure. So firstly, welcome back, and thank you for working on another project with our data. I hope you liked the initial one. Now we are introducing a third data set that you can use to actually evaluate your model and test your recommendations you would be giving to our client with that model. So the project you have been working on is a real-life project. It's a project you would be working on as a data scientist at Bertelsmann Arvado. We have similar projects like this where you would be analyzing attributes, customers, for example, to recommend credit scores. We are looking at similar of these attributes you have been working on to identify payment behavior, predict payment behavior, recommend credit scores, calculate credit scores.
Can you talk a little bit about what you want as an ending goal from sort of a business perspective? So this whole new third data set that's come into play now opens up sort of a world of different questions and how we might be able to answer them.
Absolutely. The underlying business question or the kind of problem statement is how can our client, how can the mail order company acquire new clients more efficiently? And what we're asking you to do is essentially, so you have the attributes and the demographic information of the existing clients. We would like you to analyze the attributes of these existing clients, match them against a bigger data set that includes attributes for people in Germany, and essentially figure out which people in Germany are most likely new customers for our client, the mail order company selling organic products. And it's from our kind of view, it's a real life project. So essentially what it helps to do is increase efficiency in the customer acquisition process. So instead of the mail order company reaching out to all people in Germany and targeting them with a marketing campaign, we would just then be reaching out to the people we identified as becoming most likely new customer, and can then essentially do targeted advertising. That's what it is.
Right. Right now, they have a culture where they make decisions based on, maybe like past experiences, intuition, but and a lot of that is okay. But if they can infuse those decisions by also backing them up with data, or even showing like we can go even further with this decision in X direction or Y direction, that's sort of like where you guys come in. Is that true?
Absolutely. So that's what we are doing. So the mission of our engagement is make decisions based on data instead of gut feel. Of course, we're dealing with senior finance managers, and they do have a lot of experience. But our client is really conscious that they are using data points to kind of, prove and show the rationale behind their decisions. So we'd like to have them use more reports, use reports more often, request more reports, and actually use the data we are providing.
Timo, thanks so much for some insight into the data set.
Sure. And thank you very much for participating in this project. I hope you find it insightful. It is, as I mentioned, it's data we are using. It's a real data science project, so thank you very much for that.
Hi, welcome to this course on software engineering. I'm Juno.
And I'm Andrew, and we are very excited to be guiding you through this course. Wait, Juno, why are we talking about software engineering? You told me that I was here to teach a course for the Data Scientist Nanodegree program.
Okay, I admit data scientists and software engineers have quite different roles. Data scientists are like the researchers or thinkers who explore and model data. For a data scientist, code is a means to an end. On the other hand, software engineers are like the builders and, well, engineers who make products and write code for production. Software engineers need to write efficient, robust, and maintainable code. But both data scientists and software engineers code and write programs.
I think I see where you're going with this. We as data scientists write a lot of code, but we don't always pay attention to things like code structure and maintainability. For example, a good software engineer spends the time to write clean and well-tested code. We have a thing or two to learn from them.
Yes. As a data scientist, you'll most likely be working in teams and share code across your organization. Your insights could influence important business decisions, or you may be building models to use in their product. This makes it crucial that you follow a few software engineering practices that ensure your code is clean and reliable. You'll improve the efficiency of your workflow, collaboration in teams, and communication with software developers.
It's true. Software engineering skills will help you stand out against the competition when applying for data science positions. Employers want and often expect good software engineering skills from their data scientists.
I'm glad I convinced you, because we've got some awesome projects and exercises in this course. By the end, you will have applied a number of useful software engineering practices, built a Python package, and created a web application.
Let's take a closer look at what you'll be building.
We've divided this course into 3 parts. The first part is a review of general software engineering practices, like using version control and documenting your code.
In the second part, you're going to build your own Python package using object-oriented programming. If you've ever wondered how pandas or the scikit-learn packages work under the hood, that's what this lesson is all about. And finally, the last part will be an introduction to web development. You're going to build a data visualization web app that you can put online and share.
In all of these lessons, you'll gain practical skills and produce a couple of applications that you can customize and use as a part of your professional portfolio.
But before diving into software engineering practices, we want to tell you a bit about our experiences. Hi, I'm a content developer here at UDACITY, and I previously worked on the self-driving car Nanodegree program. I have a bachelor's degree in mechanical engineering. You might ask yourself why someone who studied engineering would be teaching data science. Well, my interest in data came after college when I spent a year studying in Peru. While I was there, I started a jewelry business with a Peruvian friend. At first, it was just the two of us, the jeweler and me, the engineer. I think you can guess which one of us became the jewelry designer and which one had to learn web development, data analysis, and machine learning. To give a couple of examples of how we've used data science and analysis, I made a linear regression model that helps us price new designs. I've also analyzed web traffic and keyword searches to make content better. Over the span of 1 year, I increased unique monthly visitors from 1,000 to 12,000, and that's without spending anything on marketing. I learned to code and analyze data the exact same way you are doing right now, by taking online classes and then making awesome projects. I'm proof that someone with a non-computer science background can still be a proficient programmer.
I want to tell you about 2 experiences that demonstrate how software engineering has always been an essential tool in my data science work. My first experience is about my previous job, where I worked as a data scientist at a small startup. There, my work involved several machine learning and deep learning projects, where I personalized shopping experiences for users and built analytic tools for the business. Although I was excited that my work touched on many different areas in data science, one unexpected perk was how much software engineering I learned and applied. Almost everyone else was more of a software engineer, with roles ranging from web and mobile developer to systems architect. To implement my data science ideas and bring them to production, I had to use the proper practices and tools used in software development. Applying these practices really allowed me to collaborate effectively with other developers and set up my data science code to work well in production. Since this specific job was at a startup, I did get more involved in the software engineering side of things than I would at a larger company. But like we mentioned earlier, there are significant benefits to using software engineering practices as a data scientist in any context. This leads me to my second experience about my first major project before even landing my first data science job. There used to be a calendar app that I organized my life with and loved. When I heard it was being taken down from the App Store, I decided to build my own version. And I wanted to take it a step further and build a chatbot that would automatically create calendar entries for me and answer questions I had about my schedule. I used my data science skills to create a chatbot that classified messages and generated appropriate responses. But I didn't know anything about web development and wasn't sure where to start. So I took an online course in web development. I figured out how to build a web app that integrated with the chatbot and Google Calendar's API and set up servers to host it online. In the end, I needed both data science skills and software engineering skills to build my calendar app. But it was worth it because I was able to bring my vision to reality with this powerful combination of skills. It can seem intimidating to start learning about software engineering and how to apply it to your data science work. But that's why we're here, to walk you through it. I gained valuable knowledge and skills with resources online and on the job, and I know you can too. Andrew and I will be showing you some of the tricks we've learned so that you can start incorporating useful software engineering practices as a data scientist. Welcome to part 1 of software engineering practices. Here, we will go over a few techniques that we can adopt as data scientists to be better developers and prepare for production level code. You will learn how to write clean and modular code, improve your code's efficiency, document effectively, and use version control. These are all essential skills to develop as a programmer and will really help you when implementing production solutions. In addition, data scientists often work side by side with software engineers, and it's important you work well together. This means being familiar with standard practices and being able to collaborate effectively with others on code. Let's walk through each of these practices and learn how they are applied as a data scientist. The first practice we'll talk about is writing code in a way that is clean and modular. Data scientists often struggle with this when they first start coding, or even if they've been coding for years in a more research or academic setting. When you're working in industry, your code could potentially be used in production. Production code just means code that is run on production servers. For example, when you're on your laptop using software products like UDACITY, Google, or Amazon, the code that's running the service you're using is production code. And ideally, code that's being used in production should meet a number of criteria to ensure reliability and efficiency before it becomes public. For one, the code needs to be clean. Code is clean when it's readable, simple, and concise. Here's an example in plain English of a sentence that is not clean. One could observe that your shirt has been sullied due to the orange color of your shirt that appears to be similar to the color of a certain kind of juice. This sentence is terribly redundant and convoluted. Just reading this makes me frustrated. This can be rewritten as, "It looks like you spilled orange juice on your shirt," and accomplish the same thing. But this sentence is much more concise and clear. writing clean code is very important in an industry setting, where you're on a team that's constantly iterating over its work. This makes it much easier for yourself and others to understand and reuse your code. In addition to being clean, your code should be modular, meaning your program is logically broken up into functions and modules. In programming, a module is just a file. Similarly to how you can encapsulate code in a function and reuse it by calling the function in different places, you can encapsulate code within a module or file and reuse it by importing it in other files. We will see examples of this later. To get a better understanding of what modular code is, try to think of it as putting your clothes away. Sure, you could just put all of your clothes in a single drawer, but it wouldn't be very easy to find anything. And maybe because you can't ever find anything, you have multiple versions of the same shirt or socks because you repurchased them when you couldn't find them. It would be much better if instead you had a drawer for t-shirts, another one for dress shirts, another for socks, and so on. With this design, if you need a nice outfit for an interview, you don't need to worry about buying one just because you couldn't find the right clothes. And if you need to tell someone else how to find the right shirt, pants, and pair of socks, it will be much easier with this design. The same is true in writing modular code. Splitting your code into logical functions and modules allows you to quickly find relevant pieces of code. You can often generalize these pieces of code to be reused in different places to prevent yourself from writing extra unnecessary lines of code. Abstracting out these details into these functions and modules can really help in improving the readability of your code. Again, programming in a way that makes it easier for a team to understand and iterate on is crucial for production. In this lesson, you will get practice writing code that is clean and modular to help you accomplish this. When you first sit down to start writing code for a new idea or task, it's easy to pay little attention to writing good code and focus more on just getting it to work. So your code typically gets a little messy and repetitive at this stage of development. This is okay. It's hard to know what's the best way to write your code before it's finished. For example, it could be difficult to know exactly what functions would best modularize the steps in your code if you haven't experimented enough with your code to understand what these steps are. That's why you should always go back to do some refactoring after you've achieved a working model. Code refactoring is a term for restructuring your code to improve its internal structure without changing its external functionality. Refactoring gives you an opportunity to clean and modularize your code after you've produced code that works. In the short term, you might see this as a waste of time, since you could be moving on to the next feature. However, allocating time to refactoring your code really speeds up the time it will take you and your team to develop code in the long run. Refactoring your code consistently not only makes it much easier to come back to it later, it also allows you to reuse parts for different tasks and learn strong programming techniques along the way. The more you practice refactoring your code, the more intuitive it becomes. You'll start to find yourself writing more organized code on your first pass, with less to reorganize when you go back. Let's take a look at a couple of examples and get some practice. Now that you understand the importance of developing in a clean and modular way, let's break down what this means in code. The first tip for writing clean code is to use meaningful, descriptive names for your variables and functions. This can help you explain most of your code without comments. Take a look at this code that initializes a list of student test scores, prints the mean, curves each score by multiplying its square root by 10, and then prints the mean of the new curved scores. With this code, you wouldn't know what was happening right away without these comments. See how this compares to this cleaner code, which conveys the same purpose without the comments. Now we know what both of these lists stand for without the comments, which will help us throughout the program wherever these variables are used. We also use the function with a descriptive name, mean, instead of running a calculation each time. This not only helps readability, but follows the dry principle, or don't repeat yourself, that is important to writing modular code, which we'll talk more about later. In addition, we imported the math module to use its square root method, instead of raising each score to 0.5 with double asterisks, which isn't only more readable, but also faster in Python 3. Try testing how effective your names are by asking a fellow programmer to guess the purpose of a function or variable based on its name, without looking at your code. Coming up with meaningful names often requires effort to get right. Here are some guidelines. Let's start with the first guideline. Be descriptive, and when appropriate, try implying the type of whatever you're naming. Notice we call this list age list instead of ages, which helps us avoid confusing the integer age and the list of ages later in this code. For Booleans, it's often helpful to prefix the name with words like is or has, to make it clear that it's a condition. You can also use parts of speech to imply types by using verbs for functions and nouns for variables. Normally, you don't want to use abbreviations unless the word will be used many times, and you especially don't want single letter names. However, exceptions include names for counters, such as I in this example, as well as common variable names used in math, like x, y, t, and so on. Choosing when these exceptions can be made can be determined based on your audience for the code. If you work with other data scientists, certain variables may be common knowledge, while if you work with full-stack engineers, it might be necessary to provide more descriptive names in these cases as well. However, long names do not always mean meaningful names. You should be descriptive, but not with more characters than necessary. This first example is very verbose. This function computes the number of unique values in a list, regardless of what that list is. So we can generalize and remove of names list from the function name, and replace the argument name with r, which is standard to represent an arbitrary array. In addition, implementation details are unnecessary to include in a function name, so we can remove with set from the function name as well. The resulting function is much more clean and concise, while still being descriptive. Another tip for writing clean code is to use whitespace properly. Code with poor or inconsistent spacing is the worst. Take a look at this mess. If you were handed this code as a developer, the first thing you should do is fix the whitespace and make it consistent. This is much nicer to read and work with. Organize your code with consistent indentation. The standard for Python is using 4 spaces for each indent, unlike we have here. Also be sure to separate sections with blank lines to make it easier to organize and read. And lastly, try to limit your lines to around 79 characters. 79 is the guideline given in the PEP 8 style guide. In many good text editors, there's a setting to display a subtle line that indicates where the 79 character limit is. Notice how much clearer it is to read this Mongo query in this code, with shorter lines and proper indentation. Also notice how much cleaner this ending part of the code is, where we call create plot. For more guidelines on this, check out the code layout section of PEP 8 in the notes below. If you recall from earlier in the lesson, writing modular code is a necessary practice in software development, where you split your program into logical functions and modules. Let's go over some guidelines to help you with this.
First, don't repeat yourself. Modularization allows you to reuse parts of your code. Let's go back to the example earlier on grading test scores. Here, we have a list of test scores that we curve in 3 different ways. Say you're an educator who gave out a test that was too difficult, or gave a question that was a little unfair. So you decide to figure out a way to boost your students' scores. For the first 2 methods, we add a flat curve of 5 points to each score and 10 points to each score. In the third method, we apply a square root curve, where we find the square root of each score and multiply it by 10. Right now, it's difficult to understand what this code is for and looks pretty repetitive. This is an example of spaghetti code, which is common in data scientists and is not something we want to follow. Let's use the tips we learned earlier on writing clean code and improve this with better naming and readable functions. We can represent this list of scores better with something descriptive, like test scores, and use NumPy to get the mean of each list. We can also use list comprehensions to make this more concise and readable, and use more descriptive names for the score and resulting list. Our code is clearer now, but still needs more refactoring. First of all, these lines applying a flat curve of 5 and 10 look awfully similar. We can generalize this in one function, and we can also consolidate all of these print statements into a for loop. This actually demonstrates the next tip. Abstract out logic to improve readability. Notice how abstracting out code into a function not only makes it less repetitive, but also improves the readability with descriptive function names. You can easily guess that this line is applying a flat curve of 5 on a test scores list, and that this line is doing the same thing with 10. And this line applies a different curve using square root. And with this for loop, not only are we removing repeated lines of code, it's also easier to follow what's happening. We are clearly iterating through 4 lists and printing the mean of each. Note that although your code can become more readable when you abstract out logic into functions, it's possible to over-engineer this and have way too many functions. So use your judgment. This leads us to the next tip. Minimize the number of entities, like functions, classes, and modules. There are trade-offs to having function calls instead of inline logic. If you've broken up your code into an unnecessary amount of functions and modules, you'll have to jump around everywhere if you want to view the implementation details for something that may be too small to be worth it. It's kind of the same as naming variables. A longer variable name doesn't necessarily equate to increased readability, the same way creating more modules doesn't necessarily result in effective modularization. Moving on to the next tip, make sure that each function you write is focused on doing one thing. For example, you wouldn't want something like this. This is the same thing we had before, except now each curve function also prints the mean, in addition to returning the adjusted list. Avoid having unnecessary side effects in functions and keep them focused. Even if you rename them this way, to indicate that they're printing the mean, the functions are still doing multiple things and become more difficult to generalize and reuse. Generally, if there's an AND in your function name, consider refactoring. Another tip is that arbitrary variable names can be more effective in certain functions. Notice that in these functions, we broke some rules on using descriptive variable names. This is because arbitrary variable names in general functions such as this can actually make the code more readable. Flat curve doesn't actually have to be for test scores. It can be used on any iterable that you want to curve up by a certain integer. While we're on the topic of writing simple and focused functions, another useful tip is to make sure that you use no more than 3 arguments when possible. Of course, this is not a hard rule, and there are times it's more appropriate to use many parameters. But in the vast majority of cases, it's more effective to use fewer arguments. Remember, we are modularizing to simplify our code and make it more efficient to work with. If your function has a lot of parameters, you may want to rethink how you're splitting this up. With this small example, you saw how functions can be used to abstract out parts of a program to make it more readable, clear, and reusable. This becomes more essential the more complex your algorithms are, especially in data science work.
When you refactor, it's important to improve the efficiency of your code in addition to making it clean and modular. There are two parts to making code efficient: reducing the time it takes to run and reducing the amount of space it takes up in memory. Both can have a significant impact on a company or product's performance, so it's important to practice this. It's especially important if you'll be working in a production environment. However, it should be noted that how important it is to improve efficiency is context dependent. Slow code might be passable in one case and not another. For example, some batch data preparation processes might not need to be optimized right away if it runs once every 3 days for a few minutes. On the other hand, code used to generate posts to show on a social media feed needs to be relatively fast since updates happen instantaneously. Again, you may spend a lot of time refactoring to clean or optimize your code after you already have something working. It's important to understand how valuable this is for your work and yourself as a developer. Each time you optimize your code, you'll pick up new knowledge and skills which will make you a more efficient programmer over time. Let's see a few examples of inefficient code and practice refactoring to optimize their performance.
Let's go through an example scenario where we optimize some code to be more efficient. Say we are managing books for a store, and we want to find all the books published within the last 2 years about code. We have a file that lists all the IDs of books published in the last 2 years, called bookspublished last2years.txt, as well as a file for all coding books, allcodingbooks.txt. Since we want to find all the coding books published within the last 2 years, we'd want to find the book IDs included in both of these files. Your coworker came up with one approach and shows you this code to find the books in both files. After reading in the files, their strategy is to loop through each book in the first file, check if it's contained in the second file, and if so, add it to the final list. This makes sense and is an intuitive first approach. Let's see how long it takes to run. So that took about 13.6 seconds. There are several things we can do to make this more efficient. Here are some tips. First, use vector operations over loops when possible. NumPy and pandas are your best friends for this. There are many cases in which you can replace loops with NumPy and pandas functions that use vector operations to make your computations a lot faster. Sometimes there's a method that does exactly what you need. Other times, you need to be a little creative. This example in particular has a useful method you can use. Let me show you how I would approach this. No joke, I Google how to find common elements in two NumPy arrays, and here are the results I get. Use NumPy's intersect1d method to get the intersection of the recent books and coding books arrays. I'll give you this same notebook, and I'll put a cell right here with code to record the time it takes to run. Write your line of code in this line. The second tip is to know your data structures and which methods are faster. In addition to relying on NumPy and pandas, it's often good to double check whether there's a data structure or method in Python that you can use to accomplish your task more effectively. For example, in this case, do you recall a data structure in Python that stores a group of unique elements and can quickly compute intersections and unions of different groups? Sets. You can read more about why sets are more efficient than lists for this task in the link at the bottom of this page. Also, remember how I said I Googled everything? Last time, I was Googling how to find common elements in specifically NumPy arrays. But you can go even more general and Google something like how to find common elements in two lists Python, and you'll see posts like this that share and compare different answers. You can see the set being introduced here. This seems to have a lot of votes, but ultimately we should try different methods and compare their efficiency for our example. Because different methods perform differently in different contexts, it's smart to always test for yourself. In the next cell of the Jupyter Notebook, find out how long it takes to compute the common elements of recent books and coding books using the Python sets intersection method. Here again is some code to measure how long it takes. Documentation is additional text or illustrated information that comes with or is embedded in the code of software. Documentation is helpful for clarifying complex parts of your program, making your code easy for yourself and others to navigate, and quickly conveying how and why different components of your program are used. There are several types of documentation you can add at different levels of your program. First, you can add documentation at the line level, using inline comments to clarify your code. Second, you can add documentation at the function or module level, using docstrings to describe its purpose and details. Finally, you can add documentation at the project level, using various tools such as a README file to document details about the project as a whole and how all the files work together. In the next few sections, we will practice using these different modes of documentation and learn best practices to make sure our documentation is effective and useful. The first mode of documentation we'll talk about are inline comments. By now, you've probably seen this many times. Text following a hash symbol throughout your code. They're used to explain parts of your code and really help future contributors understand your work. There are different ways comments are used, and definitely differences among great comments, okay comments, and even useless comments. One way comments are used is to document the major steps of complex code to help readers follow. For example, with the guiding comments in this function, you don't really need to understand the code to follow what this function does. If I was seeing this for the first time and had no idea what these functions or tools were, these comments really help me understand the purpose of each block of code and even help me figure out individual lines of code or methods. However, others would argue that this is using comments to justify bad code, and that if code requires comments to follow, it's a sign refactoring is needed. Comments are valuable for explaining where code cannot. For example, the history behind why a certain method was implemented in a specific way. Sometimes an unconventional or seemingly arbitrary approach may be used because of some obscure external variable causing side effects. These things are difficult to explain with code. These numbers for detecting edge levels in an image may seem arbitrary, but the programmer experimented with different numbers and realized that this was the one that worked for this specific use case. Docstrings, or documentation strings, are valuable pieces of documentation that explain the functionality of any function or module in your code. Ideally, all of your functions should have docstrings. Here's a function for population density. A docstring is always surrounded by triple quotes. If you feel that this one line of documentation is sufficient for you to end the docstring at this point, single-line docstrings are perfectly acceptable. If, however, you think that the function is complicated enough to warrant a longer description, you can add a more thorough paragraph after the one-line summary. The next element of a docstring is an explanation of the function's arguments. Here, you list the arguments, state their purpose, and state what types the arguments should be. Finally, it's common to provide some description of the output of the function. Every piece of the docstring is optional. However, docstrings are a part of good coding practice. They assist you and future users of your code in understanding the code you produce. You can read a more thorough explanation of docstring conventions in the link below. As a prerequisite to this course, you should have already learned how to use Git for version control.
If, however, you need a refresher, check out the course linked in the extracurriculars. To familiarize yourself with how you may use version control at work, we'll first take a look at an example scenario where you are a data scientist using Git at work. We'll practice the commands you'd use in these type of scenarios, and then we'll go over some of the unique challenges and techniques for versioning data science work. Imagine you're part of a data science team that's responsible for building a company's recommendation engine. You're sitting at your desk working on a feature that incorporates demographic data like age, gender, and relationship status to improve recommendations to users. You're midway through this implementation when your boss comes over to notify you that the business intelligence team predicts that a user's friend groups would produce the best recommendations in the short term and wants you to prioritize this immediately. Looking at the recommendation engine code you have on your screen, you can see there's a bunch of unfinished, non-working code that you've added while working on the demographic feature. Running this code right now would break. If you want to get started on this new friend groups feature now, you'd have to undo all of this work, maybe by editing back lines you've modified and commenting out lines of code you added. This would be a very messy and risky route. Or, say you're using a version control system like Git. You can simply commit your changes and create another branch for this new feature. Here's what I mean. Your company has a Git repository for its recommendation engine and has a master branch, which holds the code used in production, and the develop branch, which holds the latest stable version of code with changes for the next release. You have a local version of this repository on your laptop, and to get the latest stable version, you pull from the develop branch. When you start working on this demographic feature, you create a new branch for this called demographic, and start working on your code in this branch. However, in the middle of your work, you need to work on another feature, so you commit your changes on this demographic branch and switch back to the develop branch. From the stable develop branch, you create another branch for a new feature called friend groups. After you finish your work on the friend groups branch, you commit your changes, switch back to the development branch, merge it with the friend groups branch, and push this to the remote repository's develop branch. Now, you can switch back to the demographic branch to continue your progress on that feature. As you can see here, proper use of Git commits and branches can help you work on multiple features at once and switch between them with ease. After working on this recommendation feature for a while, you've created a model to produce recommendations based on friend groups. The model is scoring pretty well on your validation set, but you remember it did even better just a few hours ago. You've been experimenting with tweaks to this model, and you're not sure what combination of parameters and tweaks were in place when your model scored the highest. Luckily, you've been including a message with each commit noting what you did, as well as the training and cross-validation scores for each commit. Instead of spending a bunch of time trying to retrace your steps from memory, or testing a bunch of tweaks again to try and get the same score, you can check your commit history, seeing messages of the changes you made and how well it performed. The model at this commit seemed to be scoring the highest, so you decide to take a look. After inspecting your code, you realize what modifications made this perform well and use those for your model. Now, you're pretty confident merging this back to the develop branch and pushing the updated recommendation engine. While you were working on these changes, your coworker, Andrew, has been working on improvements to the documentation of the same recommendation engine on a different branch called documentation. Andrew commits his changes to the documentation branch, switches to the development branch, and pulls down the latest changes from the remote repository on this branch, which includes the change I previously merged
for the friend groups feature. Then Andrew merges his documentation branch to the develop branch on his local repository, and then pushes his changes up to update the develop branch on the remote repository. After the team reviewed both of your work, they merged the updates from the develop branch to the master branch. Now, they push the changes to the master branch on the remote repository. These changes are now in production. Using branches, commit messages, and merging demonstrate just a few ways version control can be used in data science on a team. But the process will vary based on your team. Great job finishing part 1 of software engineering practices. You learned valuable skills that will help you in all of your future programming work as a data scientist. Being able to write code that's clean, modular, and efficient makes you a stronger developer and allows you to easily reuse and share your code. And using effective documentation and version control are such important practices in industry that will really help you in future projects. Congratulations again on completing this lesson. Welcome to part 2 of software engineering practices. In the last lesson, you learned how to write good code that's clean, modular, efficient, well-documented, and version controlled. Here, we will go a step further and add robustness to your code with testing, logging, and code reviews. These practices help you ensure reliability and easier maintenance of your code, which is crucial in industry. Before you can deploy your code, it will need to be tested. Writing tests is standard practice in software engineering. However, testing is often a practice many data scientists aren't familiar with when they first start in industry. In fact, sometimes the insights data scientists come up with, which are supposed to be used for business decisions and company products, are based on the results of untested code. This lack of testing is a common complaint from other software developers working with data scientists. Without testing, not only do you run into execution errors in code due to software issues, you can also be dictating business decisions and affect products based on faulty conclusions. Today, employers are looking for data scientists with the skills to properly prepare their code for an industry setting, which means tested code. It's pretty obvious when a software program crashes. You get an error and the program stops running. However, there are many problems that could occur in the data science process that aren't as easily detectable as a functional error that crashes your program. All of your code can seem to run smoothly with you completely unaware that certain values were being encoded incorrectly, features were being used inappropriately, or unexpected data were breaking assumptions that your statistical models are based on. These errors are more difficult to find because you have to check for the quality and accuracy of your analysis in addition to the quality of your code. Therefore, it's essential that you add proper testing to avoid unexpected surprises and have confidence in your results. In fact, testing has proven to have so many benefits that there is an entire development process based on it, called test-driven development. This is a development process where you write tests for tasks before you even write the code to implement those tasks. We'll talk more about this later. For now, we will get some practice writing tests, specifically unit tests. A unit test is a type of test that covers a unit of code, usually a single function independently from the rest of the program. First, you'll learn how to write unit tests in plain Python, and then how we can use additional tools to make them better. Finally, you'll see examples of types of tests you'll see in data science. Let's say you wanted to test a function that finds the nearest perfect square less than or equal to a certain number. Your first approach might be testing it interactively in a terminal or Jupyter notebook, like this. So first we'll import the function from the file, and now we'll start testing it with different values. So let's try 5. That should return 4, since that's the nearest perfect square less than or equal to it. And let's try a negative number, which should return 0, which does. And now let's try an actual perfect square, 9, which should return 9. And let's just try another one, 23, that should return 16. So awesome. While this does test the function, it's still a poor way to test because it isn't repeatable, requires you to type these in manually, and doesn't tell you whether it's returning the correct answers. Imagine you have hundreds of functions you need to test and test repeatedly while iterating on your project. You can see how inefficient and unreliable of a method this approach would be for that. After this, you may consider putting your test code into a file to make it repeatable, and end up writing this. This is better because your test code is now in a file that you can run to repeat the same tests without much work. But it's still not telling you whether it's getting the right answers. You'd still have to check. 5, the lowest one was 4, that's correct. Negative 12, oh yeah, that's 0. Still pretty slow. If we print the correct expected result with each answer, now we do have a clear way to check out the results. However, we still need to check these results manually. You have to compare what they returned and the correct answer yourself. This is not ideal if we're running a large amount of unit tests often. We can use assert to ensure that each result is identical to the correct answer. This is much better since it checks our results automatically. However, look what happens when something fails. Let's say I didn't put this equal sign and I only put a less than sign. The result is messy and it stops the program. Ideally, running a test should run all the unit tests and let you know which ones failed and which ones succeeded. This can't happen if it stops with every failure. Any tests that happened after this one failed, we can't see the results of. In addition, the message for a failure is messier than it needs to be. Fortunately, there are great tools available in Python that we will use to create effective unit tests. PyTest is a great tool that lets you start testing quickly without any boilerplate code. To install it, pip install PyTest like this in your terminal. Once you have PyTest installed, all you have to do is create a test file and write a function for your unit test. Then enter PyTest in the directory of your test file. Each dot next to the name of the test file represents a successful test. If you made a mistake in your function and one of your tests fail, the dot will be replaced by an F, and the error will be shown below. Notice your tests won't be stopped by failed assert statements. It continued to run the test after this failed one, but it will stop if you do have syntax errors. It's wise to have only one assert statement per test. Otherwise, you wouldn't know exactly how many tests failed and which tests failed, since all you see is what test functions failed. Another important note is that you have to start your test files with test underscore and your test functions with test underscore as well, for PyTest to recognize and run them. This is the default. If you wish to change this, you can do so by learning about the PyTest configuration in the link below. Test-driven development is when you write tests before you write the code that's being tested. This means your test would fail at first, and you'll know you've finished implementing a task when this test passes. This way of developing code has a number of benefits that's made it a standard practice in software engineering. As a simple example, let's say you have to write a function that checks whether a string is a valid email address. You think of a few factors to consider, such as whether the string contains an @ symbol and a period, and write out a function that addresses them, and then test it manually in your terminal. You input one valid and one invalid email address to make sure it works properly, and it does. You try a few more valid and invalid email addresses, and one of them gives back the wrong result. You realize you forgot to consider an edge case in your function, so you go back and add that in. Then you test your function with another edge case you forgot to consider, and edit your function again to fix this.
Instead of doing all of this back and forth, you can try to create a test that checks for all the different scenarios and edge cases you can think of before even starting to write your function. This way, when you do start implementing your function, you can run this test to get immediate feedback on whether it works or not in all the ways you can think of as you tweak your function. If your test passes, you know your implementation is done. In the future, when you refactor this function or make changes to other parts of your program, you can keep running this test to ensure your function still behaves as expected. This also helps ensure that your function behavior is repeatable, regardless of external parameters, such as hardware and time. When you first start writing tests, you will be slow, and you will be tempted to write implementation code before you write tests. Stick with it though, and through practice, you will get faster. Eventually, you'll be able to write all kinds of tests in very little time. Being able to log well is a very useful practice in software engineering, and especially useful in data science. Imagine you're running a model every night, and when you come into work one morning, you see that it crashed or started creating poor results. You want to check the cause, the context, and figure out how to address the issue. Since you weren't physically there to see and debug when the issue occurred, it's important to print out descriptive log messages to help you trace back your issue and understand what's happening in your code. In the next video, we'll look at some examples of good log messages and see useful logging tools available to us. Code reviews are a common practice at work, and for good reason. Reviewing each other's code can help catch errors, ensure readability, check that standards are being met for production-level code, and share knowledge among a team. They are beneficial for the reviewer, the reviewee, and the team. Ideally, a data scientist's code is reviewed by another data scientist, since there are certain errors and standards to check for specifically in data science. For example, data leakages, misinterpretation of features, or inappropriate evaluation methods. Let's walk through an example of conducting a code review. Congratulations on completing this lesson on software engineering practices. This was just an introduction, as this is a very large set of skills that you should work on continuously. By getting through this lesson, you've made a good start to your development of software engineering skills. I encourage you to research further and practice using these skills as you continue your path to becoming a great data scientist.
Hi, welcome to the lesson on object-oriented programming. You're about to do something that I bet many data scientists have never done before: build a Python package from scratch. Have you ever thought about how the scikit-learn, pandas, and scipy packages actually work? I mean, underneath the hood. Like, what exactly does it mean when your code says import pandas as PD and then pd.read_CSV? You might not have known it, but you were using object-oriented programming. In fact, all of these packages are built using object-oriented programming. You'll find that object-oriented programming allows you to create large, complex, modular programs like the scikit-learn package. This lesson has two parts. First, you'll familiarize yourself with object-oriented programming syntax. Then you'll build a Python package for analyzing probability distributions. By the end of the lesson, you'll have a Python package that you can use as part of your professional portfolio. You'll also gain insight into how Python packages actually work. Let's get started with object-oriented programming. When you first learned to program, you were probably using a style called procedural programming. A procedural program is essentially a list of instructions that execute one after the other, starting from the top of a file and working down. Object-oriented programs, on the other hand, are built around Well, objects. You can think about objects as things that exist in the real world. Like, if you were going to build a clothing store, the store itself would be an object. The items in the store, like shirts and jeans, would also be objects. The cash register would be an object, and even a salesperson would be an object. An object-oriented program would focus on the individual characteristics of each object and what each object can do. So an object has two essential parts: characteristics and actions. For example, a few characteristics of a salesperson would include the person's name, address, phone number, and an hourly pay. In terms of what a salesperson could do, that might include selling an item or taking an item from a warehouse. As another example, a shirt's characteristics could be the color, size, style, and price. What actions could a shirt take? It might sound silly to ask a question like that since a shirt is an inanimate object, but a shirt could, for example, change its price. As you gain experience writing object-oriented programs, keep this idea in mind. An object has characteristics and actions. Before you start coding, let's get a better sense for what an object really is. We're getting close to writing some code, but I first want to clarify some terms associated with object-oriented programming. I said that an object has characteristics and actions. These characteristics have a specific name. They're called attributes, and the actions are called methods. Going back to the shirt example, the color, size, style, and price would be attributes. The action of changing the price would be a method. There are two more terms I want to differentiate for you: object versus class. Here's a reminder of what I mean by object. To continue with the shirt example, an object would be a specific shirt, like a yellow shirt, size medium, short-sleeved style with a price of $15. The yellow shirt could change its price. Another object would be a different shirt, like a green, small, long-sleeve shirt that costs $20. The green shirt could change its own price as well. Do you notice anything special about the yellow shirt and green shirt? They both have the exact same attributes. In other words, they both have a color, size, style, and price. They also have the same method. It's like they came from a blueprint, a generic shirt consisting of all the attributes and methods. This generic version of an object is called a class. You've just hit on the power of object-oriented programming. You only need to define this blueprint, known as a class, one time, and then you can create specific objects from the class over and over again. In other words, you can use the shirt blueprint to make as many shirt objects as you want in any size, shape, color, style, and price. Keep this picture in your head of how the words class, object, attribute, and method relate to each other. These are fundamental terms in object-oriented programming, and I'll be using them throughout the lesson. We're going to see what all of this looks like with Python code. First, I'll give you an overview of object-oriented programming syntax. Then you can play around with my code and you'll write your own class. Let's get right into it and see how to write a class in Python. If you haven't worked with classes before, the syntax might be a bit confusing, but we'll go through some code step by step. For now, I'm going to show code using Jupyter Notebooks, but later in the lesson, you'll be modularizing code into Python scripts. In the top cell, I've written a shirt class, like what we were just talking about in the previous video. The class has color, size, style, and price attributes. I also wrote a method to change the price, as well as a method to output a discounted price. The code cells that come after this first one show some examples of how to instantiate shirt objects so that you can see how to use a class in a program.
I'll start at the top of the file and work down. The very first line tells Python that I'm going to write a class, and then I name the class shirt. Good coding practice says to capitalize the first letter in a class name, but your code will still work even if you don't do this. You can put parentheses after shirt or not. The code will run either way. The next line takes care of initializing all of the attributes with the appropriate values. Remember that a class represents a blueprint, hence I'm setting up the color, size, style, and price of a generic shirt. You'll see how the initialization of a specific shirt object works in a minute. There are two things about this that might look a bit funny. The underscore, underscore, init, underscore, underscore function, and also the self variable. The init function is built into Python. Python knows to use this function to create a specific shirt object. Again, bear with me for now. I'll go back to this in a minute. The self variable can be tricky to understand at first. Self stores your attributes like color, size, etc., and makes those attributes available throughout your class. Self is essentially a dictionary that holds all of your attributes and the attribute values. Check out the change price method to see how self works. I pass in self as the first method input so that I can have access to the price. Self has the price stored inside it, as well as the other attributes like color, size, and style. Self is always going to be the first input to your methods if you want to access the attributes. Note as well that the change price and the discount methods are like regular Python functions. For example, Python functions do not have to return anything. So like in the change price method, it doesn't return anything. It only changes the value of the price attribute. The discount method, on the other hand, does return something. It returns the discounted price. Again, the shirt class is just a blueprint. I'm going to run this first cell and then move on to the second cell. Let's see how to actually use this class. The following are some examples. If I want to create an actual shirt object, I use this syntax here. This is called instantiating an object. Notice that the syntax and order matches the init function. I'm initializing this specific shirt with the color, size, style, and price, just like in the init function. Python is going to call the init function to initialize this t-shirt object. I'm going to run the code cell. Okay, the output here is a shirt object, and then all of those funny numbers and letters at the end is Python giving the location in memory where the object is stored. But this isn't very useful unless we actually store the object in a variable. So in the next code cell, I'm doing exactly that. I'm going to run this code cell, and now I've stored this shirt object in the variable new shirt. The new shirt variable has a color, size, style, and price associated with it. You can access these attributes using this dot syntax. So I'm going to run this next code cell, and you'll see the output. Scrolling down, you use the same dot syntax to access the methods as well, except you also need to specify any inputs that these methods require. For example, to change the price, I call the change price method with a value of 10. Running this code cell, you now see that the price attribute has changed from 15 to 10. The same goes for the discount method. I input 0.2 to the discount method, and it returns a value of 8 because that's a 20% discount off the price. In this last part, I instantiate 3 shirt objects and then store those objects in a list. The reason I'm showing you this is to emphasize that these variables are like any other Python variable. Here are the results. Once I've stored the shirts into the t-shirt collection list, I then run a for loop and print out the color of each shirt. If you're new to object-oriented programming, all of this might feel overwhelming. My suggestion is to watch this video again and then move on to the next part of the lesson where you can play around with this code and write your own class. The most important thing you can do is practice. Write your own class, run the code, and debug any error messages you get. There are a couple of notes I wanted to mention about object-oriented programming. In the first part of the lesson, you'll be doing coding exercises in Jupyter notebooks. When writing software, however, you generally wouldn't write object-oriented programs in a Jupyter notebook. Instead, you would modularize the code into separate Python scripts. In the second half of the lesson, you'll be modularizing code. So here, I'm going to give a preview of what's to come later in the lesson. If you haven't seen this particular interface in other Udacity courses or lessons, this is called a workspace. It's embedded in the classroom, and you'll use it later in the lesson. This is a Linux Ubuntu environment where you can write and execute Python code. In one file, I've put the shirt class code and called the file shirt.py. Now I'm going to write a separate Python script that uses the shirt class code. In the same folder, I've created another file called example.py. Inside example.py, I want to use the shirt class. First, I need to import the shirt class, typing from shirt import shirt. The lowercase shirt refers to the shirt.py file. The uppercase shirt refers to the class defined inside this file. I could name the file and class anything I wanted to. They don't have to be the same. I just did this for convenience. Now, in example.py, I can use the shirt class just like what you did in the previous exercise. The difference is that the code is now modularized. I'll write some code that uses the shirt class. And finally, I'm going to run the code in the terminal. First, I'm going to change the directory I'm in to make sure I'm in the directory with the Python files. And then I'm going to type python example.py. Okay, so the output are the print statements I had in the code. On a separate topic, I wanted to mention how to access attribute values and change attribute values in Python. The shirt class has a method to change the price of the shirt. Like you can see in line 9 in example.py, shirt_2.changePrice 45. In Python, you can also change the values of an attribute with the following syntax. Shirt_1.color equals red. Shirt_1.size equals large. Let me go back. The shirt 1 is already red, so let's say yellow. And shirt1.price equals 43. There are some drawbacks to accessing attributes directly versus writing a method for accessing and displaying attributes. In terms of object-oriented programming, the rules in Python are a bit looser than in other programming languages. In some languages, like C++, you can explicitly state whether or not an object should be allowed to change or access an attribute's values directly. Python does not have this option. Why might it be better to change a value with a method instead of changing a value directly? Changing values via a method gives you more flexibility in the long term. What if the units of measurement change, like the store was originally meant to work in US dollars and now has to work in euros? Here's what I mean. If you've changed an attribute directly, like in line 14, if all of a sudden I have to use euros, I'm going to have to manually change this to say 38. You're going to have to do this wherever you access the price attribute directly. If, on the other hand, you would use a method like the change price method, then all you have to do is go into the shirt class and change the original method one time. I'm just going to multiply by 0.81 to convert everything from dollars to euros. Now if you go back to example.py, a line like number 9, you don't have to manually change the price from dollars to euros because the conversion is going to take care of that for you in the shirt class. For the purposes of this introduction to object-oriented programming, you will not need to worry about updating attributes directly versus using a method. However, if you decide to further your studies of object-oriented programming, especially in another language such as C++ or Java, you'll have to take this into consideration. Now that you've practiced working with all of this new syntax, let's get to the exciting part. In the rest of this lesson, you are going to learn more about object-oriented programming and then use those skills to build a Python package. The package will contain code to analyze Gaussian distributions. You can use the package to read in a data set and calculate the mean and standard deviation.
You'll also include code to plot a histogram of the dataset as well as a probability density function of a Gaussian distribution. And finally, this package will be able to add two Gaussian distributions together. I'm going to start by giving you a tour of what the code looks like and how the code works. Then you'll build up the code yourself. At the end of the lesson, you're going to extend the package to also handle binomial distributions. The best part about this lesson is that you will have an actual functioning Python package that you can pip install using the terminal. If you want, you can even upload the package to PyPy, where Python packages are stored for the general public to download and install. This lesson assumes that you're familiar with Gaussian, also known as normal distributions, as well as binomial distributions. I'll put some resources below if you feel like you need to review them. With that, let's start looking at some code.
To start off, you're going to look at a Python class I've written called Gaussian, and then you're going to code this on your own. You can see that the class has an init method for instantiating an object. There are three attributes: mean, standard deviation, and an empty list for storing data. Notice that the init function includes a default value of 0 for the mean and 1 for the standard deviation. This is like any other Python function where you can specify default values for the inputs. Notice as well, the init has no input for the data attribute. A class attribute does not need to be included in the init input variables. Then I've defined a handful of other methods to calculate the mean of the data, for example here, the standard deviation of the data here, and a method to read in a data file called readDataFile. There are a few other methods as well that we'll get to in a minute. Looking at the readDataFile method, you can see that this method reads data from a file and then stores the data in the data attribute. There's something particularly interesting about the readDataFile method. This code actually calls the calculateMean and calculateStandardDeviation methods from the self variable and then stores the results in the mean and standard deviation attributes. The self variable not only gives you access to the class attributes, but also to the class methods. The Gaussian class has a couple of other methods as well. One plots a histogram using the matplotlib package. I've also included a function for outputting the results of a probability density function, and a plot of a normalized histogram with a probability density function in the same x value range. These are just to give more examples of how you can use class methods. Next, I actually use the class by instantiating an object called Gaussian1. Here I'm going to run that code cell. Because I haven't specified any parameters, the default mean and standard deviation are used. There's a data file called numbers.txt in the same folder as this Jupyter notebook. So I read in the data from that file and then use the other methods to output a couple of plots. In this next part of the lesson, I'm going to give you a skeleton version of this Gaussian class with a few sections marked to do. This is what it looks like. Your task is to fill out the code. The code is already in this video you just went through, but try not to peek back at this video. Follow the comments in the to-do sections and see if you can code the Gaussian class on your own. The file you're going to work with also contains unit tests that you can run to help check your work. They're at the bottom of the file. Let me show you how that works. So if you run this first code cell up here, then you can execute this second code cell, and it'll show you the results of all the unit tests. It says that I have a few errors, a few failed tests, so I need to go back and work on the code. Writing code that you've already seen might seem like a silly exercise, but it should help solidify your understanding of how object-oriented programming works in Python. You'll work on a more challenging coding assignment at the end of the lesson. For now, see how much of the Gaussian class you can rewrite on your own. But don't worry, I've also included an answer file as part of the code. Great work coding the Gaussian class. The more you practice writing object-oriented code, the better you'll get at it. Thinking about Gaussian distributions, do you know what it means to add two Gaussian distributions together? The math is straightforward.
Let's say you have a Gaussian distribution and another Gaussian distribution. You want to sum these together. To find the mean of this new distribution, you add the means of the individual Gaussian distributions together. To calculate the standard deviation, you take the square root of the sum of squares of the standard deviations. Mathematically, there's a clear definition of what it means to sum two Gaussian distributions. But what about in your code? If you instantiate a Gaussian object and then instantiate another Gaussian object, can you type out Gaussian A plus Gaussian B and expect to get the correct result? No, Python doesn't have any idea how to add two Gaussian distributions together. This code is going to produce an error. What if I told you that there was a way to tell Python how to add two Gaussian distributions together? You could type Gaussian A plus Gaussian B and then get a new Gaussian object containing the correct mean and standard deviation. That would be quite magical, wouldn't it? Well, Python has a feature called magic methods that are specifically for overriding default Python behavior. And in the next part of the lesson, you'll practice writing magic methods.
Besides the methods shown in a previous video, I've added two more methods to the Gaussian class. These are the add method and the REPR or representation method. These are both called magic methods. The syntax might look somewhat familiar because you've actually already worked with a magic method. The init function, which initializes a new object, is a magic method. Magic methods let you override and customize default Python behavior. For example, the init method lets you customize how Python instantiates an object. The add method overrides the behavior of the plus sign. I'm going to execute the code cell with the Gaussian class. Below, I've instantiated two Gaussian objects, and then I add them together. Python knows how to add two floats together or two integers together. These operations are defined as part of a Python installation. Adding a Gaussian to a Gaussian, however, has no meaning in Python, so this code should produce an error. I'm going to run it. Well, the code didn't produce an error. That's because I've defined the behavior of adding two Gaussians together. Scrolling back up to the add magic method, you can see how this works. The function has two inputs, self and other. Self refers to the object to the left of the plus sign. Other refers to the object on the right side of the plus sign. I can then define what it means to add these two objects together. Adding two Gaussians together sums the means together and takes the square root of the squares of the standard deviations. Then the code instantiates a new Gaussian object with the new mean and the new standard deviation and returns the new object. For another example, consider the representation method. In Python, do you remember what happens when the only code on a line is a variable? Python will print out the value of the variable. So if I say x equals 5 and then just execute x, Python prints out the value 5. The representation magic method controls what gets printed out. So here the code overrides the default representation behavior to print out the mean and standard deviation of the Gaussian object. Here I'm going to run this line of code so you can see the results. Python has dozens of magic methods. You can override the plus sign, minus sign, division, multiplication, greater than, and less than symbols, just to give a few more examples. To get practice with magic methods, you'll go back to the Gaussian method and rewrite the code you've just seen. If you're getting tired of rewriting code, not to worry. Soon, you'll be converting this Gaussian module into an actual package and then adding more functionality. Here, you can see the clothing class that I was just talking about. It looks a lot like the shirt and pants class that you coded at the beginning of the lesson. The shirt and pants classes inherit from the clothing class. That's why the class declaration of shirt and pants have clothing in parentheses. This tells Python that the shirt class and pants class should inherit all of the attributes and functions of the clothing class. Looking inside the shirt's init method, there's this new syntax where clothing.init gets called. All that means is that a shirt object initializes itself using the clothing's init method. Then you can add any extra attributes like the long or short attribute in the shirt class or waist in the pants class. You could also extend the shirt or pants class by adding more methods. To give an example, I could add a double price method just to the shirt class. You could also override any of the clothing methods. For example, the pants class is overriding the calculate discount method. Remember, one of the main benefits of inheritance is that you can add attributes and methods to the clothing class, and then both the shirt and pants class will have those attributes and methods as well. Study all of this code to get used to the syntax of inheritance. There's one more object-oriented topic to cover in this lesson: inheritance. I think inheritance is easier to understand using a real-world object, like the shirt example from earlier in the lesson. The shirt had 4 attributes: a color, size, style, and price. And the shirt also had 2 methods: a method to change the price and a method for calculating a discounted price. As the store expands, it might stock other types of clothing like pants, socks, and dresses. These garments have a few attributes and methods in common with the shirt object. They'd probably all have a color, size, style, and price, and they could all use functions to change the price and calculate a discount. Why code separate classes for each new garment when they all have so much in common? Instead, you could code a parent clothing class, and then the pants, socks, dresses, and shirt classes could inherit the attributes and methods of the clothing class. This looks like a family tree where clothing is the parent and pants, socks, dresses, and shirts are the children. One benefit is that as you add more clothing types like blouses, you can easily add a new class that inherits from the clothing class as well. What if you wanted to add a new attribute like material to represent if the garment is made of cotton, nylon, or some other fabric? Now all you have to do is add a material attribute to the clothing class, and all the children classes automatically inherit the new attribute. Your code becomes more efficient to write and maintain. Next, I'll go through the Python syntax for inheritance. Then you'll add inheritance to the Gaussian class. To reinforce how inheritance works, I've added an example to the Gaussian class code. I've written a new Python class called distribution. This class is going to be the parent class of both the Gaussian class and the binomial class that you are going to code at the end of the lesson. A lot of the code should look familiar. The init function was the same as the Gaussian init. I've simplified the read data file function so that it only reads in a data set, whereas before this function also calculated the mean and standard deviation of the data. The Gaussian class code has changed slightly. Now the Gaussian class inherits from the distribution class. The init function uses the distribution's init function. Scrolling down, the read data file method is still in the Gaussian class. This is because I wanted to override the read data file method from the distribution class in order to calculate the mean and standard deviation. Even though the code looks a little bit different than before, the Gaussian class works exactly the same way as it did before. It might seem like the changes in the code are superficial, and I'd agree with that. I mostly wanted to introduce inheritance so that you could recognize the syntax. Near the end of the lesson, we're going to look at the source code for scikit-learn. A package like scikit-learn contains many classes that use inheritance. You'll have an easier time understanding the syntax now that you've seen how inheritance works. I've provided this distribution and Gaussian code for you in the next section so that you can play around with it. We're getting close to the end of the lesson. The next step is to modularize all of this code into separate Python files. Then you'll see how to make a Python package. And the last steps will include extending the code to include a binomial distribution and uploading the code to PyPy. So let's start by modularizing this code. From this point in the lesson, you're going to use a Linux environment with Python scripts rather than a Jupyter notebook. Jupyter Notebooks are great for data science, but they're not necessarily the best tool for writing modular software. In the next section, you'll see a classroom workspace like this one containing the code I'm about to show you. On the left-hand side, you'll see a list of directories that you can access. Each section in the rest of the lesson has its own folder. This part of the lesson is discussing the modularized code folder. Let's talk about how to modularize the distribution and Gaussian classes with which you've just been working. In Python, a module is a single Python file that contains a collection of functions, classes, and/or global variables. They're called modules because, well, they're modular, meaning that you can reuse these files in different applications. A package is essentially a collection of modules placed into a directory. If I double-click the folder containing the modularized code, there are 3 files, but these 2 are the most important: GaussianDistribution.py and GeneralDistribution.py. These files contain the same code from the section on inheritance. This folder isn't quite officially a package yet, but putting these files into the same folder is the first step to making a package. Opening the GeneralDistribution.py file, the distribution class code is the same as it was in the Jupyter Notebook. Opening the GaussianDistribution.py file, you can see that it contains the Gaussian class. The code here is almost the same as the code from the Jupyter Notebook. However, notice that the Gaussian distribution file imports the distribution class. This line says, go into the GeneralDistribution.py file and give me access to the distribution class. I want to point out that you can also use the same syntax to import a function from a module, not just a class. But for this lesson, we are focusing on object-oriented programming, so I coded everything inside a class. How can I actually use this Gaussian distribution module in a Python application? You can see an example in the examplecode.py file. This file imports the Gaussian class and then instantiates a Gaussian object. Note as well that my example code file and the Gaussian distribution.py file are in the same directory. You'll see later in the lesson that packages and applications do not need to be in the same directory as long as Python knows where to look for a package. Next, I'm going to open a terminal window and run the examplecode.py file. If you're not familiar with using the terminal, don't worry too much. Each section of this lesson comes with an instruction file discussing how to run commands in the terminal. Typing python /modularized_code/example_code.py and hitting enter runs the Python module examplecode.py. This code prints out the mean of the instantiated Gaussian distribution object, which is 22. In the next section, you'll have the chance to look at this code in more detail. As you might have done before, you install Python packages using pip install. For example, if you want to install the scikit-learn package, you go into a terminal and type pip install scikit-learn. This pip install command downloads packages from an online repository called PyPy. In this case, scikit-learn is already installed, so it's just letting you know. In the remaining parts of this lesson, you're going to set up a Python package and then upload the package to PyPy. The first step is to get the package ready so that it can be pip installed locally on your computer. I'm going to show you how to set up your files so that they can be pip installed. On the left-hand side of the screen, you can see I'm in a directory containing a folder called distributions and a file called setup.py. Let's talk about the distributions folder first. Double-clicking, this folder contains the Gaussian and general distribution classes that you've already been working with. The difference is that this folder is now officially a Python package because the folder contains an init file. A package needs an init file. There's nothing new or different about the Gaussian and general distribution files except for one line. Opening GaussianDistributions.py, you can see the third line where I import the distribution class from the GeneralDistribution.py file. There's a dot in front of general distribution. This dot is required in Python 3 but if you're working in Python 2, you shouldn't need it. The init Python file, on the other hand, is new. The init file is telling Python that this folder contains a package. A package always needs to have an init file, even if the file is completely empty. The code inside the init file gets run whenever you import a package inside a Python program. In this case, the init file is importing the Gaussian class from the Gaussian distribution module. The reason I added this line is because I want to be able to import the Gaussian class directly, writing from distributions import Gaussian. You'll see what I mean in a bit. If I didn't include any code in the init file, the package would still work, but any program that uses the package would have to import the Gaussian class more indirectly with the line from distributions.Gaussian distribution import Gaussian. It's like I'm making a shortcut for importing the Gaussian class directly. Going back up one level in the directory, there's a setup.py file at the same level as the distributions folder. This file is necessary for pip installing. Pip will automatically look for this file. Opening this file, you can see the setup file contains information or metadata about the package, like the package name, version, description, etc. Okay, let's install the package. To install the package, go into a terminal and make sure you're in the directory with the setup.py file. In this case, I'm going to have to change directories and type Python package example. Okay, now I'm in the directory containing the distributions package and the setup.py file. In the terminal, type pip install dot and then hit enter. The dot tells pip to look for the setup file in the current folder. That's it. The Python package is installed. Now I can use the package in my Python code like so. I'm going to open a new terminal. Notice that I'm no longer in the Python package example folder, and it doesn't matter because we've already installed the package. So I'm going to type Python to start the Python interpreter, and then I'm going to import the Gaussian class, saying from distributions import Gaussian, and hitting enter. Okay, now I have access to the Gaussian class, so I can write something like Gaussian 1 equals Gaussian class and initialize it with a mean of 10 and a standard deviation of 5. Hit enter, and now look, I can use the Gaussian class just like we were using it before. And you have access to all the methods as well. So you might ask yourself, where exactly did the package get installed to? The answer is wherever pip installs packages on your system. If you're still in a Python interpreter and type import package, like import distributions, you can then type distributions dot underscore underscore file underscore underscore, hit enter, and that'll tell you where the package is installed. That's all it takes to create and install a Python package locally. In the last part of the course, you're going to expand this package, creating a binomial distribution class. And then you can upload the package to PyPy so that anybody can download and install your package. If you decide to install this package on your local computer, you might want to create something called a virtual environment first. A virtual environment is like a silo for installing Python packages. That way, you won't be messing around with your computer's default Python installation. I'll put instructions on the next page for setting up a virtual environment. I want to show you how virtual environments work in Python. Unfortunately, you might run into different issues depending on your operating system and Python installation. The Classroom workspace uses an Ubuntu Linux operating system and a special Python installation known as Anaconda. In this particular case, there are some issues with the virtual environment package, and a quick fix is to run conda update Python and then hit enter. Running this command takes a while, so I've already done it before recording. If you're not using Ubuntu or Anaconda, you shouldn't need to run this command first. If everything is working correctly and you're using Python 3, the virtual environment package should already be installed. You can type python-m venv and then your virtual environment name and hit enter in the terminal. venv_name is the name you want to give to your virtual environment. You can name it anything you want. If you go over here into the workspace area, you'll see there's a new folder called venv_name. Inside of that is a Python installation. Now you can type source venv_name/bin/activate, hit enter, and you'll see that the virtual environment is now activated. So anything you install now will get installed into the virtual environment instead of your default Python installation. You'll notice that the command line now shows in parentheses the virtual environment name at the beginning of the line, indicating that you're using that virtual environment. Now I'm going to change to the directory where I have my Python package and setup file, and then I say pip install dot like before. Okay, and now I've installed the distributions package into the virtual environment instead of the default Python environment that's installed in the computer. That's really it for virtual environments. The benefit is that you can experiment with Python without affecting your default Python installation. You can always just delete the virtual environment folder from your computer, and there shouldn't be really any consequences in terms of your default Python installation. Now it's your turn. You've practiced the basics of object-oriented programming in Python. Time to show off your skills. In the next section, you'll find the code for the distribution package, but there's also a new file containing a binomial class. Your task is to write the code for the binomial class methods. You'll also have to use all the skills seen so far, including inheritance and writing magic methods. You'll need to code an initialization method, calculate the mean and standard deviation, and fill out other methods similar to the ones in the Gaussian class. Once you've finished coding the binomial class, I've got a few more fun activities in store, including looking at the source code of scikit-learn and instructions for how to put your package on PyPy. Okay, time to write some code. Before you get started writing code, here's a quick overview of the binomial class exercise. The exercise is contained inside this 4a binomial package folder. Inside this folder are quite a few files and a distributions directory. Out of all these files, there are two that you're going to need to modify. First is the init Python file inside the distributions directory here. Currently, the init file only imports the Gaussian class. You'll first need to modify this file to also import the binomial class. Going back, take a look at the binomial distribution file. You'll see that I've put in a bunch of to-do sections to help guide you along. Make sure to read the to-dos so that you understand what the code should look like. Each method also contains a doc string explaining the expected inputs and outputs. You'll see as well that I've included a file called tests.py. This file contains unit tests that you can run to help you determine if your code is working properly. Here's how to use this workspace. First, you'll need to open a terminal and go into the package directory with the command cd 4a_binomial_package. Then you can type pip install dot, which will install the distributions package. The unit tests are in the tests.py file. You can run the unit tests by typing python test.py. As you modify your code, you can run the test.py file to see if your code is working. In this case, it tells me that from distributions import binomial in the test file doesn't work. That's because I never put it in the init file inside the package. As you modify your code, you can run the test.py file to see if your code is working. However, whenever you update the package code, you need to reinstall the package. Otherwise, Python won't be able to see the changes you've made. You can reinstall the package by going to the terminal, again, making sure you're in the package directory and typing pip install --upgrade dot. You'll see that it uninstalls the package and then reinstalls it. That's it. Have fun with this exercise. It really reinforces everything you've been practicing throughout this lesson. Let's go on a tour of the scikit-learn source code. This is really why I wanted you to learn object-oriented programming and how to make a Python package. If you want to understand what packages like pandas, scipy, numpy, or scikit-learn are doing, you need to understand at least the basics of object-oriented programming. As we go through the scikit-learn source code, you'll see some things that are familiar based on what you've done in this lesson, including import statements, classes, and inheritance. You'll also notice syntax that we didn't cover, such as the @symbol, mixins, and cases of multiple inheritance, where a class inherits from 2 or more parent classes. Object-oriented programming is a big topic, and Python has a lot more functionality than what you've seen so far. I'm going to open Google and search for scikit-learn source code. It turns out that the code is hosted on GitHub. Here's the repository. Let's go into the sklearn folder and see what we can find. Okay, I see the linear model folder, which I'm guessing holds code for things like linear regression. At the very top is a tests folder. You can see that writing test code is an important part of developing a Python package, or really any program. Opening up the test folder, you can explore all the different tests that have been written for different functionality. Let's go back up to the linear model folder. Since there's an init file, you know that linear model is actually a package. Opening that file, this code should be somewhat familiar. The init file is importing the classes contained in each of the package modules. This is equivalent to the init file in your distributions package, where you were creating shortcuts to the class names. I'm going to go back. Now I'll open base.py and see what's inside. It starts off with a few comments, and then there are a lot of import statements. So the base.py file is using a lot of other Python modules or packages. Next, there's a variable called sparse intercept delay and a function called makeDataset. As I mentioned in the beginning of the lesson, a Python module can contain any combination of variables, functions, or classes. Scrolling down, this is where things get a little more advanced. The @symbol is called a decorator, and you might not have seen this before. I'll put a resource below the video if you want to learn about decorators. I'm going to scroll down a bit more. Here we are with the first class in the module. It's called linear model, and the class inherits from 2 parent classes, ABC Meta and Base Estimator. Then you can see the linear model class has a few methods. The dash before the decision function is just a convention that usually indicates that the function is only meant to be used internally inside the class and not by an instantiated object. If you want to get involved with contributing to a library like this, check out the issues page. It's at the top of a GitHub page. Here's issues. I'm going to click on it. You can read about the issues and see if there's something that you could contribute to. I'll also put a few links below giving guidelines about how to contribute to a GitHub project. Scikit-learn is a large package with a lot of code. But don't get too overwhelmed. Realize that a package like this was built over time with various people contributing to different parts. But the basic package you coded in this lesson is essentially how a much larger package works. You start small with just a few modules, and over time you add more and more functionality. PyPy, also known as the Python Package Index, is a repository where Python packages are stored. When you pip install a package, you are downloading and installing files from PyPy. Anyone can upload a package to PyPy. I'm going to show you the basics of how to do it. The PyPy website actually has a test repository as well as the regular repository. This is the test repository website. I'd suggest first uploading your package to the test repository to make sure everything works as expected. Then you can upload the package to the regular repository on this website. Remember that anybody can download and install your package if it's in the regular repository. The first step is to create an account on PyPy and the test PyPy repositories. If you go to each website, you can click on Register and make an account. I've already done this, so I'm going to skip this step. Next, go to your terminal and enter the directory with your package files. Let's open this DSND probability folder where the package is located. You'll see that there are a few extra files than what was originally in the package you were working with before. You'll need to add these extra files. The first one is a file called license.txt. Opening that file, this is where you put copyright information. I've used the language for the MIT license, which I copied and pasted from the opensource.org website. Next, you'll also need to add a readme.md file. I haven't filled out this file with enough detail yet, but this is where you would document how your package works. And finally, create a file called setup.cfg. All you need to put in here is some data about the name of your README file. Let's go back up one level and open the setup.py file. You can see I've named my package dsnd_probability. The folder with all the package files is also called dsnd_probability. If you want to upload this code to PyPy, you'll need to come up with a different name. Every package on PyPy needs a unique name. In the setup.py file, in the packages variable, use the same name that you put in the name variable. I'm keeping zip_safe to false because it means that the package can't be run directly from a zip file. This is especially important if your packages rely on data files that need to remain unzipped for use. Again, note as well that I've changed the name of the package folder to match dsnd_probability. I'm going to do a bit of hand waving here, though if you want to read more about how to upload to PyPy, I'll include a link to the documentation. Go to your terminal window and make sure that within terminal, you're inside the folder with your package files. Then type python setup.py sdist. If you look at the package folder, there are now a couple of new folders that appeared. Inside the dist folder is a tar.gz file that you're going to end up uploading to the PyPy repository. Next, go back to the terminal and install the twine package with pip install twine. And then type the following command to upload the package to the PyPy test repository. It's twine upload --repository-url, then https://test.pypy.org/legacy/space/dist/*. This is what it looks like. Hit enter. It asks for my username. This is the username for the test PyPy repository and my password. Okay, so it's giving me an error that says I'm using the same version that I uploaded before. So I'm just going to change this from 1.2 to say 1.3. You might end up having this error as well and having to do the same thing. This is because I've already tried to upload this package before with the same version. So I'm going to go back and I'm going to delete this dist folder and this extra info folder that were created before. And now I'm going to repeat the same steps. Python setup.py sdist. Okay, now I'm going to try again. Twine upload --repository-url. Enter my username, my password. Okay, and this time it looks like it worked. So I'm going to go to the test PyPy website for a second. I'm going to log into my account. And okay, it looks like everything uploaded correctly. Let's go back to terminal for a second. I can now actually pip install this package using the following command. Pip install --index-url https://test.pypy.org/simple/space dsnd-probability. And this says to pip install the package from the test repository website. Okay, it looks like it installed successfully. Assuming that everything goes well and you're ready to upload the package to the regular PyPy repository, here's how you can do that. Type twine upload space dist/star. Enter your username, your password. Okay, and now let's check on the regular PyPy repository website if everything uploaded. I'm going to log in. And okay, it looks like everything uploaded here as well. So remember, we already installed the package from the test website, so I'm going to uninstall it. Since the package is now also on the regular repository, I can pip install directly. I just write pip install and then the name of the package. Okay, and it looks like everything installed correctly. Now I'm going to see if I can use it in a Python program. I'm going to open a new terminal window, and I'm going to open a Python interpreter. And now I'm going to say from dsnd underscore probability import Gaussian and import binomial. Okay, so far so good. So if I say Gaussian 10, 7, hit enter, then it's made a Gaussian object with mean 10 and standard deviation 7. If I type binomial 0.4, 25, hit enter, it gives me the mean, standard deviation, probability, and number of samples. So it looks like it worked. So what I've shown you is the very basics for getting something up and running with PyPy. If you're going to upload the package made in this lesson, make sure you use a different package name than dsnd underscore probability. Otherwise, you won't be able to upload the package because the name will conflict with the package I just uploaded. Also realize that in the package name, I used underscore, but if you go back to the PyPy website, the package gets named with a dash, so that's something to be aware of as well. When you're pip installing, you'll have to use the dash, but then when you're using it in the Python interpreter or in your program, you'd use the underscore. So now it's your turn. Follow the instructions in this video and try uploading your own package to PyPy. This has been quite a journey. You started out learning the basics of object-oriented programming, and you ended up with a Python package that you can share with the world. Let's review all the concepts from this lesson. First, you wrote some basic object-oriented programs using clothing. You coded a few classes and instantiated objects. These objects had a set of characteristics called attributes and a set of actions called methods. Then you started working with a more complex class representing Gaussian distributions. You practiced writing magic methods and writing programs that included inheritance. Next, you converted the Gaussian class into a Python package, and then you added another class called binomial. Once all of this code was ready, you uploaded this package to PyPy. That's a lot of work for one lesson. You should be really proud because, as I said in the beginning, I don't think too many people know how to write a Python package and upload it to PyPy. This object-oriented programming lesson, however, is not the end of the software development class. In the next lesson, you're going to make a web app containing a data dashboard. This is going to expand your software engineering skills and give you another tool for telling stories with data. I hope you enjoyed writing object-oriented programs, and I'll see you in the web development lesson.
Welcome to the deployment section in this Nanodegree program. I'm Jennifer Staub, an expert in cloud computing. My passion for cloud computing was ignited when I began using Amazon Web Services for genomic research at a pharmaceutical company in 2012. Using cloud computing services provides secure supercomputing capability for big data analytics that I could build and manage alone. With this deployment section, you'll be developing, training, validating, and deploying machine learning models using Amazon SageMaker service. While you'll use SageMaker for deployment, the skills you'll be learning are applicable to any production environment that aims to deploy machine learning models and deep learning models with Python. We'll keep this lesson platform neutral. We want to make sure that you get a good foundation in deployment so that you're able to apply this knowledge using any cloud platform in the future. With this lesson, we begin by providing you with an understanding of cloud computing. Next, the lesson will focus on how machine learning is typically used in the workplace. Deployment is a critical part of the machine learning workflow in the workplace. With this final lesson, we'll examine deployment and how it fits within the machine learning workflow. Imagine you're going to take part in a Kaggle competition where you'll predict the median value of a home in Boston, Massachusetts using a provided data set. To better understand this competition, let's take a closer look at the data. Here's some of the data that shows the average number of rooms in a house and that house's median value. It makes sense that the more rooms a house has, the more it will be worth. But there's some variance in the trend due to other factors. For this competition, you use data to train a model and predict the median value of a house, given the number of rooms and other features of the house. Besides your competition submission, your ultimate goal is to deploy your trained model to a smartphone application that you've developed. This application will allow users to discover what Boston houses are worth based upon the house's features. How might you approach this challenge? Well, a common approach is to use the machine learning workflow. We'll discuss this workflow and how it's used next. Let's discuss the details of the machine learning workflow. It's composed of 3 components: explore and process the data, modeling, and deployment. The first step is to retrieve the data. For our Kaggle competition, this is simple. We're given a data set that contains all the housing data that we'll need to train our model. Therefore, this step involves downloading the data, in this case 2 CSV files. Next, we'll clean the data and explore the data. This involves exploring and visualizing our data to identify the most promising features, like relationships between housing values and the number of rooms that can be used in the modeling component. The data may also have to be cleaned to identify and remove any anomalous values such as outliers or mistakes. The final step of this component is to prepare and transform the data. Most machine learning models expect standardized data values. Therefore, this step often involves normalizing and converting the format of the data. In addition, the step is where the data is split into training, validation, and test data sets. Remember, the training data set is used to train the model. The validation data set is used for model tuning and selection, and the test data set is used after training for evaluation of the model. The next component, modeling, focuses on developing the model that's deployed to production. The first step is where the model is developed and trained using the training data set. The final step of modeling is to evaluate and validate the model. In this step, you'll tune the model using the validation data set. You'll also select the model if you've developed more than one trained model in the previous step. The final step is to evaluate your model using the test data set. The final component of deployment focuses on deploying, monitoring, and updating the model in the production environment. This is what we'll be focusing on in this lesson and the rest of the Nanodegree. We'll start with deploying the model to the production environment. Simply put, this means making your model available for use by a web or software application. For our Kaggle example, we'll deploy the model to a smartphone application. This will allow application users to determine the worth of Boston houses based upon a house's features. The final step is to monitor and update the deployed model. With our example, imagine there's a tech boom in the Boston area and it causes a dramatic increase in the median housing prices. To update your model, you'll build and train it using this new data and then deploy it as a new version of the smartphone application. Application users can access the updated model by downloading the updated application. The cyclical nature of the workflow enables user data captured during deployment to be used to create new models. Specifically, the data captured during deployment can be explored and processed in the first component, then used to develop a new model in the second component, and finally deployed to the production environment in the third component of the machine learning workflow. Model deployment is often a critical aspect of machine learning in the workplace. That's why it's good to keep the machine learning workflow in mind. How you've used machine learning at home or in school may differ to how it's used within the workplace. Maybe you've participated in a Kaggle model competition to practice your machine learning skills. Or maybe you've used machine learning algorithms to determine the best model for your academic research. For these examples, only complete the first two components of the machine learning workflow. Specifically, they end once the most ideal model is determined based on performance measures. This differs from workplace usage because deployment is typically a critical part of machine learning in the workplace. Now, there are cases where deployment is included in personal and academic usage. For example, an academic research group has developed a model that predicts the location's risk of mosquito-borne illness with high accuracy rates. Because of the high accuracy rates, these researchers received additional funding to build and maintain a web application that deploys their model. In this way, deployment of this web application can be used by health and government officials to prevent mosquito-borne illness epidemics. For an example of personal usage, deployment, you decide to create a smartphone application. Imagine you're creating a Magic 8-Ball application that provides the user with yes, no, or ask again answers to questions they ask the application. Suppose you design this application so instead of providing a random answer, the application asks the user a series of questions to determine the user's mood using sentiment analysis. Based upon their mood, your application provides the user with an answer to their question. In the workplace, it's quite common to use deployment with the machine learning workflow. Machine learning models are used within an organization's web or software applications for activities like fraud detection, recommender systems, risk assessment, or facial recognition. Each of these activities require new inputs to make a prediction based upon the deployed model. The organization will want to monitor and update their deployed model to make sure it provides the best predictions over time. Now that we've learned how machine learning can differ when it's used in the workplace, we'll focus on deployment for the rest of this lesson. We've learned with deployment, we are simply making our model available for use with a software or web application. This means users can input their data into a model and receive predictions back from the model through the application. Thinking back to our Magic 8-Ball application, users ask a question and provide some additional data to the application. The application sends this additional data to the model, which uses to predict the user's mood. Then the application returns an answer to the user's question based upon the user's predicted mood. Let's imagine there's a company, Oracle's or us, that provides a Magic 8-Ball service. Service users call in and speak to a representative who gathers their additional data. This data will be used to predict the user's mood. The user is put on hold while the representative talks to the typist to give them the additional data to input into the model. The typist then tells the representative the prediction, which they'll use to answer the user's question. Using this example, we can think of the representative as the application, whose responsibility is to interface with the user and gather their data. We can think of the typist as the model, whose responsibility is to take the data and return a prediction. Just like the representative and typist communicate with each other, our application and model communicate with each other to provide user predictions. The environment is the computational system that hosts the application. The type of environment is defined by the kind of user who can access the service. With our example, we're providing predictions to users who are customers, so it's a production environment. If instead users were employees testing the application, it would be a test environment. The application communicates with the model through an interface to the model that's called an endpoint. We'll discuss endpoints in more detail next. I'm Jennifer Staub, an instructor at UDACITY. I'm speaking with Jesse Swidler. He's a senior software engineer at UDACITY.
Hi Jennifer, it's nice to be here today. I've been working on web applications for the last 8 or 9 years, and I'm happy to talk to you today.
So Jesse, as your job as a software developer, how do you find containers useful?
Yeah, well, I think the shipping container analogy of containers is really the best way to understand how containers make our life easier. Before there were shipping containers, it was very difficult to move things around the world, versus now we can put everything in a nice little box, and because they're all in the same box, we can attach them to a truck and drive them to a shipyard and put them on a ship or put them on a big boat. And we can, build big expensive tools, cranes to move these boxes around, pick them up and put them different places. And that's how containers makes our life better. Everything becomes the same and we can develop tooling around that sameness.
So you're saying that using containers in software is similar to our shipping container analogy.
Yeah.
And it just makes life easier because you can have these tools that are developed for a specific container, but it doesn't really matter what's in the container. Like, it doesn't matter what software we're running underneath.
That's right, Jennifer.
Is that like, or I've gone wrong, I've gone astray?
No, that was really, I stalled because, so containers is not a full virtual machine, but for beginners, it's probably useful to think about it that way because you're sharing a kernel with the underlying OS.
So since it's not a full virtual machine, what makes containers special or better that they're not? What are the advantages of not having them as a full virtual machine?
Well, because they're not a full virtual machine, it's lighter weight on the OS, which means the applications can run with very low overhead. So you don't pay a huge penalty for using the container.
So can you tell us how we use containers with the workspace in the classroom?
With workspaces, most of the student environments are put inside of one of these containers. And because of that, we can put the containers in our environment where they can be deployed to all of the students at the same time. We can control authorization to them in the same way. And just like with the shipping containers, we've built tools around exposing containers for students. And without the ability to do that, we wouldn't be able to make new workspaces as easily.
So essentially, workspaces run in containers.
Yeah, in and through containers. All up and down the stack, we use containers.
So basically, when students log on, they're using workspaces, they're essentially using containers.
Yeah. Yep.
So they've already used containers in their nanodegrees already.
Yeah, very directly inside the workspaces, but more generally, every time you use the internet, you are probably using containers on a server somewhere.
Oh, wow. That's really interesting. I never thought of it like that. So what happens if we want to update software in a workspace? How does that affect things?
Well, that's a good thing about containers is we generally build them through build scripts. And because of that, we can just update the script to use the new dependency and run it again. And then we'll have a new container with the updated software.
Wow, that makes updating software really easy.
Yeah.
So how have containers made your job as a software developer easier for you?
Containers has really changed everything about the way I do my job. Because before I used containers, it was difficult to split things up the way you want, And now with containers, most software development for web applications is done via microservices, and we break things down in much smaller, more manageable units.
That makes sense. So it's made your life much easier.
It really has.
Well, thank you today for talking with us today. I really appreciate you talking to us about containers. I feel like now I have a better understanding of containers because I realize how they're connected to the workspaces that we use at UDACITY.
Thanks for talking with me.
With this lesson, you've learned quite a bit about deploying machine learning models within cloud environments. Great job. You initially learned that cloud computing can be simply thought of as transforming an IT product into a service. With our vacation photos example, we transform storing our photos on an IT product, the flash drive, into storing them on a service, like Google Drive. Ultimately, our vacation photos will be stored in a Google data center instead of on our own device. While this provides benefits like easy access and shareability of our photos, using the cloud service also carries security and privacy risks. You've learned how the machine learning workflow is used to build, train, evaluate, and deploy models to a production environment. You discovered deployment is a critical part of the machine learning workflow in the workplace. You understand that deployment is simply making your model available for predictions through a software or web application. You also learned about the characteristics of deployment and the technologies that are used for deployment. In the next lessons, you'll see how to implement these concepts you've learned to deploy your own machine learning models.
Hi, I'm Sean Carroll, and in this lesson, I'm going to introduce you to Amazon's SageMaker service. By the end of this lesson, you should have an understanding of how SageMaker works, and you'll have had a chance to try it out yourself. To start, let's answer 3 big questions. What is it? Why use it? And how does it work? First, what is SageMaker? Well, practically speaking, SageMaker is a combination of 2 very useful tools. The first is a managed Jupyter Notebook instance. This is the same Jupyter Notebook that you know and love, except instead of running in a workspace or on your personal computer, it runs on a virtual machine hosted by Amazon. As you've seen throughout this Nanodegree, notebooks give us a place to explore and process data, and can be used to test ideas before needing more sophisticated and powerful machinery. The second tool provided by SageMaker is an API, which simplifies some of the more computationally difficult tasks we might need to perform, like when we want to train or deploy a machine learning model. So why use SageMaker? The simple answer is that it makes a lot of the machine learning tasks we need to perform much easier. For example, in the machine learning workflow you looked at earlier, SageMaker provides tools to make each of the steps involved simpler. The notebook can be used to explore and process the data, and the API can help simplify the modeling and deployment steps. So how does SageMaker actually work? For the most part, when we talk about using SageMaker, we really mean working in the managed notebook. This notebook has all of the benefits that we talked about before, with the added bonus of having access to the SageMaker API. The SageMaker API itself can be thought of as a collection of tools that deal with the training process and the inference process. The training process is exactly what you think it is. A computational task is constructed. Generally, this task is meant to fit a machine learning model to some data. Then this task is executed on a virtual machine. The resulting model, such as the trees constructed in a random tree model or the layers in a neural network, is then saved to a file. This saved data is called the model artifacts. The inference process is very similar to the training process. First, a computational task is constructed for the purposes of performing inference. Then, this task is executed on a virtual machine. In this case, however, the virtual machine waits for us to send it some data. When we do, it takes that data, along with the model artifacts, which were created during the training process, and performs inference, returning the result. So that gives you a basic understanding of the SageMaker service. Before going into any more detail, let's actually use SageMaker to build our first model.
All right, to start using SageMaker, the first thing we're going to need to do is set up a notebook instance. To do that, we need to sign into the AWS console, which I've done here, and then scroll down, and underneath Machine Learning, we want to click on Amazon SageMaker. This will open up the SageMaker dashboard. From here, on the left-hand side, we want to click on Notebook Instances. As you can see, I don't have any set up currently. To make a new one, we click on this orange button in the top right corner that says Create Notebook Instance. Most of these settings are fine the way they are. However, we do need to name our notebook instance. I'm going to call mine Deployment Notebook. We also need to make sure to set a role. A role acts like a security certificate, letting Amazon know what other resources our notebook will have access to. We need to make sure that we allow our notebook access to S3. To do that, we click on this dropdown and select Create a New Role. The default selections will be perfectly fine. The most important line is the second one here that says any S3 bucket with SageMaker in the name can be accessed by our notebook. Since there are no additional buckets we want to have our notebook access, we'll select none here. A little later on, we'll talk about what S3 is, but for now, just think of it as a place to store data, like training data, or maybe a trained model. Once we've done this, we click on Create Role. The role has now been created and automatically assigned to our notebook instance. To finish it up, we just scroll down to the bottom and click on Create Notebook Instance. The status of our notebook instance is now pending, which means that Amazon is working away in the background to set everything up. At this point, we just need to wait. And Amazon has finished setting up our notebook instance. If we look under the status column now, it says that our notebook instance is in service, which means that it's running. Now, it's important to note that the default behavior is for a notebook to begin running once you've created it. It's important to know that because the cost of a notebook instance is based on the length of time that it's running. So if you aren't going to be using your notebook, make sure to stop it and then start it again later. Now that our notebook instance is in service, we can click on Open to open up the Notebook Hub. I will zoom in a little bit. All right, so on the top here, you can see there's a tab that says SageMaker Examples. This gives you a bunch of notebooks that work through different examples of using SageMaker, and I would certainly recommend that you take a look at some of those if you'd like some additional resources. For now, though, we are going to use Git to download the notebooks for this module into our notebook instance. To do that, we click on New and open up a terminal. All right, so first we want to switch into the SageMaker directory, which we can do like this. And now what we want to do is clone the GitHub repository for this module into the SageMaker directory. So we do that by typing git clone and then the name of the repository, which is https github.com UDACITY SageMaker deployment. And there we go. And now that we're done, we just type exit and close the terminal tab. And you can see that a directory has been added called SageMaker deployment. And inside are all of the different notebooks that we'll be going through. As our first example of using SageMaker, we are going to take a look at the Boston housing dataset. And we're going to use that dataset to predict the median cost of a house in the Boston area. To start with, go into the tutorials folder and open up the Boston Housing XGBoost Batch Transform high-level notebook. Okay, so that's a mouthful. Each of these words will make a little more sense as we go through. To start with, Boston Housing is the dataset we're working on, and high level is the API that we are going to be using in this example. Basically, it makes using SageMaker a little easier. First things first, we need to import all of the Python modules we will need, and that includes all of the SageMaker specific modules. Each of these bits that we import here that come from SageMaker, we will talk about in a little more detail later on. All right, so next we get the data, and fortunately for us, the Boston housing dataset is provided by sklearn, so there's very little to do here. We just load the data. Now that the data has been loaded, we need to split it up into training and testing sets. Now I go one step further here and break the training set up into a validation and training set. And the reason for that is that in this example, we are going to use XGBoost as our algorithm of choice, which is a random tree model. And in my experience, I have found that random tree models are very prone to overfitting, so having a validation set can improve the results. The way that SageMaker trains and deploys models is the following. To start with, a virtual machine will be created, and it will have all of the properties that we want it to have. For example, it might come equipped with a GPU, or it might have some amount of RAM, or some specific number of processors, whatever we need for a particular task. Then the virtual machine will load an image. Typically, this image is in the form of a Docker container. And in our case, we'll be using a provided Docker container, which contains the training and inference code to use XGBoost. In order for the virtual machine to execute the training code successfully, it needs to access our training data. And SageMaker assumes that this data is available on S3, which is Amazon's data storage service. So we need to make sure that we upload our data sets there. Fortunately, this is very straightforward. In order to upload our data to S3, we first have to save that data to a file. Now here we have chosen to save all of our data inside of the Boston subdirectory of the data directory. We make sure that that directory exists. And then we use pandas to write our testing, validation, and training data sets to CSV files in the data directory. Now, the SageMaker session, which we are currently using, that is associated with this notebook instance, has associated with it a Python object. So here's this session object. And if you recall, if I scroll all the way up in our notebook, you can recall that we grabbed this session object using the SageMaker API. Going back down. So this session object contains a bunch of useful methods and information. For example, one of the methods that it includes is this upload data method, which, given a path to a file and a prefix, uploads this file to the default S3 bucket associated with this session. So our notebook instance has a default S3 bucket, which is kind of like a drive. And this upload data method uploads a file of our choosing to this drive into a folder, which is given by the prefix, which we've set here. So to go over this again, the session object contains an upload data method, which uploads a data file to S3 in a bucket, which is the default bucket for this notebook instance, inside of a folder, which is given by the prefix. Also, it's important to note that the return value of this method is a URI, which points to that data on S3. Now that we've downloaded, processed, and uploaded our data, it's time to start training the model. And now that we've downloaded, processed, and then uploaded our data, it's time to start creating a model. As I mentioned in the last video, we're going to be using the XGBoost algorithm to create a model. Understanding how the XGBoost algorithm works is a little beyond the scope of this lesson. However, it's an important algorithm to have in your toolbox, as it is very effective when looking at tabular data. In particular, it is one of the top performing algorithms used in various machine learning competitions, such as those you might find on Kaggle. In order for SageMaker to use XGBoost to fit a model, it needs to launch a virtual machine, which loads a Docker container that we specify. Amazon provides an XGBoost Docker container for us to use. However, the name of the image depends on which region we are working in. Fortunately, there is a nice utility method called getImageURI that is provided by Amazon that, given the region name and the algorithm we want to use, creates the appropriate container name. Once we have that, we can create a SageMaker estimator object, providing the name of the container we wish to use, in our case the XGBoost container, the role we are going to give this estimator. Remember that a role tells Amazon what resources a particular object is allowed to access. And since we want our estimator to access our training data, which is contained on S3, we have to make sure that our estimator has a role which allows access to S3. When we first created this notebook instance, we gave it a role that allowed it to access S3. So if we give our estimator the same role that this notebook instance has, we should be okay. We also need to tell SageMaker how many instances, that is how many virtual machines, we want to create. In our case, 1 is fine. And we need to tell SageMaker the sort of instance or the sort of virtual machine we want it to use. And the ML-M4X large instance type is perfectly fine for our uses. Lastly, we need to tell SageMaker where to store the final saved model. In this case, we're going to save it to the default bucket in the folder that we set up before, the prefix that we used previously. And lastly, we need to provide the session object just in case SageMaker needs to use some additional information. All right, now we have an estimator object that has been created. That estimator object is a wrapper for our XGBoost algorithm. Now, XGBoost itself has some hyperparameters that we can specify. For the most part, we're going to ignore what these mean, but I would certainly encourage you to play around with these values to see how it affects the model and how it fits the data. It is important to note that because the median cost of a house is a floating point number, we want to use linear regression. Early stopping rounds is used by XGBoost to determine whether or not it should complete its processing of the data early. For example, if the model starts to do worse on the validation set, then we're probably overfitting and we should stop training the model. And lastly, we tell XGBoost the maximum number of rounds that we want it to iterate. Now that we've set the hyperparameters, it's time to actually start fitting the model. In order to fit the model, the XGBoost estimator object has a handy function called fit. And all we need to do is provide it the location of the training data and the location of the validation data. Of course, that location is an object of its own, which describes not only where on S3 that data is located, but also the format of the data. In our case, they're CSV files. Now we can watch as SageMaker requisitions our virtual machine, gets everything ready for it, loads the image, and trains the model. Now that the training job is finished, we can look and scroll through and see all sorts of output, describing how XGBoost is improving at every round, and at the very end, telling us the total number of seconds that we are billed for. So now we have a fit model, and what we'd like to do is test it out on the testing dataset. To do this, we are going to use SageMaker's batch transform functionality. Now, a batch transform essentially means that we want to hand it a whole bunch of data and have SageMaker figure out how to split that data up, how to send it to our model, and how to merge all of the results. We will see a little later how we can do that ourselves and get a little more insight into what SageMaker is doing in the background, but for now, we can just view this as another convenient black box. So to do that, we can start by using our estimator object that we created and then fit, and calling the transformer method, which creates for us a new transformer object. The only thing that we have to provide is how many virtual machines we want that transformer to use in the background and what sort of virtual machine we want the transformer to use. Again, we only need one for our purposes, and ML M4 X large is wonderful for our use. Now that the transformer has been created, it's time to actually start the transform job. Now what we do is we give it a location. This is the data that we saved, the test data that we saved on S3. We tell it what kind of data it is. In our case, it is CSV data. And further, we tell it how, if it needs to, it can split the data up. Our data is tabular, which means that each line is its own sample. So if it needed to break the data up into chunks, it could do so by splitting it up by line. Interesting to note is that this cell has now completely executed. And what is happening is that SageMaker in the background is creating a transform job, which it will then run for us. But inside of the notebook, we don't really have any indication as to what's going on. However, if we call the wait method, this provides us with some output to give us an indication as to how the transformation job is progressing, and in addition, it will let us know when it has finished. So for now, we'll just wait for this to finish. So now the batch transform has completed. So what happened? Well, SageMaker took our testing data, sent it to the model. The model then performed inference for each sample. SageMaker collected all of these predictions up and created a new file and saved that file on S3. The location of that file is stored in the XGB transformer output path variable. And we can use a little bit of notebook magic to use AWS's S3 functionality and copy the output file to our notebook instance so we can more easily play around with it. Now the output file has been saved inside of the Boston subdirectory of the data directory, and we can use pandas to read that CSV file in, and then we can create a nice little graphic to show how well our model is doing. We would expect in a perfect world where we had a model that worked 100% of the time that this would be a line y equals x. The data here kind of doesn't exactly lie along that line, but it does mostly, and so we can maybe view this as being a success, but that there's some room for improvement. As a last optional step, we created a bunch of data and saved it inside of the data directory. And if we were to just leave that data there and continue working through the various notebooks, eventually the disk space that we have available on our notebook instance would be used up. And when that happens, you can get some errors that are a little hard to diagnose. So as a last step here, we're going to clean up that data directory and then remove the directory. And that's it. That's our first example. So in the next video, we are going to take a look at a mini project for you to do. Now you're going to get a chance to use SageMaker to build a model. To start with, open up the SageMaker deployment directory, and then inside of that, the mini projects directory. The notebook we're going to be working in is IMDb Sentiment Analysis, XGBoost, Batch Transform. In this notebook, you're going to use SageMaker to create an XGBoost model that will try and determine whether a review posted on the Internet Movie Database is positive or negative. To begin with, step through the various cells that download the data, prepare the data, and process the data. There isn't really anything for you to do here except execute the cells, and you should be warned that the data processing can take some time. For me, it took almost a full hour. So I would recommend running all of the cells first and then reading through to see what they're doing after the fact. Step 4 is where your work is going to begin. To start, you will break the training data set up into a validation and training set, then save the test, train, and validation sets to a file, and then upload those files to S3, just like we did in the Boston Housing notebook. Then you will create an XGBoost model and fit it. Lastly, you will create a batch transform job to test the model and take a look at how accurate your predictions are. Optionally, you can make sure to remove any files that were created in the data directory and the cache directory. This just makes sure that the disk drive on your notebook instance doesn't get filled up too quickly. I would recommend taking a look at the Boston Housing notebook, as a lot of the things that we did there are going to translate into the tasks that you want to do in this notebook. If you do get stuck, however, don't worry, because in the next video, I'm going to go through in detail my solution. All right, now that you've had a chance to fill this notebook out yourself, let's go through and take a look at my solutions. To start with, I have already run all of the data downloading and processing steps, so we can start right away here at step 4, where we start adding our own code. First things first, let's split our training data set into a training and validation set. Here we have 25,000 reviews, and we've already randomized the order of the reviews. So to split into a training and validation set, we can just take the first 10,000 as the validation set and then leave the remaining as the training set. Once we've done that, we just, as we did in the Boston Housing notebook, save the testing, validation, and training datasets to CSV files in an appropriately chosen data directory. Also, like in the Boston Housing dataset, we make sure that when we save the CSV files, we do not include a header or an index, as that is the format that SageMaker requires the data files to be in. Now that the test, validation, and training sets have been saved, we can first do a little bit of memory management. So you will see this sort of a code cell appear in a number of the notebooks. And the reason for this is that the default virtual machine that our notebook instance is running inside of doesn't have a lot of RAM available to it. So if we let unused data just sort of linger, we can accidentally run out of memory inside of the notebook. So we have two options. We could increase the capabilities of the virtual machine that our notebook is running inside of, but that may be costly. Or we could do something like this, where we make sure to keep track of memory that is no longer being used and free it. Next step is to upload the data files to S3. And this is essentially done in the same way as we did in the Boston Housing notebook. The difference really is that we are changing the prefix. Remember, the prefix is basically like the folder name on some drive, and the drive is the default drive or bucket that corresponds to this notebook. Aside from that, we just use the upload data method for each of our data files and upload them to S3. Now the data files have been uploaded and we can move on. To begin with, we make sure to get a hold of the execution role. Remember that the role describes what other resources our notebook has access to, and we need to make sure to give the estimator we're about to create a role. We may as well give it the same role that we're using for this notebook. And we also need to make sure to create the image URI for the XGBoost algorithm, and that depends on the region that we're currently using. So we use the getImageURI method. And then we create the SageMaker estimator object in the exact same way as we did in the Boston Housing notebook. The difference here is in one of the XGB hyperparameters. Since we are trying to determine sentiment, that is a binary outcome, positive or negative, we want to make sure that we're using a binary or a two-outcome regression. And in particular, logistic regression is typically what we want to be using. So the only real difference between the Boston Housing notebook and this one is that we have changed the objective to being a binary logistic regression. Okay, so now we have defined the XGBoost model and we need to actually fit it. So again, just like in the Boston Housing notebook, we just provide the training and validation datasets and away it goes. Once the model has been fit, we can go on to testing to see how well our model behaves. First thing we need to do is create a new transformer object. And once that's been done, we set up a transform job, making sure to specify both where the test data is, the type of data it is, and the way in which SageMaker could, if necessary, split the data up. Now remember, the transform job is happening in the background, it's being set up and run in the background. So if we use the wait method, we can get some visual output to let us know how that transform job is progressing and when it's finished. Once the transform job has finished up, we can copy the output from that transform job to the notebook instance, then read in that data and check to see how well our model performed. Oh, not so bad, almost 87%. Again, we can then do the optional cleanup step to get rid of any of the files that we created throughout the notebook. So that's it. You have created your first ever model in SageMaker. Of course, we have used a lot of the high-level functionality of SageMaker, and as a result, most of the magic has happened in the background. In the next few videos, we're going to go into much more detail as to how SageMaker works. Our goal in the remaining videos is to start looking into some of the details of what SageMaker is doing. To do this, we will start by looking at the Boston Housing example that we started with, except instead of using the high-level API, we're going to use the low-level one. This way, we can see all of the steps that need to be taken and all of the objects that are created along the way. If you'd like to follow along, navigate into the Tutorials folder and open up the Boston Housing XGBoost Batch Transform low-level notebook. I've already opened up the notebook here, and I've run the first few cells. The beginning of this notebook is the same as the high-level version that you did earlier. A quick word of explanation before we get started. The reason for looking closely at the details is so that when errors inevitably show up, they're easier to diagnose. SageMaker's high-level API makes some choices on your behalf, which can be great when you want to get something done, but can be a little more problematic when things go wrong. So now that we've downloaded the data and done some initial processing, it's time to upload the data files to S3. As before, the way that we do that is to first save the files locally inside of the notebook instance. To do that, we start by making sure that a directory exists inside of the data subfolder, and then we use pandas to save those files to the directory we've chosen. To see where those files have been saved, if we select the tab that shows the notebook hub, and we navigate up one directory, we can see that there's a folder called Data. Inside of the Data folder is another folder called Boston. Now, if you remember from the notebook, we are saving the data to the Boston subdirectory of the data directory. Heading back to the Notebook Hub page, inside of the Boston subdirectory, we can see the test, train, and validation CSV files that we created using pandas. Now that the files have been saved on the notebook instance, we can upload them to S3. Remember, to do that, we use the upload data method of the session object. Before we do this, let's talk a little bit about what S3 is. In essence, S3 is Amazon's data storage facility. It provides a place for you to store data that you might want to read many times. For example, training data or a saved model. If we open up the AWS console page, which we can do by clicking on the AWS icon in the top left corner, and scroll down and look under storage for S3, we can open up the S3 console. This will show you any buckets, remember a bucket works kind of like a drive, that you have created inside of S3. Currently, I don't have any buckets. If I go back to the notebook and I execute this cell, SageMaker tells me that the default bucket associated with this notebook instance has been created. Now, if I navigate back to the S3 console and refresh the page, I can see the S3 bucket that has been created. Further, if I select this and open it up, we can see that there's a single directory, again, with the same name that we specified in our notebook. And inside of that directory are the test, train, and validation files. Now that we've uploaded our training and validation data to S3, it's time to construct our model. When we use the word model, we should be very careful about what we mean. For now, we mean model as understood by SageMaker, which is a collection of information including any model artifacts created during training and additional information describing how the model artifacts should be used. This will make a little more sense as we go through creating our model. To remind ourselves how this works in the high-level case, let's take a look at the high-level notebook. This is the high-level notebook, and if we scroll down to training and creating the XGBoost model, what we did was first get the URI to the XGBoost Docker container. We then created an estimator object, which included which algorithm to use by means of a link to a container, some information about the type of virtual machine that should be used to run the algorithm, where to store the output, and then some other information like what role the virtual machine should have, and some additional session information. Next, we set algorithm-specific hyperparameters, and lastly, we called the fit method, providing a link to the training and validation datasets. The ultimate goal of these 3 steps was to create a training job. A training job essentially does what it sounds like it does. It runs an algorithm on some provided data to fit a model and then saves the resulting fit model to a file somewhere. We will be setting up the training job ourselves in the low-level notebook. Switching back to the low-level notebook, in order to create the training job, we need to specify all of the bits of information in a single large dictionary object. We're going to call our dictionary object training params. Of course, we're going to need the URI to the Docker container containing the XGBoost algorithm. Next, we make sure to specify what role the virtual machine that we will eventually create should have. Next, we need to specify the algorithm we wish to run. We do that by specifying a link to the container. Next, we need to specify where the resulting model should be saved. This output of our algorithm is what is called the model artifacts. Next, we need to describe what properties the virtual machine we are going to run our algorithm on should have. In our case, we're going to use a single virtual machine which is relatively medium powered and does not require too much in the way of storage. This parameter sets a timeout condition. Essentially, if the training algorithm gets stuck in some sort of infinite or very long loop, this makes sure that our virtual machine doesn't run forever. Those are the parameters that make up the algorithm specification. Now we need to set the parameters that are specific to the algorithm we've chosen, in our case, XGBoost. We can do that here. As you may notice, the hyperparameters that we've chosen here are the same as the ones that appear in the high-level notebook. Next, we need to tell SageMaker where to pull the data from. In particular, we need to tell it where the training data is. In this case, it is in S3, and it is CSV data, and the validation data, which is also on S3 and is also CSV data. So now we have specified which algorithm to use, parameters specific to that algorithm, and the data that is sent to the algorithm. All that is left is to ask SageMaker to construct the training job with the parameters that we have chosen. One additional parameter that must be included is a name. Every training job must have a name, and that name must be unique. The way that we make sure that our training job has a unique name is by including a timestamp at the end of the name. Once we've done that, we ask SageMaker to create the training job, and away it goes. Just like when doing the batch transform, the training job is being created in the background, and once it has been created, it will be executed. If we want to have some sort of visual representation of what is going on, and to alert us when that training job has completed, we need to use this logs for job method and include the wait equals true parameter. Now we just need to wait for our training job to complete. Now that the training job has completed, we can build the SageMaker model. Remember, the SageMaker model is really a collection of information that includes both a link to the model artifacts, that is the saved files that were created by our training job, and some information that describes how those model artifacts should be used. Before we do that, however, let's actually take a look at the training job inside of the SageMaker console. To do that, let's open up the tab that currently is on the S3 console. If I click on the icon in the top left corner, it brings me to the main AWS console. And from here, we can choose whichever service we want to look at. In our case, we want to scroll down to machine learning and select Amazon SageMaker to open up the SageMaker console. Now, the last time we were here, we clicked on Notebook Instances, which shows each of the notebook instances that we have created. This time, we want to take a look at training jobs. As you can see, I have quite a lot of training jobs that I have built up over my time playing with SageMaker. However, this one right here at the top corresponds to the training job that we just completed in the low-level notebook. How do I know this? Well, for two reasons. First, the creation time is today. And secondly, when we named this training job, remember we included a timestamp at the end of it, which again includes today's date and the time that I created this training job. If I select this and click on it, it shows me some information about the training job. One piece of information that may be of use to you in the future is down at the bottom where it says View Logs. If you click on this, it will open up a CloudWatch dashboard from which you can take a look at the output that was created by that training job. So if you have any errors that show up while training, they will appear here. This can be a very useful tool when you are working on training jobs that are a little more complicated than this one. Going back to the low-level notebook, again, our training job has completed, so now it's time to build the model inside of SageMaker. So, how do we do that? Well, as I said before, a model in SageMaker is really a collection of data. In particular, it includes a link to the model artifacts, which we can extract from the training job information, and some additional information about how those model artifacts can be used. Now, just like when we created a training job, a model must have a name that is unique. So the way we are going to create the model name here is to take the training job name, which was already unique because it had a timestamp, and append model to it. Once we have the model name, we package up information including a link to the model artifacts and a link to the Docker container, which contains the algorithm necessary to perform inference using our created model artifacts. Lastly, we use the SageMaker object to create a model, which includes the name that we specified, a role, and the data structure, which includes a link to the container and a link to the model artifacts. So now that we've run this cell, what actually happened? Well, if we go back to the SageMaker dashboard, on the left-hand side, if we click on Models, again, I have a whole bunch here built up from previous experiments with SageMaker. If we look at this top one here, it looks like the name of the training job that we created, including the correct timestamp, with the word model appended. So this is the model that we just created in the notebook. If I click on here, notice that all of the information we provided is now included. Looking through, we can see a link to the model artifacts and a location of the inference code. Now that the model has been created, we'd like to test it to see how well it's doing. If we click on the high-level notebook, we can remind ourselves how we went about it there. First, we created a transformer object in which we described the number of virtual machines and the type of virtual machine we wanted to use. And then we called the transform method, which created a batch transform job, which was then executed by SageMaker. Just like when we train the model, we will construct our own batch transform job in the low-level notebook. Going back to the low-level notebook and scrolling down, the first thing to notice is that just like in the training and in the model creation steps, we have to name our transform job. Also, like the model and training job cases, we have to make sure that the name is unique. So again, we make sure to append a timestamp on the end of the transform job's name. Next, we need to describe the transformation job in detail. We begin by setting a name, choosing the model which we wish to use for the transformation job. We describe how many simultaneous transformations will occur at any given time. For now, we'll just use one, but if we had a very large data set, maybe we'd like more than one to run at the same time. Next, we describe the maximum amount of data that is sent to our model at any given time. If you need to, you can increase this, but for now, we will just leave it at 6. In this case, we're choosing multi-record, which means we want to send multiple records in each chunk of data. Then we describe where we would like SageMaker to save the results of our batch transform job. Once we've described the output, we should also make sure to describe the input. Here, we are telling SageMaker that we are sending it CSV data, that we can break the data up line by line in case the data is too large to send in a single chunk, and where the data is located, in particular on S3 in this location. Lastly, we tell SageMaker what sort of machine to use when running the transform job. Now that we have specified all of the parameters of our transformation job, it's time to ask SageMaker to create the job. Just like in the training case, SageMaker is now working on creating and executing that transform job in the background. So in order to get some visual representation of what's going on, we need to call the waitForTransformJob method. Now we just need to wait for the transform job to complete. Now that the transform job is completed, we can take a look at the results. First, we make sure to copy the output from our transform job to the local notebook instance, and then we create a nice graph to take a look to see how it's doing. It turns out not too bad.
Now you've had a chance to see some of the basics of what SageMaker can do for you. For the most part, we've looked at how SageMaker can be used in a lab-like setting, where we're interested in exploring and processing data, creating models, and then testing those models. Next, we're going to look at how SageMaker can help us deploy the models that we've created so they can be used outside of the notebook. In addition, we're going to look at building a simple web app that will interact with a deployed model.
We've looked at how SageMaker can be used to create and train models, and we've looked at how the batch transform functionality can be used to test a trained model. Now we'll look at how you can deploy a trained model. In our case, we'll be deploying it by making it available at an endpoint, which is a supported way of deploying a model using SageMaker. We'll use the deployed model from the notebook itself, but later on in this lesson, we'll create a web app that can access a deployed model. To follow along, navigate into the SageMaker folder, and then inside of the tutorials folder, and open up the Boston Housing XGBoost high-level deploy notebook. To start with, we'll be using the same dataset and creating the same sort of model as in the other Boston Housing notebooks. In particular, we'll be predicting the median cost of a house in the Boston area using XGBoost. Since we've done this before, I will go ahead and train the model now. Now we've obtained the data, done any processing that was required, built the model, and trained it. Instead of creating a batch transform job to test our model, we're going to test it by first deploying it and then sending the test data to the deployed endpoint. Using the high-level approach makes actually deploying the model very easy. We simply call the deploy method of the trained model object, making sure to specify the number of virtual machines we want to use and the type of virtual machine. Currently, SageMaker is preparing, and then we'll run our deployed model. We'll come back once this is done. As you can see, the model has now been deployed. So what does this mean exactly? What this means is that SageMaker has created a virtual machine that contains our trained model that can be accessed at an endpoint. In other words, at a specific URL. In the next video, when we go into more detail, I'll show you how you can find this URL. But for now, the predictor object, which was returned by the deploy method, takes care of all of that for you. In order to send data to our model's endpoint, we can use the predict method of the predictor object that was returned. However, the data that we provide to the predictor object needs to be serialized first. Fortunately, SageMaker provides this functionality for us so long as we specify the type of data that our model expects. In this case, we are going to be using CSV data, and so we can use the provided CSV serializer. Once our model has performed inference on each of the records that we sent it, a result will be returned, which will be the serialized predictions. This means that the result is a comma-delimited string of results for each record, and so we need to convert it back to a NumPy array, which is what we do right here. Once we have the resulting data in a format that we can use, we can make a nice little graph to see how our model is doing. Of course, we should expect this model to perform similarly to the other XGBoost models that we've made using the same dataset. The last step that must be completed is to shut down the deployed model. Remember that SageMaker has created a virtual machine for you that is hosting your trained model. This virtual machine will continue to run, waiting for data to be sent to it until you shut it down. Since the cost of running a deployed model is based on how long it is running for, when you no longer need an endpoint, you need to shut it down. In this video, we're going to look at deploying a model in SageMaker with a lot more detail. To follow along, open up the Boston Housing XGBoost Deploy Low-Level Notebook. Again, the majority of this notebook is the same as the low-level notebook that we went through that used the batch transform method for testing the resulting model. To remind ourselves of how this works, first we load up any of the necessary modules. Then we download and prepare the data, but in this case, since we're using data provided by sklearn, it's very simple. We split the data up into a training, validation, and testing set. Then we save the data locally and upload it to S3. Once our training data is available on S3, we can set up the training job, where we describe all of the important bits, like, for example, what algorithm we want to use, the hyperparameters specific to that algorithm, and where our data is stored. Once we have described the training job, we then ask SageMaker to create and run that training job, and we can wait for that job to complete. Once the training job terminates, the output of the machine learning algorithm, in this case XGBoost, is saved to S3, and those resulting files are called the model artifacts. We can then create a model inside of SageMaker by specifying which model artifacts should be used, along with which Docker container contains the appropriate inference code. Just like in the previous video, instead of testing the model using the batch transform functionality, we're going to deploy the model and then send the test data to the deployed endpoint. Remember, in SageMaker, deploying a model means creating an endpoint. And that endpoint, from the user's perspective, is just a URL that we can send data to. Behind the scenes, things are a little more complicated, but fortunately, SageMaker takes care of most of the heavy lifting. What this means for us is that to deploy a model means to create an endpoint, and to create an endpoint, we need to tell SageMaker some details about how that endpoint should operate. In other words, we need to create an endpoint configuration. Just like most of the objects that we deal with inside of SageMaker, an endpoint must have a name, and that name must be unique. So we're going to use the same trick that we've used before by appending a timestamp to the end of our chosen name. Once we have a name, we need to specify a list of what are called production variants. In effect, these are different versions of the same model or different models. An endpoint sort of acts like a uniform resource that we can send data to. SageMaker can then take the data that is sent to an endpoint and, if we want it to, split it up among different models. For now, we only want to deploy a single model at our endpoint, and so our production variants consist of a single item, and that single item is the model that we specified that we created earlier. Once we ask SageMaker to create the endpoint configuration, a new object has been created. Now, this endpoint configuration can be thought of as a blueprint that we can use as many times as we need to in the future, and it tells SageMaker how to create a specific endpoint. So for example, if I go back to the SageMaker console, and on the left-hand side here, I look at endpoint configurations, you can see this first one here is the endpoint configuration that we just created. So this will stay here in perpetuity, and we can create an endpoint using this blueprint, this configuration, whenever we'd like to. Heading back to the notebook, we can now ask SageMaker to create an endpoint based on the configuration we just made. Again, just like always, we have to make sure to specify a name, and that name must be unique. So now SageMaker is setting up our endpoint in the background, and as before, we can use this method here to see a visual output as to how our endpoint construction is progressing. While SageMaker works on setting up our endpoint, let's take a look and see what was created. If we head back to the SageMaker console, remember that this object here is the endpoint configuration that we made. And if we further click on the endpoints listing here on the left, we can see the endpoint that we just asked SageMaker to create. And currently, it is in the process of being created. So we'll wait for SageMaker to finish making this endpoint for us. Now we can see that our endpoint is in service. If we head back to the notebook, we can see that the process of creating our endpoint has been completed as well. So now we can test the model, which, as we said before, means we can serialize our data and then send it to an endpoint. Now, in this case, because we don't have a predictor object, we need to serialize the data ourselves, which is pretty straightforward. We basically just turn our matrix, which is a listing of records, into a comma delimited file. So we do that. Then we use the SageMaker runtime client to call our endpoint with the specified name, with content which is a CSV file, and then we include the data we wish to have our model process. The resulting object is then a serialized output, which we need to convert to a string and then turn back into a NumPy array. Once we have our resulting output, we can then plot a nice little graph. As before, once we're done using our endpoint, we need to shut it down. But I'm going to show you a slightly different way to shut down the endpoint from just using the notebook methods. So if we go back to the SageMaker console and look at our endpoint, clicking on this endpoint here gives us some more information about it. In particular, right here is the actual URL that can be used to send data to our endpoint. Now, it turns out not just anyone can send data here, and we'll talk about that more in detail later on. Another useful feature of this page is this delete button. If I click on the delete button, it will shut down the endpoint for us. So we don't have to use the notebook to shut down the endpoints. We can use the SageMaker console as well. And yes, we'd like to delete it. Our goal over the next few videos is to take the sentiment analysis mini project that you worked on in the last lesson and create a simple web app that uses it. The web app that we're going to create will look like this. And what you can do is take a review. For example, here is a rather negative review, and then you click on submit, and the model lets us know that this review was negative. As another example, we could take this very positive review, click submit, and our web app tells us that our model believes that this review was positive. In order to do this, we will deploy the sentiment analysis model in the same way that we deployed the Boston housing model earlier. However, there are a couple problems that we'll have to solve. The first is that the sentiment analysis model expects to be sent a bag of words encoding of a movie review. But as you can see here, we allow the user to enter a block of text. So how do we encode the user's input in a way that the model can understand? The other problem we'll need to solve is one of security. Endpoints created by SageMaker can only be accessed by a web app if that web app is properly authenticated and has permission to use SageMaker endpoints. Since that seems like a lot of work for a relatively simple web app, we will instead create our own endpoint that can be accessed by anyone with no restrictions. This will require using some additional Amazon services. In particular, we're going to need Lambda and API Gateway.
The first feature representation we'll look at is called Bag of Words. The Bag of Words model treats each document as an unordered collection or bag of words. Here, a document is the unit of text that you want to analyze. For instance, if you want to compare essays submitted by students to check for plagiarism, each essay would be a document. If you want to analyze the sentiment conveyed by tweets, then each tweet would be a document. To obtain a bag of words from a piece of raw text, you need to simply apply appropriate text processing steps: cleaning, normalizing, splitting into words, stemming, lemmatization, etc., and then treat the resulting tokens as an unordered collection or set. So, each document in your dataset will produce a set of words. But keeping these as separate sets is very inefficient. They're of different sizes, may contain different words, and are hard to compare. Also, what if a word occurs multiple times in a document? Is there a better representation you can think of? A more useful approach is to turn each document into a vector of numbers, representing how many times each word occurs in a document. A set of documents is known as a corpus, and this gives the context for the vectors to be calculated. First, collect all the unique words present in your corpus to form your vocabulary. Arrange these words in some order and let them form the vector element positions or columns of a table, and assume each document is a row. Then count the number of occurrences of each word in each document and enter the value in the respective column. At this stage, it is easier to think of this as a document term matrix, illustrating the relationship between documents in rows and words or terms in columns. Each element can be interpreted as a term frequency. How frequently does that term occur in this document? Now consider what you can do with this representation. One possibility is to compare two documents based on how many words they have in common or how similar their term frequencies are. A more mathematical way of expressing that is to compute the dot product between the two row vectors, which is the sum of the products of corresponding elements. Greater the dot product, more similar the two vectors are. The dot product has one flaw. It only captures the portions of overlap. It is not affected by other values that are not in common. So, pairs that are very different can end up with the same product as ones that are identical. A better measure is cosine similarity, where we divide the dot product of two vectors by the product of their magnitudes or Euclidean norms. If you think of these vectors as arrows in some n-dimensional space, then this is equal to the cosine of the angle, theta, between them. Identical vectors have cosine equals 1, orthogonal vectors have cosine equals 0, and for vectors that are exactly opposite, it is minus 1. So the values always range nicely between 1 for most similar to minus 1 most dissimilar.
Our first task, starting with the mini project that you worked on last lesson, is extended by way of deploying it. To follow along, navigate to the SageMaker deployment folder and then into the tutorials folder and open up the IMDb Sentiment Analysis XGBoost web app notebook. As in the mini project, we will start by downloading the data and then doing a little bit of processing. So we start by reading it in. If you remember from the mini project, one of the ways that we converted our reviews to a list of words was to use Beautiful Soup and NLTK. We used Beautiful Soup in order to remove any HTML formatting that may have appeared, and we use NLTK to stem the words. Here we're going to take a bit of a more simplistic approach, and we are just going to remove any punctuation and any HTML formatting that will appear in our reviews. And we're just going to do that by using the Python 3 regular expression module. There's a reason that we've chosen to simplify this method quite a bit, and it has to do with some of the technology that we'll use later. In particular, this makes using Lambda much easier. So how does this method work? Well, suppose we start with this review right here. As you can see, there is some HTML formatting, and we have some punctuation here and here. So review to words will then clean that up, and what we're left with is a cleaned version of the review. So now what we'd like to do is do that to each of the reviews in our data set. Now that that's done, we need to take our cleaned reviews and we're going to encode them using bag of words. What that means is that we are going to look at all of the reviews in our training set, and then we will collect the most frequently appearing words, and then we will encode each review as a vector, where each entry in the vector tells us the number of times that particular word appears in our review. Notice that the vocabulary size that we use here is 5,000, which means that we are only going to track the top 5,000 most occurring words in our training set. What that means is, once we have encoded a review using the bag of words approach, we should end up with a vector which has length 5,000, which we do. Next, we need to move on to uploading our datasets to S3, and we do that in the standard way. First, we will split our training set up into a validation and training set. Next, we will save the test, train, and validation sets to disk using pandas. And to save a little bit of memory, we will set the variables that held onto our pandas data frames to none. Keep in mind that the notebook instance that you are likely to be using does not have a lot of RAM available, so if we just sort of let these data frames hang around even though we don't need them anymore, we could end up running out of memory, which can lead to some sometimes difficult to diagnose issues. Once that's done, we are going to use the SageMaker upload data method to upload our test, validation, and training sets to S3. Next up, we create an XGBoost model in the same way that you did in the mini project, and then we fit the model. Now that the model's fit, we can go ahead and test it by creating a transformer object and then creating a transform job on our test data to make sure that our model is working as we expect it to. And once the batch transform job is done, we can copy the resulting output from S3 to our local notebook instance and then check to see how well the predictions did. Turns out not so bad. All right, so now we are going to extend the mini project in order to deploy it for the first time, much in the same way as we did with the Boston Housing Notebook. Of course, deploying is relatively straightforward using the high-level approach. We just call the deploy method and wait for SageMaker to set up our virtual machine and get it running. Now that SageMaker has finished setting up the virtual machine, which we are using to deploy our model, we can test the model again. We should get the same results that we got when we created a batch transform job. However, we're going to test it again to make sure that everything is working as we expect it to. So first, in this case, because we're using the high-level approach, we can use SageMaker's built-in serialization methods. We just need to make sure that we tell SageMaker what format our model expects to receive data in. In this case, for an XGBoost model, it expects CSV data. Now, since our testing data is too large to send in a single invocation of our endpoint, we need to split it up. So we split it up into chunks, and then we collect all of the output. Then we send our test data off to our endpoint to see what our model thinks. Now that our model has finished performing any predictions it needs to on the test set, we can take a look and see how well we did. Good. We got the same result as when we created a batch transform job. Now we deployed our model in this section so that we could test it to make sure that everything was working. We're going to have to do a little more work before we can actually use our endpoint in our simple web app. So for now, we're going to shut down the endpoint that we've deployed. It's a good idea to do this if we're not going to use it in the near future, because remember that the cost of deploying an endpoint is based on the length of time that it's running for. So if you don't need it, shut it down. In the last video, we took a look at the mini project that you worked on last lesson and extended it by deploying it. Of course, we didn't do much with the deployed endpoint. We just used it as another opportunity to test our model. Now we're going to start putting together all of the pieces in order to make our endpoint work with the web app. Remember that in the introduction we talked about how we have two problems we need to overcome. The first is that our model's endpoint expects to receive a bag of words encoded version of the review. However, our web app allows our user to type any review in as a string. So how do we do that? The second problem we have to overcome is one of security. A deployed SageMaker endpoint will only allow access to another object which is authenticated with AWS and has permission to use a SageMaker endpoint. That seems like overkill for a simple web app, so what we'd like to do is create a new endpoint which is open to anyone that can receive a string as input, perform some data processing, and then send the processed review off to our model, get the result back, and return it to the original caller. A nice picture to summarize this is right here. So we have our web app, and our web app takes a string from the user, sends it off to the new endpoint that we're going to create. the new endpoint does some additional processing to the review and then sends that processed review over to the model. The model then creates a prediction, sends the prediction back to our newly created endpoint, and our endpoint returns the result back to our app, which it can then display to the user. The technology we're going to use in order to implement this new endpoint is, first of all, Lambda, and then we're going to create an interface to our Lambda function using API Gateway. For now, let's just talk about Lambda. Lambda is an example of something called a function as a service. That is, instead of having to create a server and have it running the whole time before you even need it, you can instead tell Amazon that you want a specific function to be run whenever a specific event occurs. That way, you don't have to pay for a server running the whole time. You only have to pay each time your function is run. Before setting up a Lambda function, though, let's take a look at what kind of processing we need to do. To start with, our Lambda function is going to receive a string, which contains a movie review. In our case, let's think of test review as being the string that will be sent to our Lambda function. This is a rather negative review. The first thing we need to do is to get rid of any HTML formatting that may appear inside of the string, and we need to remove any punctuation that appears. If you recall from earlier, we wrote a function called review2words that did just that, using only Python's built-in regular expression module. So if we call this method on our sample review and we print the result, we will see that we get a cleaned up version of the review. Next, we needed to create a bag of words encoding of the review. To do that, we need a vocabulary, which remember we constructed by looking at the most frequently occurring words in the training set. Based on this vocabulary, we count the number of times each word in the vocabulary occurs in our review, and then we create a sequence that encodes all that information. Doing that is pretty straightforward, and in fact has been implemented in this method right here. So given our input, which is the cleaned review, and the vocabulary dictionary, the result is a bag of words encoded version of the review. Of course, if we were to just print this bag of words encoding out, it wouldn't make much sense, since it's just a vector of length equal to the size of the vocabulary. As a sanity check, though, we can make sure that the bag of words encoded version of the review has the correct length, and that agrees with the size of the vocabulary that we created earlier. Alright, so what we'd like to do now is take our bag of words encoded review and send it off to our model to see what happens. Of course, we shut down the endpoint of our model in the last video, so we need to start it back up again. Now that our endpoint is up and running, we can send our bag of words encoded review off to it to see what happens. Now, in the past, we have used the XGB predictor object in order to call our endpoint. Of course, on the Lambda function we're going to create, we do not have access to this XGB predictor object. So, we need to use the SageMaker interface itself. To do that, we can get an object which points to the SageMaker runtime. Once we have that, using the name of the endpoint we have created, which we can remind ourselves here, we can use the invoke endpoint method, making sure to include the name of the endpoint, the format of the data that we are sending it, and the data itself. So let's see what happens. It seems we got an error. So why did we get an error? Well, if we scroll down to the bottom, we can see that parameter validation failed, which means that some of the parameters that we used to invoke our endpoint were not correct. In particular, look at the value of the body. This doesn't look like a CSV file, and we told SageMaker we were going to send a CSV file. Instead, we sent a list of integers. So we need to make sure to serialize this object before we can properly call the invoke endpoint method. So let's do that now. Here, again, we include the name of the endpoint, we tell SageMaker the type of data that we will be including, and then we serialize that data. We do that by joining together each of the entries in the bag of words vector, separating each of them by a comma. Once we do this, we get a response, and what does that response look like? A whole bunch of data. Of course, a lot of this data has to do with the fact that we communicate with our model using an HTTP endpoint. That is, an endpoint that is just a URL. Looking right here, though, we can see that there's a body object, and that body object contains the real information we're looking for. So what we can do is read in that body object, making sure to convert the result to a string. And what do we get? 0.378. It seems like Our model did not think that review was particularly positive. In fact, our model thought it was negative. So this gives an example of the sort of processing we're going to need to do inside of the Lambda function. Next, we will actually set up the Lambda function. In the last video, we talked about why we need a Lambda function, and we talked about what that Lambda function needs to do. In this video, we're going to actually implement that Lambda function. To start with, let's jump ahead and take a look at what the contents of the Lambda function will be. They're included right here. Of course, we need to import any of the modules we're going to use inside of it. Here, you will see the same review to words method that we used at the very top of this notebook. And here, you will see the same bag of words encoding method that we also used earlier on in this notebook. One thing to note is that the bag of words encoding method requires a vocabulary. So we're going to have to make sure to include that in our Lambda function. Now we can look at the Lambda function itself. It's pretty straightforward, but I included lots of comments in case you want to take a look at it yourself. At the top here, we have to make sure to include the vocabulary that we created earlier on using the training set. Then we need to extract the review that is submitted by the user from the body of the event that was passed to the Lambda handler. Once we do that, we need to clean up the review by removing any HTML tags and any punctuation. Next, we construct a bag of words encoding of our review. Once we have the bag of words encoded review, we can invoke the endpoint that we've created, making sure to include the endpoint name, and making sure to serialize the bag of words encoding of our review. Once we get the response, we read it back, convert it to a string, and then, for convenience, we round it either to 1, meaning that the review is positive, or 0, meaning the review is negative. Lastly, we return the result to whoever called us. So how do we actually go and set this up? Well, there are two things we need to do. In addition to creating the Lambda function itself, we need to give that Lambda function permission to use a SageMaker endpoint. So let's set up a new role that our Lambda function will have. To do that, we go back to the Amazon console and we scroll all the way down to Security, Identity, and Compliance and click on I am. Our goal is to create a new role for our Lambda function. So on the left-hand side, we click on Roles. And then we click on the Create Role button because we'd like to create a new role. Now, our new role is going to be for a Lambda function. So we select Lambda function under the service that will use this role. Then we click on Next. Now, what permissions do we want to give our Lambda function? Well, we want to give it access to SageMaker. So if we type SageMaker into the search bar and then scroll down, you will see SageMaker Full Access. Make sure to click on the checkbox to the left to include the SageMaker Full Access permissions to this role. Click on Next, and now we need to give this role a name. I'm going to call mine Lambda SageMaker Role to remind me that this is a role for Lambda that provides access to SageMaker. And if we click on Create Role, the role will be created for us. Great. So that's the first step. We've now set up a role for our Lambda function to have. Now we need to set the Lambda function up itself. If we again go back to the main Amazon console, and this time under Compute, we click on Lambda, we can create a new Lambda function. We would like to start from scratch, and we need to name our function. I'm going to call mine Sentiment Lambda Function. Since we're using Python in this course, we need to make sure to set the runtime to Python 3.6. Lastly, we need to give this Lambda function a role. Of course, we want to use the role that we just created. So we leave this at choose an existing role, and then we choose the role that we created from this drop-down menu here. Now clicking on Create, our Lambda function has been created. If you scroll down, we can see the code for our Lambda function. Currently, it doesn't do much at all. However, if we go back to the notebook, scrolling down, we can copy and paste the function that I've provided here. So we select it, copy, and paste. Remember, there are two things that we need to add to this Lambda function. The first is the name of the endpoint that we've deployed. Heading back to the notebook, remember that we can get the name of the endpoint by typing xgbpredictor.endpoint. So if we copy this and paste it over here, now our Lambda function knows which endpoint to use. The second thing we need to add here is the vocabulary object. Going back to our notebook, we can print the vocabulary so that we can copy it and paste it into the Lambda function. Once we've done that, click on Save. So currently our Lambda function has been set up. Let's create a test event to test it. In the drop-down menu right here where it says Select Test Event, click on Configure Test Events. This is how you can add a new one. We want to create a new test event, and our event template, scrolling all the way up to the top, is going to be API Gateway AWS Proxy. Our event name is just going to be Test Event. As you can see, our test event is going to send a whole bunch of data to our Lambda function. But the only bit of data that our Lambda function cares about is the body entry, which we are going to replace with a review we wish to send our Lambda function. So let's plug in a very simple example review. Let's just say the movie was horrible. I do not recommend this at all. Clicking on Create will then create this test event. Now that this test event has been selected, I can click on Test, and the result is 0, meaning that my model thinks that the review I entered was negative. So far so good. Our Lambda function is working. However, how do we get our website to use it? Well, we're going to have to create our own endpoint using API Gateway, and that's what we'll do in the next video. Remember that in the last video, we set up a Lambda function, making sure to give it permission to access a SageMaker endpoint, and then we tested it to make sure it was working. In this video, we're going to create an endpoint that triggers our Lambda function. That is, we're going to create an endpoint or an interface that our web app can use in order to send data to our Lambda function. To do that, we're going to use API Gateway. If we go back to the Amazon console and then scroll down all the way to Networking and Content Delivery, select API Gateway. API Gateway lets you create an endpoint which you can use to trigger all sorts of things. For this example, we're going to use it to trigger a Lambda function. So click on Get Started, and then click on OK. We would like to create a new API, and our API's name is going to be Sentiment Analysis. Then we click on Create API. So we have a new API. Currently it doesn't do anything. Let's add an action, which we can do by clicking on the Actions drop-down menu, and then selecting Create Method. Which method? We are going to use a post method. Now, this involves knowing a little bit about the HTTP protocol. However, that is a bit beyond the scope of this course. So we want to create a post action. Once we've selected post, we click on the check mark, and a new post action has been created for our endpoint. What kind of integration type would we like? Well, we would like it to integrate with a Lambda function. Furthermore, we would like to use Lambda proxy integration. This means that our API is not going to do any sort of data checking whatsoever. It is just going to send whatever it receives to the Lambda function and then return back to the caller anything that the Lambda function spits out. Which Lambda function are we going to use? The one that we created earlier called Sentiment Lambda function. Once we have made sure that we are integrating with a Lambda function, made sure that we are using Lambda proxy integration, and selected the Lambda function we want to use, click on Save. Yes, we would like to add permission for our API to access our Sentiment Lambda function. So we've created an API, and we've given that API something to do. Now we need to actually deploy it. Again, if we click on the Actions dropdown and select Deploy API, we need to give it a deployment stage. Now this has something to do with the different types of environments you might need to deploy this API in. For example, if you just wanted to test something internally, you might deploy this to a test stage. For us, we're just going to call our deployment stage prod for production. To do that, we select the drop-down menu and add a new stage. The name of that stage is going to be prod. Once we've done that, we can click on deploy. And that's it. Our API is now deployed. And this is the URL that our API can be accessed at. So if we send a post request to this URL, the body of that post request will get sent to our Lambda function, and our Lambda function will return to us whatever the results of our model is. So now we have a Lambda function that does the data processing we need, we have a model that creates the prediction we need, and we've created an API that allows us to access all of those things. Next, we're going to launch the web app using our newly created API. So we've built a model, created a Lambda function that lets us interact with that model, and then created an API or an endpoint that allows us to send data to our Lambda function. The last step is to actually launch our web app. To do that, we need to know the URL for the endpoint that we've created. If we go back to the API gateway page and select the API that we created in the last video, and then on the left-hand side click on Stages, we can see that there is the single stage that we created last time, prod. Selecting this gives us information about our API. In particular, at the top here, it tells us the URL that can be used to invoke the API. So let's copy this. If we now go to the Notebook Hub, where we originally opened up the web app notebook, you can see that there's an index.html file. Selecting the checkbox to the left and then clicking on Edit lets us edit this. Now, you don't need to know how this web page works, but what you do need to do is make sure you add the name of your deployed endpoint. This is an old one here, so I can get rid of it and replace it with the new endpoint that we just created. Now that we've done that, we can save this file, close this page, and now if we open up this web page, we'll be able to use our web app. For some reason, just clicking on this doesn't seem to work correctly. However, if I select the checkbox to the left and click on Download, and then run it from my local computer, it does seem to work. I'll just zoom in, and now we can submit some reviews to see whether or not our model thinks they're positive or negative. We'll start with a very positive review. Let's see what our model thinks of this review. It seems our model was right. Okay, how about a negative one? And we can submit it to our model. Okay, so our web app is now working. Since we don't really have any further use of our web app, we need to make sure to shut everything down. In particular, we need to make sure to shut down our deployed endpoint. Remember, the cost of an endpoint is based on how long it's running for. So if you don't have a use for it, you need to shut it down. If we head back to the notebook and scroll all the way down to the bottom, we can delete our endpoint by executing this code cell right here. Of course, you can also use the console as I showed you in a previous video. In addition to shutting down the endpoint, you may wish to delete the Lambda function that you created and delete the API that you created. To do that, heading back to the Amazon console, first, to delete the Lambda function, select Lambda under the Compute heading, and you will see the Lambda function that you created. Selecting this, clicking on Actions, and going down to Delete will allow you to delete this Lambda function. To delete the API that you created, go back to the Amazon console, scroll down to Networking and Content Delivery, and select API Gateway. Again, here you will see the API that you created. Select it, click on the Actions dropdown, and select Delete API. You will need to type in the name of your API to confirm that you do want to delete it. And that's how you can clean up all of the different resources that you used in order to launch your simple web app.
In this lesson, we're going to take a look at how you can use SageMaker to create better tuned models. Often, when we are creating a model, we have to choose some hyperparameters. For example, you might need to choose the number of vertices in a tree created by a random tree model. Or you might choose the size of a hidden layer in a neural network. It would be nice if there was a way to test a whole bunch of hyperparameters and then pick the best performing model. SageMaker provides a process for doing this called hyperparameter tuning. Next, you're going to see how you can do this on your own models.
In this lesson, we're going to take advantage of SageMaker's hyperparameter tuning functionality. Essentially, what SageMaker can do for us is train a bunch of different models and choose the best one. Of course, we are going to have to tell SageMaker how many a bunch is and what we mean by best model. To start with, let's remind ourselves how SageMaker trains a model. I'm going to open up the Batch Transform XGBoost high-level notebook. I've already opened it up and run the first few cells. And the important ones here are in step 4 when training the XGBoost model. Remember, what we do is we first create an estimator object, and this kind of acts as a wrapper for the parameters that we're going to use to construct our model. We then set parameters that are specific to the model that we've chosen. In our case, because we've chosen XGBoost, these are some of the hyperparameters we wish to set. And then we call the fit method, and SageMaker takes care of creating a training job and executing it for us. So how do we know that these hyperparameters are the best hyperparameters for the model that we are working on? And the answer is basically trial and error. We would maybe change this to 6, or change this to 0.3 or 0.05. We'd make some modifications here, and then we would train the model another time, and then we would check to see whether the metric that we're using, in this case RMSE, has decreased when we change these hyperparameters. This is a very iterative process where we're just sort of plugging in new numbers up here and training the model again and checking the output. And since that's very routine, we would hope that there would be an automated way of doing this, and there is. This is what SageMaker's hyperparameter tuning does. So instead of giving gamma, say, a parameter value of 4, we would give it a range of values, and then SageMaker would try different values in that range, and then using, by default, Bayesian optimization, it would find the optimal, or attempt to find the optimal value for gamma. Optimal in this case is going to depend on whatever training metric we use to differentiate different trained models. Before we see how to do this, I just want to take a moment to talk a little bit about this output that we see here. When a training job successfully completes, part of what is displayed here is the output that the Docker container containing the XGBoost algorithm that was running output to standard output. Sometimes when you get an error, you don't get this output in the notebook. This output still exists, however, to look it up, you need to use something called CloudWatch, which I'm going to show you in a moment. In order to use CloudWatch, we need to look at the logs that were generated by a specific training job. In this case, scrolling all the way up to the top, we can see that the name of the training job is this one right here. So now if we open up the SageMaker console and we look under training jobs, we will see right here at the top is the training job that we just created. Selecting this and scrolling down, we see that there is a section called Monitor, and in particular, there's a link called View Logs. If we click on this, it will open up the logs for this particular training job inside of CloudWatch. So now if I select this, it will give me a list of all of the output that was generated during this training process. As I said before, this can be a very useful way to diagnose issues that might arise when training a model. It's also useful when you have a deployed model. If it starts acting strangely, the errors may appear here in CloudWatch. Also, when working on the project, you'll note that you can include some of your own custom code. And if you wanted to, you could print output using that custom code, and it would appear here in the logs. If you open up the Boston Housing XGBoost Hyperparameter Tuning high-level notebook, which I've already done here, and then execute the first few cells, and scroll down to the part where we want to train the XGBoost model. To begin with, we construct an estimator object in exactly the same way as if we were just training a single model. Essentially, this is going to be used as the base model, which SageMaker will change and tweak in order to test various hyperparameters. Next, we will actually set some hyperparameters. Now, again, this is going to be the base model from which SageMaker will depart. So by default, we'll set eta to 0.2, for example, although we may allow SageMaker to vary that later on. So now we've set up our estimator object. It's time to create a new object, which in this case is called a hyperparameter tuner object. To begin with, we give it an estimator object, which acts as the base model. We tell it how to differentiate between two different trained models. In our case, we are going to use the RMSE metric, and in particular, we care about the metric applied to the validation dataset, not the training dataset. Next, we want to find the model that minimizes the validation RMSE. Max job says how many models we want SageMaker to train in total. Max parallel jobs says how many models we want SageMaker to train in parallel with one another. Lastly, we tell SageMaker what different ranges we want to give specific hyperparameters. So for example, this eta hyperparameter, we tell SageMaker that it should be a continuous parameter in the range 0.05 to 0.5. Once we've created the hyperparameter tuner object, we simply call fit on that hyperparameter tuning object, in the same way as we would on an estimator object. Now, much like some of the other training jobs that we've constructed in the past, the work that SageMaker is doing is happening in the background. If we want to have a visual representation of what's going on, we need to use the wait method. And now we wait for the hyperparameter tuning job to complete. Now that SageMaker has finished training a bunch of models for us, we can take a look and see what the best trained model was. This is stored in the best training job method. As we can see, this is the name of the best training job. In the past, when we wanted to create a transformer object in order to create a batch transform job to test our model, we did so using an estimator object. However, we don't have an estimator object which has been trained. We created an estimator object earlier in order to create the hyperparameter tuner object. However, the original estimator object has not been trained. What we can do is create a new estimator object using the attach method and attach this estimator object to a training job. This will result in creating an estimator object that is trained, and in fact is associated with the model artifacts that were created as a result of the training job that we pass in as a parameter. In this case, we're passing in the name of the best training job. So XGB attached is now the trained estimator object associated with the best training job from our hyperparameter tuning job. From there, we can do the same sort of stuff that we did before when testing our model. That is, we create a transformer and then start our transform job, waiting to see what the results are. Now that the batch transform has finished up, we can copy the resulting output back to our local notebook instance and then create a nice little chart to see how well we did. Now that you've seen how to use SageMaker's hyperparameter tuning functionality, it's time to try it out for yourself. In the mini projects folder, there is a notebook called IMDb Sentiment Analysis XGBoost Hyperparameter Tuning. In this notebook, much like the other mini project notebook, there isn't really much for you to do here except in step 4, where instead of creating a single XGBoost model, you will use SageMaker's hyperparameter tuning functionality to train a bunch of different models and then pick the best one. To make things a little more interesting, somewhere in this notebook there's an error. I would encourage you to just continue along throughout the notebook as if there is no error, and when you do encounter a problem, try diagnosing it yourself using CloudWatch. If you get stuck, the solution notebook is also included, and in the next video, we'll go through my solutions. Now that you've had a chance to try out SageMaker's hyperparameter tuning for yourself, let's take a look at my solutions. So, as I mentioned earlier, the first 3 steps are the same as the other mini project that we worked on, so I've already executed those cells. Starting here with step 4, the first thing, of course, that we do is make sure that we split our dataset up into a validation and training set, and then save those datasets to our notebook instance. Once we have our dataset saved to our local notebook instance, we use the upload data method to upload those datasets to S3. Next, we do the same thing that we did in the other mini project, in that we first get a little bit of information about our current notebook instance, including both our current role and the name of the container that is specific to the region that we are currently working in. Just like in the previous notebooks, the first thing to do is create an estimator object. Here I've created an estimator object in the same way that we did in the previous XGBoost Sentiment Analysis notebook. And furthermore, I just used the same hyperparameters that we used last time as well, including making sure to change the objective to binary logistic. Now that we've created an estimator object, which serves as the basic model, which SageMaker will use in the hyperparameter tuning job, we need to set up the hyperparameter tuner object. Like we discussed in the last video, we first provide the estimator object, which is the base model. We then say which metric we would like to optimize. In our case, again, we'll be using RMSE of the validation set. And then we describe what makes a model better. In this case, it is having a smaller RMSE value. Next, we tell SageMaker the total number of models we'd like it to create for us. In this case, I've just chosen 6 because each of these training jobs takes a bit longer than the Boston housing example, so I don't want to wait too long. Next, we tell SageMaker how many models should be created in parallel. And lastly, we describe the ranges that we want various parameters to take on. Now that we've created the hyperparameter tuner object, we just ask SageMaker to train it. And as we discussed, this is all going on in the background. So we just wait for it to finish. Now that the hyperparameter tuning job has finished up, we can test our model to see how well it's doing. As before, first what we do is we create a new estimator object by attaching it to a training job which has already completed. In this case, we want to attach it to the best training job that was found during the hyperparameter tuning job. Now we have a trained estimator, and we can use that trained estimator to create a transformer object. Once we've done that, we can start our batch transform job to test our model. As before, remember that the transform job is done in the background, so we need to call the wait method to wait for the transform job to finish up. It seems as if the batch transform job failed. So why might this be? Well, unfortunately, the output here doesn't quite seem to lead us to what the issue might be. And in fact, down here at the bottom, it says, see job logs for more information. So this seems like a good opportunity to take a look at CloudWatch to see what sort of output this batch transform job generated and to see if we can figure out what the error might be. If we go back to the SageMaker console and look down here under batch transform jobs, we can see the batch transform job that failed. Selecting this transform job and scrolling down to the monitor section, we want to click on the View Logs link, which will open up the CloudWatch logs for this batch transform job. We want to take a look at the data log here, and if I do that and click on it, and I look at the listing here, it says that for some reason, when reading the test dataset, there is an issue. If I look even closer and I start expanding each of these errors, we can see right here that this error tells us that the inference data that was sent had 5,001 columns, whereas the number of features that should be presented at inference time is only 5,000. What this seems to imply is that there is some issue in the way that we've created our test data set. So if we go back to the notebook and scroll all the way back up to where we created the test data set, we can try and inspect and see where the issue might arise. Now, it appears as though we saved the test data set in the same way that we saved the validation and training data sets. Remember though that the training and validation data sets require the ground truth labels, but the test data set does not. So this is sort of the wrong way to go about saving the test data set. So what we should have had here is this line right here. That is, we just save the test data set directly to CSV, and we do not include the ground truth labels. Once we've done that, we need to make sure to upload the new test dataset to S3. Once that's done, we can run the batch transform job again, making sure to include the location of the newly uploaded correct test dataset, and then wait for it to finish. Now that the batch transform job has finished up, we can copy the output files to the local notebook instance and check to see how well our model is doing. Now that you've had a chance to try out SageMaker's hyperparameter tuning, let's take a look and see in a little more detail what's happening. To follow along, inside of the tutorials folder, we're going to be working through the Boston Housing XGBoost Hyperparameter Tuning low-level notebook. Of course, the beginning of this notebook is like the beginning of the other low-level notebooks, in that we first import any modules that we need, download the data, split the data up, upload the results to Amazon S3, and then we train and construct the XGBoost model. In this case, however, we are going to use SageMaker's hyperparameter tuning API to train a bunch of different models. To begin with, this looks a lot like the low-level batch transform notebook, in that to start with, we construct this training parameter dictionary. And inside of this dictionary goes a bunch of information, such as the role we want the training container to be run as, which training algorithm we'd like to use, which in our case is going to be XGBoost, where the data should be saved, what sort of remote instance should be used, a stopping condition in case something bad happens and we end up with a very lengthy computation, like for example an accidental infinite loop, and then the first difference. Rather than specify the hyperparameters for the algorithm that we are going to be using, instead we specify only the static hyperparameters. That is, the hyperparameters that we are not going to vary using SageMaker's hyperparameter functionality. In this case, we are going to leave gamma fixed at 4, leave subsampling fixed at 0.8. Since we are trying to determine the median cost of a house, it makes sense for our objective to be linear regression. Of course, we don't want that to change. And then we'll leave 10 as our early stopping rounds and 200 as the maximum number of iterations of the algorithm. Next, we specify the input data. Now this is again similar to when we constructed just a training job. We describe the data we want to use as the training data. We say where it is, that it's on S3, that it's CSV data, and we do the same thing for validation. So in short, this training params object is very similar to the training params object we created when making a training job. The difference is instead of setting hyperparameters, we set only the static hyperparameters. We'll set the ones that we want to allow SageMaker to vary a little later on. Now that training param object is used to create the base model that SageMaker will use, similar to the way that we constructed an estimator object to be used as the base model in the high-level approach. To specify the things that are allowed to change, we need to set up a tuning job. To do that, we first specify the different parameters that we allow to vary, first specifying the continuous parameters with a max value, a min value, and the name of the parameter, and also specifying the integer parameters, again with a minimum value, a maximum value, and the name of the parameter that we are allowing SageMaker to vary. After that, we specify the total number of models that we want SageMaker to create for us, and the total number of models that should be created in parallel. Bayesian is the strategy that SageMaker will use to update the modified hyperparameters. And lastly, we need to tell SageMaker how to determine when a model is better or worse, and we do that by saying that a model is better if the validation RMSE is minimal or is smaller. So we have a data structure which describes the base model, and we have a data structure that describes how the tuner should operate. If we put those together, we can create a hyperparameter tuning job. As with everything SageMaker related, we need to make sure to name this job, and the name needs to be unique. Now there is a further constraint on the tuning job name that you should be aware of. Most of the job names that we construct are allowed to be up to 63 characters long, so we have quite a lot of flexibility in the name that we prepend to the timestamp. In the case of a tuning job, the maximum length is 32 characters, and the reason for that is that the tuning job will create a bunch of training jobs, and it will automatically assign those training jobs names based on the tuning job name. So that's just something to keep in mind. You might get an error if you make the tuning job name too long. Once we've specified a name, we can create a hyperparameter tuning job by saying what name we want it to have, providing a tuning job configuration that tells SageMaker which hyperparameters vary and by how, and a training job which describes the base model. Of course, SageMaker, in addition to creating the job, will start running the job, and like always, it gets done in the background. So if we want to have some sort of visual representation, we need to use the wait for tuning job method. If we'd like to see a little more in detail what's going on with our tuning job, we can switch over to the Amazon SageMaker console, and on the left-hand side, select Hyperparameter Tuning Jobs. You will see at the top here that there's a tuning job in progress. This is the tuning job that we just created, and it tells us the current progress in terms of the number of models that have been created. So far, 0 models have been created out of the first 3 that are about to be created. If we click on this link, we can see all sorts of additional information. As the individual training jobs that are created are completed, they will form this list here, and we can look at details corresponding to each of these specific tuning jobs. And in addition, as the tuning job progresses, we can take a look at the best training job to this point. Of course, currently we haven't completed any training jobs, so there is no best. And as one more piece of information that might be of use, we can take a look at the hyperparameter configuration, and that just provides us a nice summary of the tuning job that we created. Heading back to the notebook, we will wait for this tuning job to finish up. Now that the tuning job has finished, you can see that we've got a whole bunch of output here. This output describes the results of our tuning job, and one of the most important bits is all the way down here where it says best training job. You can see that this is an entry in the resulting dictionary which contains the name of the tuning job that performed the best. So we're going to need that name so that we can create a model from the training artifacts associated with this training job. Now, if you don't want to go through this output and copy and paste, you can get a copy of this object by using the describe hyperparameter tuning job method of the SageMaker client. All you have to do is provide it with the name of the tuning job whose information you'd like to get. Now, tuning job info contains all of the information up here. In particular, it has the name of the best training job. Using that name, we can use the describe training job method to get information about that training job. In particular, we can get access to the model artifacts which are stored on S3. Once we have a URI to the model artifacts, we can use that to construct a model object. Remember that in SageMaker, a model is a collection of data that contains the container that is meant to be used during inference, in addition to the model artifacts that were created during training. Once we've created the model object, we can create a batch transform job to test our model. To create a batch transform job, we do the same thing as we did in the previous notebook, in that we just create a data structure that it contains all of the information about the batch transform job we wish to create, and then we ask SageMaker to execute that batch transform job and wait for the results to see how well our model is doing. Now that the batch transform job has finished up, we can copy the results to our notebook instance and then take a look and see how well it did.
In this lesson, we're going to look at how you can change a deployed model without needing to first shut it down. There are many situations that might arise during the life of a deployed model that would cause it to no longer function as well. For example, maybe you're creating a recommendation engine, and its job is to recommend to a user different articles they might find interesting. Over time, your user could develop new interests, or maybe old interests no longer apply. In that case, retraining your model might be a good idea. Once you do, you will need to deploy that new model and replace the old one. SageMaker provides functionality to let you do this without interrupting service to the end user. Next, you're going to learn how to use this functionality yourself.
In this lesson, we're going to take a look at updating an existing endpoint. Suppose that you had already constructed a model and deployed it, and that deployed model is now being used in an application somewhere. You might later on need to change the model, but want to do so in a way that didn't interrupt availability to whatever app was using it. SageMaker provides functionality that allows you to do this and not have any downtime. In addition, we're going to look a little bit closer at the low-level way of creating endpoint configurations, as this will allow us some more flexibility and let us build some slightly more sophisticated endpoints. For example, we'll take a look at creating an endpoint that sends data to multiple different models. This might be helpful, for example, when doing an A/B test. Along the way, we will also be using a mixture of the high and low-level approaches to creating things inside of SageMaker. This can be helpful in your own work because the high-level approach is really convenient in some cases, but in others, you may need the flexibility of the low-level approach. To start with, we're going to look at the Boston housing dataset again, and as we have done before in other notebooks, we will begin by creating an XGBoost model that models the median cost of a house in the Boston area. We of course import all of the necessary modules, including all of the SageMaker ones. Then we load in the data, split it up into training, validation, and testing datasets, save that data to our local notebook instance, upload it to S3, and then we go off and train a model. To do that, remember, first we create an estimator object which uses the XGBoost container for training. We then set hyperparameters specific to that algorithm, and then we call fit to fit our model to the training and validation data. Now the result of calling the fit method is that model artifacts have been created. However, the model itself has not yet been created, and when using the high-level approach, the model won't get created unless it needs to be. For example, if you create a transformation object or if you deploy the model. Since we want to have more control over the deployed model, we are going to create our own model using the low-level approach. So to do that, we set up the data structure that describes which containers should be used for inference, and in addition, points to the model artifacts that were created earlier. Once we've done that, we can ask SageMaker to create the model, and once we have a model, we can create an endpoint configuration. Now this is the same sort of endpoint configuration that you've seen before, where we only have a single production variant, and we call that variant XGB model. Once we have an endpoint configuration, we can ask SageMaker to create an endpoint with those properties. Once that's done, we can test our endpoint to make sure that it's working. First, we serialize the input data, and then send it off to our endpoint. The resulting response we can look at, and like most things in SageMaker, the result is a JSON object, which from a Python perspective might be thought of as a dictionary object. This response object contains a bunch of information about the results of our model. In particular, it tells us the format of the data that was returned. It tells us the name of the production variant that our data was sent to. Now, in this particular case, our endpoint only ever sent data to a single model, so we should expect that this is the variant that the data was sent to. And we have a body object, which is a streaming object. In order to access the contents of a streaming object, we need to first read it in, and once we've read it in, we have a bit stream. Since we know that our result should be an actual string, we need to convert that bit stream into a string, which we can use the decode method to do. The result is almost 40, which is not super close to the true result, but is close enough. Now we're going to use the XGBoost model a little more later on, but for now, we can shut down the endpoint that we created. Next, we're going to create a second model. So we've created an XGBoost model, and it's deployed and being used somewhere in an application. But it turns out that for some reason, our XGBoost model is too complicated. Maybe it's taking up too many resources at inference time, or we're just having to use it too often, or maybe we can't explain the way it works very well, and so what we'd really like is a much simpler model that we can explain. In any case, suppose that now what we'd like to do is create a linear model. We can create a linear model in much the same way as we created an XGBoost model. We will start by using the high-level approach to create the model artifacts, which can be done by first creating an estimator object, making sure that the container that we use during training is the linear learner container. And just like in the XGBoost case, we need to set some hyperparameters specific to this algorithm. In this case, our data has 13 features, and so we need to make sure to set the feature dimension to 13. We are doing a regression because we are trying to estimate a real number. And the linear learner algorithm, while creating a linear model, does so by looking at mini batches. In particular, it uses the gradient descent algorithm in order to fit the model. And so we can set here the number of rows that are used in each mini batch. Once we've set the hyperparameters, we can then call the fit method, and SageMaker will take care of creating the model artifacts for our linear learner model. Now that we've finished fitting our linear model, we can go ahead and deploy that model much in the same way as we did with the XGBoost model. First, we create a model object inside of SageMaker by describing where the model artifacts are being stored and which container should be used to perform inference. Once that's done, we can create an endpoint configuration. Much like the XGBoost example, we have only a single production variant, and we call that production variant the linear model. Now that we have an endpoint configuration that uses our newly trained model, we can ask SageMaker to create an endpoint with those properties. Once our endpoint has been set up, we can go ahead and try and test out our model to make sure that everything is working the way we expect it to. Just like with the XGBoost endpoint, we're going to send the first row of our test data, which we do by first serializing it and then sending it off to our endpoint. And just like in the XGBoost case, we get a JSON object as a response, which in this case tells us that our return type is JSON data and that the variant that was used was the linear model. Of course, we expect that the variant used was a linear model since we only have one production variant listed. So now if we read in the body object and turn it back into a string, what we get, as described in the response variable, is a JSON return. In this case, it is a JSON object which contains the score of 35.8. So if we compare that again with the true value, we can see that in this particular case, the linear model is actually doing a little bit better than our XGBoost model. Of course, looking at a single data point is not a very good way of determining how good a model is behaving, but it at least gives us something to look at. Next, since we're not going to use the linear model all by itself, we're going to shut down the endpoint. So far we've created two different models, the XGBoost model and a linear model. Suppose now that we wanted to switch from a deployed XGBoost model to a new linear model. However, we want to make sure that our new model is performing at least close enough to our XGBoost model. One of the ways we might do this is by performing an A/B test. That is, we create a new endpoint that receives a bunch of data, and then the endpoint decides which of the two models to send that data to. We can do that when we set up an endpoint configuration by listing each model as its own production variant. So here, we are creating a new endpoint configuration in which we have listed two production variants. The first is the linear model, and we give it the name linear model. And the second is the XGBoost model, whose name is XGB model. The amount of data that the endpoint will send to each model is dependent on the initial variant weight. The way that SageMaker determines the proportion of data to send to each model is that it will take a total of all of the weights, and then it will say the proportion of data that I send to the first model will be that model's weight divided by the total. And it will perform a similar calculation for each of the other production variants. In this case, we have two models, each of which has weight 1. So the total is 2, which means that 1/2, or half of the data, will be sent to the linear model, and the other half of the data will be sent to the XGBoost model. Once we've created that endpoint configuration, we can of course ask SageMaker to create an endpoint with those properties. So our endpoint is up and running, and we can send some data to it. So as we've been doing so far, we will start by sending just the first row of our test dataset after we serialize it to this new combined endpoint. In the response, we can see that our data was sent to the XGBoost model. Next, let's take a look at sending the first 10 rows of our test dataset to the endpoint and print out the response from each of those calls. We can see that the first one was sent to the XGBoost model, the next was sent to the linear model, XGBoost again, XGBoost, linear model, etc. Essentially what SageMaker is doing is whenever data comes into the endpoint, it flips a coin. Heads goes to the XGBoost model, tails goes to the linear model. If at some point we forget the configuration of a deployed endpoint, we can use this describe endpoint method of the SageMaker client. The return result will be a JSON object, or Python dictionary, which describes all of the properties that we set about that specific endpoint. This is a little difficult to read, but we can see here that there's an entry for production variants, which includes the linear model and the XGBoost model. So now suppose we've been running this A/B test for a while, and we've been collecting data, and it turns out that it's working pretty well. Our new linear model is working very well. So we'd like to complete the change. That is, instead of having our endpoint send data to both the XGBoost model and the linear model, we'd like to change it so that it only sends data to the linear model. To do that, we can use the update endpoint method of the SageMaker client. All we have to do is specify which endpoint we'd like to update and what endpoint configuration we would like that endpoint to look like once the update has finished. In this case, we are going to update our previously deployed endpoint so that its configuration only sends data to the linear model. Of course, this is happening in the background. In the meantime, if we take a look at the endpoint as it currently exists, we can see that it currently has two production variants, the linear model and the XGBoost model. The reason for this is that the endpoint which uses the linear model endpoint configuration has not yet started, and SageMaker wants to make sure that our endpoints never go down. So in the background, SageMaker will first launch a new endpoint with the configuration that we want to change our deployed endpoint to. Once that new endpoint is ready, it will then configure the existing endpoint so that it routes all data to the new endpoint that has been created. This way, the end user never sees any downtime. To see this, let's wait for our endpoint to finish being updated. Now that our endpoint has been updated so that it only points to the linear model, we can ask SageMaker to describe this endpoint and see that indeed, the current endpoint has only a single production variant, which is the linear model. Of course, we should make sure to shut down the endpoint now that we're finished with it. So we looked at how you can create an endpoint that sends data to more than one model, and we looked at how you can update an existing endpoint so that there's no loss of service to the end user. In this mini project, we're going to take a look at a fun problem that tries to mimic in some ways the sort of issue you may encounter in a real-life scenario. In particular, once you've created a model and it's deployed and being used, what happens if the underlying data distribution changes so that your model no longer performs as well as it once did? In this notebook, you'll go through the process of examining some new data, trying to figure out why your model no longer behaves as well as it once did, and then updating that model to take into account the new data. If you get stuck, don't worry. Solutions are provided. And in the next few videos, we'll go over my solutions. Alright, so hopefully you had some fun going through and trying to complete this notebook. Now let's take a look at my solutions. To start with, the first 4 steps are things that we've looked at before in previous notebooks, so I've executed those cells in advance. At this point, we have an XGBoost model that has been trained and which we tested and seems to be performing pretty well. So the story at this point is that our XGBoost model is good enough that we want to put it in production. So we've deployed it somewhere and it is being used by some application. Over time, we collect some reviews from users and we create ground truths for those reviews. We could maybe do this by hand or find some other mechanism to do that. But regardless, we've collected a bunch of these sample reviews and we'd like to see how well our model is performing. This is a part of health checking our model, essentially. So we load in the new data, and the first thing we do is encode our new data so that we can send it off to our XGBoost model. Remember that the processing that we'd perform on a review is in 2 parts. First, we stem our input so that things like hunting and hunt appear as the same token. Then we look at the 5,000 most frequently occurring words in the training set. We call that our vocabulary. And then for each review, we count the number of times each word in our vocabulary occurs, and we store that vector of length equal to the vocabulary, in our case it's 5,000, as the bag of words encoded version of our review. Now our new data has already been tokenized. However, we still need to create a bag of words encoding of it. To do that, we create a count vectorizer object using the vocabulary that we created earlier on in the notebook. And we want to make sure that there's no extra preprocessing or extra tokenizing happening. Once we've created that count vectorizer, we can use it to transform the new data to get the vectorized or bag of words encoded version of our data. As a quick check that this transform operation did what we expect that it did, we should double check and make sure that any of the rows in our new data set have length equal to the size of our vocabulary. In our case, the vocabulary size is 5,000, so the length of each of the reviews should be 5,000, which it is. Okay, now our goal here is to test our model to see how well it's doing on the new data. So to do that, we're going to set up a batch transform job. And in order to execute a batch transform job, we need to first save the new data locally into a CSV file. And then we need to upload that CSV file to S3 using the upload data method. Once our data has been uploaded and is available on S3, we can go ahead and use the transformer object that was created earlier and transform our new data to see how well our model is performing. Once the transform job has finished up, we can copy the results to our local instance and then check to see how well our model is performing on the new data. Oh, it turns out not so great. So something has gone wrong here. I think that a reasonable explanation is that something has happened to the underlying distribution. So that is that the words in our new data set don't mean the same thing or aren't being encoded as well as they were in the original data set. So what can we do to try and look and see what's happening here? So the original XGBoost model is now deployed, helping set up the scenario that we are trying to tackle. And we have reason to believe that something about the nature of the problem we were trying to solve has changed. And the way this change is expressed is that our model no longer works as well as it used to. So what we'd now like to do is figure out what's going on. Why is the new data not being classified as well as the original data? To start our investigation, we will take a look at some of the examples of reviews that have been misclassified. This will give us some idea of what's going on. As an aside, the way that I've created this method here is as a generator. And if you've not really been exposed to generators in Python before, now might be a good time to take a look. In an overly simplified sort of way, all you kind of have to do is replace a return statement with a yield statement. What this means is that once there is a single return value available, it will return that value, and then if you call next on the resulting generator a second time, it will continue from where it last left off. So if you notice here in the for loop, I iterate through each of the rows in our new data set. When the first example of a misclassified review is found, it will return that result, stopping this loop. However, in some sense, it doesn't really stop the loop so much as pause it so that it can be continued on later to find the next example. This is just a useful way of going through a big bunch of data to find counterexamples because it means that we don't have to process the entirety of the new data set. The way this works is that we first create a method that has this yield keyword inside of it, and we use that method to construct a generator. After that, whenever we call next on the generator, it will construct the next counterexample for us. So here's the first one. This is an example of a review which has been misclassified by our XGBoost model. And if I execute this cell again, I'll get another example. And if I execute it again, I'll get yet another example. So you can use this method to explore some of the incorrectly classified reviews. Suppose that after looking at these for a while, you think that one of the problems is that the usage of words has changed between the original dataset and the new dataset. One of the ways of looking at this discrepancy is to look at the 5,000 most frequently occurring words in each of the two datasets. Now, 5,000 isn't just a randomly chosen number, this is the size of our vocabulary. So another way of looking at this is that I'd like to compare the vocabulary that we used when we initially created our model to the vocabulary that might be used if we use our new data to train a model. So to do that, let's create a count vectorizer and fit it to the new data. This will allow us to take a look at the resulting vocabulary. Once the count vectorizer has been fit to the new data, I can create a set containing the words in the original vocabulary and a set containing the words in the new vocabulary so that I can look at the difference. So this, for example, will take all of the words in the original vocabulary, remove those words that also appear in the new vocabulary, and show us what is left over. Similarly, this will take all of the words in the new vocabulary and remove the words that also appear in the original vocabulary, leaving us with this. So I don't really want to give away the answer here. The intent here is for this to be very open-ended, but as far as next steps go, you might want to take a look at how often each of these words appear in their respective training sets. For example, how often does spill appear in the original training set? How often does Masterson appear in the new data set? You may assume that these words don't appear very frequently in their respective data sets. If they do appear frequently, that might be an indication that something funny is going on. So now we have reason to believe that something has changed about the underlying distribution of the data. And our proposed solution is to train a new model on the new data and replace the original model. To start, we need to make sure that we create a valid training set. So earlier we used the new reviews to create a new vocabulary. Now we need to use that new vocabulary to create a bag of words encoding of our new data. Once this is done, as a quick check, we should make sure that the size of any row in our new bag of words encoded dataset is equal to the length of the vocabulary that we were using. In this case, our vocabulary has length 5,000, and so we should expect the length of each row to also be 5,000, which it is. Once that's done, we need to split our new data into a training and validation set so that we can save our new data along with the new training and validation sets to our local instance. Once that's done, we upload all of the data to S3 using the upload data method so that we can create and train a new XGBoost model. We begin by setting up an estimator, and in this case I've used the same hyperparameters as we used in the original XGBoost model. Once we've created the estimator object, we can then call the fit method and fit our new XGBoost model to the new dataset. So now we should probably make sure that our new model is behaving in a way that we expect. One of the first ways we will do that is by testing our new model on the data that we use to train it. In practice, this is a pretty bad idea. Since we use the new data to train the model, testing it on that same data is sort of a textbook example of leakage, and you should never do this in a real application. In our case, the reason we're doing it is so that we have a numerical baseline to compare things to. So, in order to test our new model, we create a new transformer object, which we use to create a transform job on our new data. Once that transform job has finished, we copy the results to our local instance and check to see how well it's doing. Seems like our new model is behaving pretty well on the new data. Of course, we expect this to be true since our new model was trained on that same data. A second thing we're going to check is that our model is behaving okay relative to the old data. We don't expect that the distribution has changed so much that our new model should behave very poorly on old data. So we start by reading in the original test data and then transforming it. The reason for doing this is that we are using a new vocabulary for our new model. And so we need to make sure that when we create a bag of words encoding of the original test set, we use the new vocabulary to do it. Using the new vectorizer that we constructed earlier, we can transform the original test set into a bag of words encoded version. Once we've done that, we can write the results to our local instance, upload that file to S3, and then transform it using our new model. Once that's done, we can check to see how well our model is doing, and it seems like it's doing not so bad. So in general, it would appear that our new XGBoost model is doing exactly what we want it to. It's performing well on the new data, and it's performing well on the old data. Seems like it would be a good idea to switch our existing endpoint to using the new model. Of course, since we are imagining that we have some application running using the original model, we should make sure that we use SageMaker's update functionality so that our endpoint never has to get shut down. Recall that in order to update an endpoint, we need to create a new endpoint configuration. And in order to create an endpoint configuration, we need to know the name of the model we'd like to send our data to. We can get that name from the transformer object that we created earlier. Once we've got the model name, we can then create a new endpoint configuration. In this case, we're creating an endpoint configuration which has only a single production variant, which is our new XGBoost model. And once that endpoint configuration has been created, we can ask SageMaker to update our existing endpoint so that its new configuration uses the new XGBoost model. Now, in our real-life scenario, this would be a job well done. We have diagnosed a problem, created a solution to that problem, and then updated our endpoint such that our end user didn't experience any loss of usage. Since we no longer need the endpoint that is deployed, we should make sure to delete it. I'd also like to point out that there are some additional questions here at the end, and these questions are really meant to be open-ended. For example, what other ways could the underlying distribution possibly change if we were trying to create a sentiment analysis model? This might be useful in more applications than just determining whether or not a movie review is positive or negative. For example, in some cases, firms use sentiment analysis of shareholder reports to determine whether or not a stock is going to perform well or poorly. Another question is, since we didn't want our model to change too significantly from the original model, was it a good idea to train the new model using only the new data? Should we have instead mixed the data in some way? And if so, in what proportion should we mix it? Lastly, in this example, the new data that we received was quite significant, so we could use it to train our model. But what if you had much fewer examples? Suppose that you were given a new dataset that only had 500 samples. Not really enough to create a new model, but enough to know that your old model wasn't behaving very well. How would you fix that? As I said earlier, these questions are meant to be open-ended, and there isn't really a right answer to any of them. They're meant to give you an idea of some of the problems you might have to tackle in a real-life scenario. In this module, you learned a little bit about deployment, and in particular, you learned how you can use SageMaker to create and deploy your own machine learning projects. Before you go, let's talk a little bit about the different things that we learned about, starting with the notebook instances. For the most part, we've been using the notebook instance as our primary touchpoint for SageMaker, and it will likely be the case that this is your main method of interacting with SageMaker as well. It provides a convenient place to do some data processing, and then ask SageMaker to perform various computations to help you train and test models. We also talked about training jobs. We performed training jobs using the high-level approach by letting SageMaker take care of setting up the job specifics. Later on, we looked at how we can define those job specifics ourselves. Then, when we wanted to train a bunch of training jobs to test various hyperparameters, we learned that we could use SageMaker's hyperparameter tuning jobs to do that. We also learned how to create models, which in SageMaker is a collection of data. Essentially, it is a pairing of model artifacts that were created during a training process and a container that contains code that uses those model artifacts to perform inference. We also talked about endpoint configurations. These describe to SageMaker how a specific endpoint should be set up so that when data is sent to it, it gets forwarded on to the correct model. In some cases, you may even want to have an endpoint send data to multiple models. In addition, we saw how once we have an endpoint configuration, we can ask SageMaker to create an endpoint. Currently, I don't have any endpoints running because, as I've mentioned many times, you are charged for the length of time that an endpoint is running. So if you don't have use for it, you should shut it down. A very useful functionality that we also discussed is a batch transform job. What this allows us to do is to perform inference on a whole bunch of data all at once. And it provides a very convenient way of doing so that we don't have to first deploy the model and then send our data points bit by bit, making sure to shut it down at the end. SageMaker takes care of all of that for us, launching the instance that performs inference, sending all the data to that model, and then shutting down the compute instance once it's finished. I personally think that SageMaker is a great tool for quickly developing machine learning jobs and then being able to start putting those things into production. I hope that you have a great time using SageMaker in your own projects, and I look forward to see what you make. Before we leave off, let's quickly go over the different Amazon Web Services resources that we've used and make sure that everything has been shut down and cleaned up. To begin with, you should make sure that any notebook that you have is stopped. That is not in service. Remember that you are charged for the length of time that your notebook instance is running. So if you have any running, you should make sure to stop them. Also, you should double check that you don't have any endpoints running. Remember, just like notebook instances, you are charged for the length of time that an endpoint is running for. So if you have any running, you should make sure to shut them down too. Those are the SageMaker specific resources that we've used throughout, but let's take a look at some of the other Amazon services that we've used. Clicking on the top left corner, we can go back to the main Amazon console. Aside from SageMaker, we've used 3 other Amazon Web Services. The first is S3, which is listed here under storage. In the free tier, you're given a certain amount of storage in S3 that you aren't charged for, but beyond that, or if you are no longer in free tier, it costs you some small amount of money for the space that you occupy on S3. So if you're done with all of the data, you should make sure to delete it. In my case, I would just delete the entire bucket. Heading back to the main console, one of the other services that we used was Amazon Lambda, which is listed under the Compute heading. With Lambda, you're only charged whenever your Lambda function is executed, and in the free tier, you're allowed to have some number of executions before you're charged. If you don't want to have a Lambda function hanging around on your account, you can just make sure to delete it. I've already deleted mine. Lastly, heading back to the main console, the third Amazon service that we used was API Gateway. You can get to API Gateway by scrolling down to Networking and Content Delivery. Remember that API Gateway allowed us to create an endpoint that sent data to the Lambda function. If you don't want any endpoint configurations hanging around on your account, you can also delete that here. I've already done that. That's it for the Amazon services that we used in this module. It's a good idea to make a habit of going through and checking each of the resources that you've used to make sure you don't have anything hanging around that may incur a cost. In this video, I wanted to give you a few tips and tricks that I've used while developing some of this material. SageMaker is a wonderful tool that can really help reduce the development time of a lot of machine learning projects. However, problems can be sometimes difficult to diagnose. We spoke in a previous video about using the CloudWatch logs, and it's something that I have found very helpful. In particular, say I'm training something, I can look at the training job and see if it has failed. The most recent training jobs here have no failures, but I can take a look at one of them. And if I scroll down, there is a link to the CloudWatch logs, which I can open up to take a look at the output that was generated by that training job. I found this to be very, very helpful. This is especially true when you are training a model that allows you to incorporate your own code. For example, any PyTorch model where you get to include your own training method. Sometimes errors can occur that are very difficult to diagnose, but taking a look at the output here can be very helpful, especially if you include some additional output in your provided code. Another general trick that I should mention is that you should not be afraid of copying and pasting. It is certainly the case that many of the things you need to do inside of SageMaker are very similar to other things that you've done inside of SageMaker. Training a model, for example, sometimes requires a few lines of code, but the changes between 2 different models being trained is typically very small. So copy and paste is your friend. Another thing I'd like to mention is the documentation. The main documentation is this document here. However, SageMaker, the platform itself, moves very quickly, sometimes more quickly than the documentation. So you're not always able to find all of the features that are available in the documentation. It's a fantastic place to look to start, but sometimes you have to look a little deeper. Another useful piece of documentation is the Python SDK. We've been calling this the high-level approach, and this documents sort of a different approach to using SageMaker, which can be helpful as well. And this document is also fantastic, but at times suffers from the same problem as the previous document in that the code base moves faster than the documentation. When in doubt, I would say don't be afraid to look at the actual code base itself. Fortunately, it's provided here on GitHub. One of the reasons this is really helpful is that the Python SDK, or the high-level approach, as I said in a previous video, makes some choices on your behalf, which can be fantastic because it can reduce the development time, but it can also be a little difficult to diagnose because you're not always sure what's happening. If you want to know exactly what's happening, checking the actual code can be really helpful. For example, I can open up the estimator Python file, which will include the description of the estimator class. That way I can scroll down and take a look at, say, what's happening when I try and set some hyperparameters, or train, or fit the model. I've actually found looking through the code to be really helpful, and it's also very well documented, so when I get stuck, that's usually where I turn. One last tip that I'll give you is that most of the problems that I encountered while developing this material had to do with naming the various objects that were created. The fact that you need to have a unique name is a blessing and a curse. It is a blessing in that you can reuse many of the objects that you have created at a later time, since each one has a unique name. It can be a curse when you don't quite pay attention to the naming convention that you've been using, or you're not careful about making sure your names are unique. Tips and tricks aside, I hope you enjoy playing with SageMaker. Good luck! The project that you will be working on is very similar to the XGBoost sentiment analysis web app that you created earlier on. The difference here is that instead of using XGBoost as your algorithm, you will be constructing your own neural network using PyTorch. Now, the PyTorch functionality in SageMaker is a little bit different than the XGBoost algorithm. One of the ways in which it's different is that you get to provide your own code. As a result, you won't be able to do all of the project inside of the notebook, and instead you're going to have to make some modifications to some Python scripts. Inside of the project directory, you'll see all of the things that you need to complete this project. The notebook will lead you through each of the steps, which includes all of the code that you need to complete and some additional questions that you need to answer. The train folder contains the code that will be used for training the model, and in particular, you're going to have to make some modifications to the train Python script. The serve folder contains the Python files that will be used in your deployed model. You will also need to make some changes inside of the serve folder in the predict Python file. Lastly, the website that you'll be creating that interacts with your deployed endpoint is inside of the website folder. Now, this website is essentially the same as the one that we used in the XGBoost web app, but you'll have to set it up to work with your own endpoint. Once you've completed all the steps in the notebook, make sure to package up the notebook and the files that you modified, in particular the train file, the predict file, and the modified index file.
Hello, welcome to this lesson on deployment. I'm Cezanne Camacho. I teach deep learning concepts here at UDACITY, and today I'm happy to have with me a deployment expert, Dan Mbanga. Could you tell us a bit about what you do, Dan?
Yes, and thank you, Cezanne. I lead Amazon AI business development efforts for machine learning services. On a day-to-day basis, I work with our customers from startups to large enterprises to ensure that they do successfully build and deploy their machine learning models on Amazon SageMaker.
So far, we've been talking a lot about machine learning models, and in this lesson, we'll talk about deploying trained models using cloud services like Amazon SageMaker.
I'll talk about the capabilities of SageMaker, and Cezanne will lead you through practical code implementations.
Getting comfortable with deployment, as with anything, is really all about practice. So we'll give you some insights into how to use SageMaker and its built-in tools, and challenge you to solve a variety of tasks along the way. Let's get started.
Welcome. Today I'm interviewing Dan Mbanga from Amazon AI. You work on business and technical initiatives at Amazon, including things like Amazon SageMaker. And that's kind of what I want to talk to you today about. So just to start, sort of front of mind, so we all have a working definition, how do you describe Amazon SageMaker to someone who's working with machine learning?
Yeah, thank you, Cezanne. Amazon SageMaker is an end-to-end machine learning service. Essentially, it solves the problem of building, training, tuning, and deploying machine learning algorithms. If you think about our story at Amazon, where we do have internal and external customers, that by internal and external customers, I mean us at Amazon Web Services, we work with internal Amazon companies that are building products for e-commerce or other services like Alexa. There's a lot of machine learning involved there, and there are thousands and thousands of data scientists and AI engineers around the world building and training machine learning platforms at scale. So we had that challenge of scaling machine learning, making it accessible to multiple developers, getting to understand the workflow of machine learning, and then training people and building tools around that workflow to make sure that we ease the process of eventually building products with machine learning. So gathering that experience, we basically decided to create Amazon SageMaker, which essentially follows developers and data scientists through the end-to-end process of building, training, and tuning machine learning algorithms. And if you think about that process, you have to think about collecting data. You have to think about an environment where people have to crunch the data, look at the data distribution, analyze the data, do the whole statistical approach of looking at data set. And then that environment needs to be organized in such a way that it has tools that are enabling these data scientists to essentially get that work done. And the third thing they need to do is to scale the process potentially of training these algorithms on large data sets. And then there's a very strong infrastructural orchestration need from that perspective. And the other thing that needs to happen is figuring out where the models are eventually going to live, either in a real application or on a device. And all of these design and orchestration decisions have to traditionally be the responsibility of data scientists and developers. SageMaker takes some of that responsibility away, the undifferentiated heavy lifting essentially, and make sure that data scientists and developers can focus on data science, and then the infrastructure and orchestration piece of the work is done by the platform.
So one of the things you mentioned is scale and products at scale. And I was wondering if you have some applications that you find the most interesting that are really enabled by these things that SageMaker makes available, whether it's data management or deploying to a huge number of customers.
Yes, there are two ways we can think about scale. Right? One on the explosion of data that exists out there now. If you think about social networks, if you think about using devices that are internet connected that are generating a lot of data, so many applications that could include chatbots, that could include social networks, applications really have the massive opportunity to deal with a lot of data and use that amount of data with machine learning algorithms that help understand the end users better, that help get to better decisions as far as potentially recommending products, for example, to these end users. So we see a lot of applications in the world of mobile development or Internet of Things, right, where large amounts of data are passed through machine learning algorithms. We also see a lot of applications in sports analytics, where you have the NFL, for example, using machine learning algorithms and platforms like SageMaker to transform the experience that end users have or consumers have in front of their TV with the benefit of machine learning.
I didn't think about that.
Yeah, and in Formula One, for example, does live analytics and then uses machine learning models in the back end to do some early predictions and then rebroadcast that experience back to the users on the TV. Mm-hmm. And so if you think about the stream of data that goes from the cars that are racing all the way up to the cloud, and the expectation to pass the insights in real time or in near real time back to the users that are watching the show, it's pretty incredible the amount of data that goes through the life cycle of machine learning.
A lot of what I've been focusing on when I teach machine learning is, training and defining these models. Mm-hmm. But there's a big other piece, and I hear a lot from industry professionals that building is probably the smallest piece of these technologies. The biggest part is really maintaining, updating in the face of gathering new data. Mm-hmm. So I was wondering if you could speak to what makes SageMaker and cloud services a sort of good skill to have career-wise for people who are looking to become machine learning engineers.
Okay, let's follow through the process of building a machine learning product, for example. Mm-hmm. As you know, that involves big data, that involves handling data, that involves getting from understanding a business problem and mapping that business problem to a machine learning problem. That's already a skill that you're teaching in the program. The other thing that people need to do is to get into collecting the right amount of data that would relate to solve that machine learning problem. So there's a data collection, organization, and analysis component to do there. And then the next thing that developers and data scientists need to do is to jump in the process of selecting a machine learning algorithm, building and training a machine learning model from that algorithm, and then validating that machine learning model against some metrics. That could be accuracy, that could be cost, that could be time, and many other parameters that are potentially used to the business. Mm-hmm. And then if they have a satisfactory machine learning model based on the metrics that they have, then they can put that in production. And if they don't have a satisfactory model, then they go back in the process of collecting the data or selecting different algorithms. So if you think about that entire end-to-end process of machine learning, as learners are going through the process of learning how to apply that process to the data, companies are also going through the process of automating that machine learning lifecycle. Mm-hmm. So there's synergy there where, as a learner, it's very important for you to get acquainted with a tool that can teach you the best practices involved in that process. And SageMaker does that. SageMaker would facilitate the process of collecting data, and then the platform would essentially instruct you as what are the best ways to look at data labeling practices and then understand how to hand over the data to a machine learning algorithm or model. And then when it comes to training machine learning algorithms at scale, the platform is designed with APIs and all the other related automation to essentially create clusters, apply hyperparameter optimization in some cases to the algorithms that you're training, and at the end give you some validation metrics for you to look at whether your machine learning algorithm was a successful trained algorithm or not. Mm-hmm. And then the next thing that is possible to do with the platform is automate the deployment of the machine learning model in production. So again, following the process of building and training and deploying machine learning algorithms. So if you get into that mindset, you stand much more like a higher probability of being successful in an interview with an employer that is interested in machine learning because they are going through the exact same process.
Yeah, the great thing about machine learning, right, is that these algorithms improve over time with more data, more examples. And when you think about developing a product, it's very different than something that's just a physical thing that you give someone, it's done. It's something that you want to be able to go through this cycle of gathering data, improving your algorithm, then giving the best thing to your consumers. So I think like really thinking about that whole cycle when you're a part of a team or an engineer who's in charge of all of that is really important. So I'm excited to be partnered with you and teach all these things.
Before we get into specific case studies, I want to talk a bit about how to approach solving tasks with machine learning. Generally, the algorithms you use can be broken down into two major types, supervised and unsupervised. I find it helpful to think of these in the context of a specific example, image classification. Say we've been given a bunch of images of vehicle types. Supervised learning means that our training data is made of images and their corresponding class labels. So we'll have images of cars, bikes, buses, and so on, all with their true label. The label is also called the ground truth. Then we can train an image classifier that takes in an image as input. Its goal is to produce a label that is as close to the true class label as possible. As we train the classifier, it tries to improve its accuracy. Supervised learning basically means we have a certain known target, in this case the known label, to aim for during the training process. And we achieve a successful training when the model is highly accurate at learning how to predict true labels given new data it hasn't seen before. In other words, data that wasn't part of a training set. Now, let's think about how we might approach this task if we were not given any labels. So, our training set is made of unlabeled images. We'll have to take an unsupervised approach. This means that instead of relying on given information about how to group or label data, we have to rely on finding natural groupings in the data. We can train an algorithm to separate images into clusters according to perceived similarities in color or geometric traits. But we don't really have a way of checking that these groupings are correct or incorrect, so there is no measure for accuracy. We'll have to develop a new metric for separating data into groups, something like the distance between similar and different groups of data, and at the end of a training, we'll end up with an image clustering algorithm. The way images are clustered together is really meant to give us some insights into what patterns naturally emerge from a given data set. In this first lesson, you'll focus on finding patterns in data using a variety of unsupervised algorithms in Amazon SageMaker. By the end of this lesson, you should be able to utilize SageMaker resources and apply these techniques to tasks of your own design. Now let's talk a little bit about model design and algorithm selection. Choosing an unsupervised or supervised approach has a lot to do with your end goal. Unsupervised learning is often most useful when your end goal is relatively simple. For example, when you only want to group similar observations, you don't need a lot of detail about each individual observation. To group vehicles into cars, bikes, or buses, you probably don't need the specific car model. Alternatively, say you've been asked to distinguish between different models of cars, like images of a Tesla versus a Toyota Prius. Then you may actually want to go the extra step of labeling your vehicle image data so that you can train a specific classification model. If you have a lot of unlabeled data, you may be wondering, how can I efficiently and accurately label this data? Data labeling is unfortunately a human-intensive task. Ideally, you would want to send your raw images to people who can manually draw bounding boxes around different car models, as recognizing car models is a problem you are solving. You may also think of ways to automate your data labeling task with the help of what is called an active learning model, which is a machine learning model that can learn from human initial annotations. SageMaker combines these two capabilities, or these two approaches, sending the data to real humans and creating an active learning model for future tasks, into one feature called ground truth. Ground truth tries to solve the problem of going from raw data to labeled training data. It allows you to first send some of your data to be labeled by humans. Then, having gotten these initial labels, it trains a machine learning model that learns to automate this labeling task in the future. Overall, this reduces the time and cost to label similar data sets in the future by about 70%.
Your first case study will be to analyze U.S. Census data. The census is a big survey that includes information about the demographic makeup of various regions in the U.S. One of its main purposes is to count up the population of each state. That number is used to determine congressional apportionment. But data like this has a variety of applications. The census includes information like the most prominent age range in certain areas of the U.S., the rate of unemployment, and so on. You can imagine using this information to create localized marketing campaigns, inform campaign strategies, and generally to learn more about certain areas in the U.S. In this lesson, you'll use a SageMaker Notebook instance to load in and process this data. When you explore the data, you'll see that it's just tables of information. It doesn't contain any class labels to aim for. So you'll employ unsupervised learning techniques to group this data. Unsupervised algorithms allow us to ask, what are the natural groupings that I can find in this population data? And which features are most effective at distinguishing these different groups? Your end goal will be to produce groupings that reveal some similarities and differences between regions in the US, segmenting the population based on shared demographic traits. This is called population segmentation. We'll approach this task step by step. First, I'll be going over an exercise notebook that demonstrates loading in and processing data. Then I'll show you how to deploy an unsupervised model. Intermittently, you'll get a chance to practice what you've learned in code exercises. You'll define population features and learn how to train and deploy an unsupervised model.
One commonly used image segmentation technique is k-means clustering. It's a machine learning technique that separates an image into segments by clustering or grouping together data points that have similar traits. As an example, let's look at this image of oranges in a bowl. If I ask k-means to break up this image into two different colors, it will give us an image that looks like this. The oranges and the lighter part of the table are all considered to be one cluster of orange points, and the dark background and any part in shadow are clustered as dark brown data points. But we're getting ahead of ourselves. Let's talk about how k-means clusters this data step by step. K-means is called an unsupervised learning method, which means you don't need labeled data.
Instead, unsupervised learning aims to group and characterize unlabeled datasets, and in doing so, often identifies patterns and similarities in groups of data. So, you can give k-means a set of any unlabeled data, like the pixel values in an image, and just tell it to break it into k clusters, where k is a variable whose value you choose. For the orange example, we chose a k equal to 2, and if we increased that to say k equals 3 or 6, we would get 3 or 6 different colored segments. In this case, those segments divide differently shaded parts of the oranges and the table. Let's go through a simple example in even more detail. Here's a small image, just 34 by 34 pixels, of a rainbow pattern. I'll use k-means to separate this image into 3 clusters based on color. To start, we know that each pixel in this image has an associated RGB value. In fact, we can actually plot the value of each pixel as a data point in RGB color space. The axes are just values for R, G, and B. And notice the values on these axes. Here, the highest R, G, and B values, say close to white, will be at this top corner. And if we turn this space, we can actually see that the points fall into natural color clusters. If I tell k-means to separate this image data into 3 clusters, it will look at these pixel values and randomly guess 3 RGB points that partition the data into 3 clusters. Let's call these points center point A, center point B, and center point C. It then assigns every pixel value to a cluster based on its closest center point. So all of these pixels on the left belong to cluster A, and these more to the right to cluster B, and these on the bottom to cluster C. And here I've divided each into a separately colored region. K-means then takes the actual average, or mean, of all the RGB values in each cluster, and these mean values become the updated values for each center point. Let's go back a step and take one cluster as an example, cluster A. K-means looks at all the pixel values in this cluster and computes a mean RGB value. Let's call that mean A. It then updates the position of the center point A to be this mean value. This is why I initially called these center points. They're supposed to be in the center of their cluster. And it does the same thing for cluster B and center point B, and cluster C and center point C, moving the guessed center points to the mean of their cluster values. Then this process repeats. New clusters are formed based on where they are in relation to these new adjusted center points, and then an updated mean is calculated from these clusters, and the center points are updated again. So there's a sort of pulling done by the data points to create new center points. This process repeats again, and the center points will generally move a smaller and smaller distance from their previous value after each iteration. The algorithm keeps repeating these steps until it converges, and convergence is defined by us. It's usually after a number of iterations, say 10, or based on how much the center points move after each iteration. If the center points move less than some small value, say 1 pixel, during an iteration, then the center points have converged and the algorithm is finished. The center points that arise at the end of this process should best separate the data. Next, let's see how to do this clustering in code. The first thing you'll want to do is get access to the notebooks that we'll be using in this lesson. I'm assuming that you've gone through this process before and already have an AWS account. So I've already logged into my AWS console here. And I'll just quickly go through getting to the SageMaker console and creating a notebook instance. It never hurts to practice, and this dashboard occasionally changes in appearance. So this is what it looks like as I'm going through this exercise. I've logged into my personal AWS account, and I have my region, which is in Northern California. And you should set this for yourself as well. Then I want to get to Amazon SageMaker, and I can just search for it by name. So here's the SageMaker dashboard. You can see a lot of buttons on the side that point to things like notebook instances, training jobs, as well as things like models and endpoints, which will be useful for monitoring how our models train later. For now, I want to actually create a new notebook instance, so I'm going to click on this button. Now, I actually have a couple of notebooks that I'm in the middle of working with, but it's okay if this is blank or looks a bit different for you. We'll be working with a completely new notebook anyways. So to create a new notebook, I'm going to click this button up here, Create Notebook Instance. You should see this pop up, a place to specify my notebook instance settings. First, I need to add a name for my notebook. You can call this whatever you like, and I'll name it something descriptive, like ML Case Studies. For many of the rest of these values, you can leave them as the default value. For example, the instance type is ml.t2 medium, which is a CPU instance that's going to be ideal for a development environment. Next, there's the IAM role. In small print, you can see a description of this role. It says choose a role or let us create a role with the Amazon SageMaker Full Access IAM policy attached. This role defines the permissions that your notebook has, like what data it can read or write. And a full access role will give us access to all the public datasets in S3, for example. I'd suggest you click this and select Create a New Role. Here you can see that by default, you have access to any S3 bucket with SageMaker in the name, and we can also specify any additional buckets. But for these examples, we won't have any, and so you can select None here, and then click Create Role to complete a new role. Okay, so we have an instance name, we have a type, and we have a new role that we just created. Now for VPC, lifecycle, encryption, and volume size, you can leave these as the default values. Now you could create an empty notebook instance right now, but we'll actually want to link this to a Git repository, and we can do that with this tab here. I want to link this notebook to a public Git repository. Specifically, I'll want to clone the lesson notebooks that are in a Udacity public repository called ML SageMaker Studies, and I can link to it by name. This repository holds examples for a bunch of lessons, and so I just need to create this one notebook instance to work through all of them. The last thing I need to do is just click Create Notebook Instance. Then you should get back to this main notebook instance page, and you should see that your notebook is in pending status. I actually deleted one of my older notebooks to make room for this new ML Case Studies one. It may take a moment for this to become in service, but once it does, you can select to open it in Jupyter or Jupyter Lab. I find Jupyter Lab to be most helpful when you're moving back and forth between files often, as you might in larger projects. But for these example notebooks, I'm just going to work in Jupyter. When you open this notebook instance, you should see all the files that were in the GitHub repository for ML SageMaker Studies. These are all the lessons and examples that we'll be going through. I suggest you create a notebook instance of your own and have that open in one tab while going through these lessons. That way you can alternate between learning and applying what you've learned. For the first lesson, I'll be working with the population segmentation directory. Tasks and exercises are presented to you in the Pop Segmentation Exercise Notebook, and if you need a place to consult a final solution, you can look at the solution notebook. So to work through this lesson, I'm going to click on this exercise notebook. Alright, next I'll go over the task of population segmentation and start loading and exploring the data we'll be working with in this exercise notebook. So I'm going to click into my population segmentation exercise notebook. So the first thing I want to do is make sure I'm operating in the correct kernel. So I'll go to Kernel, Change Kernel, and I can see that SageMaker offers a variety of different kernels to operate in. For all of these examples, we'll either use Conda MXNet P36 or Conda PyTorch P36. This indicates the type of deep learning framework that we might use. MXNet is the one that's built into SageMaker, and P36 indicates the version of Python we'll be using. So for this example, we'll be using built-in algorithms, and using MXNet-P36 will be the ideal kernel. And I can check which kernel I'm in by looking at the top right corner of my notebook. For this segmentation example, I should note that my strategy will be to go over this first notebook in great detail. And as we go through examples, I'll transfer more and more responsibility to you, leaving it up to you to complete the code, but I'll always provide a final solution notebook. Now you can read a bit about the US Census dataset here, and the overall approach I plan to take to segment this data. This notebook is really a modified version of code that comes from a SageMaker blog post linked here. In this notebook, you'll employ 2 unsupervised learning algorithms to do population segmentation. This aims to find natural groupings in population data and reveal some feature-level similarities between different regions in the US. To implement population segmentation, you'll go through a number of steps. First, data loading and exploration. Then data cleaning and preprocessing. After cleaning your data, you'll move on to dimensionality reduction with PCA. PCA stands for Principal Component Analysis, and you'll use these components to create new features and transform your original training data. Finally, you'll cluster your transformed data using a k-means clustering algorithm. We'll also get a lot of practice visualizing what each of these models, PCA and k-means, has learned to do, meaning we'll take a look at the components and the k-clusters that are produced by these models. Each of the exercises in this notebook are designed to give you practice with each step of the ML workflow, and to demonstrate how to use SageMaker tools, such as data management with S3 and SageMaker's built-in algorithms. Okay, so the first couple cells you'll see in here are loading a bunch of libraries, some for visualization and some that are specific to SageMaker, specifically the Botto3 and SageMaker libraries. SageMaker has many libraries installed, so you often just have to import the resources you want, much like in the workspaces in the Udacity classroom. Now we can get the data. This particular dataset is already in an Amazon S3 bucket, and I can load the data by pointing to this bucket and getting a data file by name. So first, I'll have to create a Botto3 client to interact with S3. Now if I run this cell, and I did this correctly, I should be able to look at a list of objects in that bucket. So here I'm calling my client, asking it to list all the objects that are in my bucket, and then printing out the contents of that bucket. And I can see there's just one file in here, census data for SageMaker. It's a CSV file, and I'm just going to get that one name. So I have the name of the CSV file that I want to retrieve. And to actually get an S3 object, I'm going to call our client again and call getObject, passing in the bucket and the key, which is the file name I just saved from here. And in this last line, I'm printing out what the data object contains. So this object actually holds a lot of metadata, including things like the content type, which is a CSV file here. At the end, I see this body tag and a label streaming body here. This streaming data is exactly what I want. So in the next cell, I'm going to access that body, read it in, and print out its data type. I can see that the data type is bytes, which I can read in with a call to io.bytes.io. This will finally give me a data stream that I can read in just like a CSV file and create a data frame of county information. So that was a number of steps to read in a data stream from an S3 bucket. But I really just wanted to show you how to load in any data from an S3 bucket. And later you'll see that you can also directly download data from the web. So I'm loading the data and I'm taking a quick look at what's held in this CSV file, just printing out the head or the first 5 rows of data. I see a census ID, a state and county, and a lot of other features that look like they're counting up people and percentages for different demographic characteristics for that county. The census records traits like total population, race, transportation methods, and labor statistics, and these traits have even changed over time, as ideas of population categories change. As with any population data, the traits paint a simplified picture of the US population, and real life is not as clean as this data. That being said, looking at commonalities or differences between regions can give you some really interesting and useful information. Now that we've loaded in the data, it's time to clean it up, explore it, and pre-process it. When you first explore any data, it's good to know what you're working with. How many data points and features are you starting with? And what kind of information can you get at a first glance? So you should investigate the shape of the data, and I want you to implement a simple data cleaning step, your first exercise. This will be to drop any incomplete data points, so any data with any columns missing or empty should not be included in the final training set. After you drop any incomplete data, I want you to do some data preprocessing. Eventually, you'll want to feed these features into a machine learning model. ML models need numerical data to learn from, and not categorical data like strings, like state and county. So you'll reformat this data such that the data is indexed by region, specifically by state-county. Then you'll drop the old state and county columns along with the census ID column, which is just an assigned number and doesn't give us any demographic info. So instead of having row indices, this data will now be indexed by state-county, and the rest of the features can remain as columns here. After completing your code, you should get a data frame whose start looks a bit like this. Basically, you want a clean data frame with no empty columns of useful numerical regional features to compare. If you complete all this code, you can move on to some interesting visualizations later on in the notebook. I also want to note that you should make sure to use the given variable names, as they may be referenced later on in this notebook. I'm assuming that you'll execute all of these cells in order, and for example, clean counties df, which should look like this final clean counties data frame, will be referenced later on in this notebook. If you get stuck on either the cleaning or reformatting exercises, or just want to check your work, you can consult my solution video next. So we've loaded in the data, and my first step will be to clean it up and explore it. Data exploration is one of the most important parts of the ML workflow, because it allows you to notice any initial patterns in data distribution and features that may inform how you proceed with modeling and clustering the data. So above, I loaded in the CSV file as a county's data frame, And here I'm just printing out the number of rows and columns in that data frame. Then on that data frame, I'm calling .drop NA across axis equals 0, which means I'm dropping any rows that have any incomplete data. And I'm saving this cleaned data frame as clean counties df. And then I'm printing out the shape to see how many rows of data I've lost. So if I run this cell, I can see that I originally started with 3,220 data points and 37 columns. Then after this cleaning step, I can see that I've dropped 2 rows of data, and now I'm down to 3,218 data points. Okay, so this clean data is what I'll want to use as I continue to process this data below. Next, I wanted to create a new data frame, indexed by state county instead of individual indices. So for each of the data points in our clean counties data frame, there is a state and a county value, and I can merge the two into a single string using a dash character. And then to index our data frame by this value, I'm going to call cleancountiesdf.index and set it to a new state-county value. So this is the first step, and I can see that now instead of having individual indices here, I'm indexing all the data by its unique state county. But I haven't dropped any columns yet. I can see that the state county corresponds to the index, and so now these 2 columns are actually redundant, and I can get rid of them. I'll also get rid of the census ID column, which doesn't really give me any meaningful information about these counties. So that's exactly what I'm doing in this next cell. I'm specifying the names of each of the columns that I want to drop, and then I'm calling .drop on our clean counties data frame to create a new clean counties df. If I display a few of these points, now I have the data frame that I want, indexed by state county and with numerical features as columns. And I can see that I've actually gone from having 37 column values to 34, and I can print out the entire list of those feature values here. So here's a list of all those column names in our clean counties df. We have the total population, counts of men and women, racial counts, labor counts, and a bunch of other data here. And now that we've completed this step, creating a nice clean counties data frame, we'll be able to do some interesting visualizations, looking at the distribution of data over all of our counties. In fact, in this next step, I'll want to compare some features and learn more about them. In the next cell, I'm going to display some histograms of our features, which will show the distribution of data points over discrete feature ranges. So first, I'm making a list of features that I want to compare. In this case, I've chosen a bunch of transportation types. These are specifically recorded as commute types. Do people drive, carpool, take transit, walk, or use another method when they commute to work? From looking at my data frame, I know that all of these features are represented as percentages, and so the x-axes of these plots should be comparable. So for each feature in this transport list, I'm going to create a single histogram, grabbing the feature values in the clean counties data frame by name, and specifying a number of bins to make in our histogram. So here's one example histogram of people who mainly drive to work. Each of these bin widths describes some sort of feature range. In this case, percentage points, so from about 0 to 5, 5 to 10, and so on ranges of percentage points. Then the y-axis is how many data points actually fall into these bins, so how many counties fall into a certain feature range. There's some spread here, so really I can see across counties, people commonly drive about 70 to 85% of the time, and there's even really small bumps close to 0% of the time. If I scroll down, I can see the same data for people who carpool in each county. Looks about like 10% of the time for the majority of counties. And I can see that for public transit and walking. And just intuitively, I think this makes sense. I think the concentration of people who use public transit are probably in big cities where those systems are already built, and it makes sense that that's a small percentage of the population. Now I want to note that I haven't sorted anything into clusters yet. I'm just looking at how people in our counties classify their own transportation method to work. I can even change the number of bins if I want a more granular look, upping the number to get a more detailed description of this distribution. Now this is only an example for transportation data, and there's a lot of other features in our data set. So as an optional exercise, I'm challenging you to create a set of histograms of your own. Create a list of features that you're interested in looking at, and display the resulting plots. After that, you'll be asked to normalize this data in preparation for training a PCA model. After dropping any incomplete data and taking a look at the results, you are tasked with normalizing the data. Above, when we looked at our clean counties data frame, you could see that the range of features was really large. Some of these columns have really big and wide-ranging values, and others have percentage values. Since unsupervised learning relies on looking at the relationships between features, I want these features to be consistently comparable. In fact, I want to scale all of these numerical features into a range between 0 and 1. And I can start to do this with a call to the sklearn pre-processing library, where I can import a min-max scalar. I can create a scalar object which is able to look at the minimum and maximum values in a feature range and divide every value by that range to get a normalized value between 0 and 1. So I'm creating a scalar, then to get my counties scaled data frame, I'm using fit transform, passing in my clean counties data frame as a float type, and applying that min-max scalar. This is a pretty typical normalization step. Now I want the features and the indices to be the same for this scaled data frame as they are in our clean counties data frame. That is, I want the columns to be our features and the indices to be our state county indices. And let's see the result. Now I can see that all of these numerical values are in decimal ranges. I can even go one step further and check that the maximum and minimum are what I expect. By calling .describe on a data frame, I can see stats like the minimum and the maximum value. And indeed, they're 0 and 1 respectively for all of our numerical columns. So we cleaned our data, we got rid of our categorical columns, and now we've just scaled it. Now we're almost ready to put this through a PCA model and reduce the dimensionality of this data for future analysis. Let's learn more about PCA next.
Hello and welcome. In this notebook, we will learn how to use principal component analysis for dimensionality reduction. Dimensionality reduction is one of the main applications of PCA. In the previous lessons, you've already learned how PCA works and about eigenvectors and eigenvalues. In this notebook, we will see how to apply PCA to a small dataset. Let's begin by understanding what dimensionality reduction is all about. Let's suppose we had some two-dimensional data that looks like this. We can see that most of the data points lie close to a straight line. We can also see that most of the variation in the data occurs along this direction, but there's not much variation along this direction. This means we can explain most of the variation of the data by only looking at how the data points are distributed along this straight line. Therefore, we could reduce this two-dimensional data to one-dimensional data by projecting all these data points onto this straight line. By projecting the data onto a straight line, we can actually reduce the number of variables needed to describe the data because you only need one number to specify a data point's position along a straight line. Therefore, the two variables that describe the original data can be replaced by a new variable that actually encodes this linear relationship. It is important to note that the new variable is just an abstract tool that allows us to express this data in a more compact form and may or may not be interpreted as a real-world quantity. Now let's see how we can do this in code. For simplicity, we will use a small two-dimensional dataset. In a later notebook, you will get a chance to apply what you learned in this notebook to real stock data. We will start by creating some randomly correlated data. In this code, you can choose the range of your data and the amount of correlation. The code outputs a plot with the data points and the amount of correlation. In this case, we chose our data range to be between 10 and 80. Therefore, the data points range between 10 and 80 in both the x and y axis. Remember, a correlation of 0 means no correlation at all, and a correlation of 1 means complete correlation. You can vary the amount of correlation and create the data that you like. Once you have created your data, the next step in PCA is to center your data around 0. It is also customary to normalize your data. This is known as mean normalization. While centering the data is necessary, normalizing the data is optional. And this is what I have done here. Mean normalization not only centers your data around 0, but also distributes your data evenly in a small interval around 0. As you can see here, the data is no longer in the range between 10 and 80, but after normalization, the data is now distributed between -3 and 3. This will help your algorithm converge faster. With our data centered, we're ready to perform PCA. To do this, we will use a package called scikit-learn. Scikit-learn's PCA class allows us to easily implement PCA on data. The first thing we need to do is to create a PCA object with a given set of parameters, including the number of principal components we want to use. We will start by using two components because we want to visualize them later. Here, we can see the parameters that the PCA algorithm is going to use. The next step is to pass the data to the PCA object using the fit method. A quick note: in scikit-learn, the PCA algorithm automatically centers the data for you, so you could pass the original data set to the fit method instead of the normalized data as we have done here. Once we fit the data, we can use the attributes of the PCA class to see the eigenvectors, also known as the principal components, and its eigenvalues. One important attribute of the PCA class is the explained variance ratio. The explained variance ratio gives us the percentage of the variance explained by each of the principal components. In general, the principal components with the largest eigenvalues explain the majority of the variance, and this is usually the ones that we want to keep. For example, here we can see that the first principal component explains 94% of the variance and has the largest eigenvalue. Now that we have the principal components, we can visualize them. Here we see the data with the first principal component and the second principal component. We can see that the first principal component lies along the direction in which the data varies the most. One question that you will frequently face is how many principal components you should use. For example, suppose you had a dataset with 1000 dimensions. Should you reduce this dataset to 500 dimensions? Or could you do better and reduce it to 100 dimensions? Usually, the number of principal components is chosen depending on how much of the variance of the original data you want to retain. For example, you may want to retain 90% of the variance, or you may only want to retain 50% of the variance. You can use the explained variance ratio attribute of the PCA class to determine the number of components you need to keep to retain a given amount of variance. For example, if you wanted to retain 90% of the variance, you can add up the elements in the explained variance ratio array until the desired value is reached. The number of elements you had to add up to reach the desired value determines the number of principal components needed to retain that level of variance. For example, if you had to add up 5 elements to retain 90% of the variance, then you will need 5 principal components. Now that we have seen what all the principal components look like, we will now use PCA to perform dimensionality reduction. Since the data we're using in this simple example only has 2 dimensions, the best we can do is to reduce it to 1 dimension. So we will now choose the number of principal components in our PCA algorithm to be equal to 1. Once we ran the PCA algorithm with only 1 component, we can see what the transform data looks like by using the transform method of the PCA class. In this simple case, the transform method projects the data onto the first principal component, so we'll just get a straight line. When working with higher dimensional data, the transform method will project the data onto the lower dimensional surface determined by the number of principal components you used in your algorithm.
One thing to note is that each data point here has 34 associated features. So this is 34 dimensional data, which is pretty high dimensional. Unsupervised algorithms rely on finding relationships in n-dimensional feature space. And for higher dimensions, we often get noisier clustering, for example. So an algorithm like k-means has a hard time figuring out which dimensions to pay attention to. And some of these dimensions are not as important as others. For example, if every county in our dataset had the same exact total population, then this particular feature wouldn't give us any distinguishing information. It would not help us to separate the counties into different groups, because its value doesn't vary between counties. This is just a hypothetical example. Instead, we really want to find the features that help us separate and group data. In other words, we want to find features that cause the most variance in our dataset. So before we cluster this data with k-means, I'll want to take one more step, a dimensionality reduction step.
My aim will be to form a smaller set of features that will better help us separate our data. The technique we'll use is called PCA, or Principal Component Analysis. PCA is most useful when you have a bunch of features and you want to find out which linear combinations of these features matter the most, which are responsible for the largest variance in our data. So to perform PCA, we'll use SageMaker's built-in model for PCA. To create any model, you'll first need to specify an IAM role and SageMaker session. These let the model know what permissions and session to train in. So in this cell here, I'm storing our SageMaker session by calling sagemaker.session. This is a capital S, it's a session object, and I'm storing that as a variable here. Then I'm getting the IAM role. We specified this role earlier, and I'm getting it by name with an import getExecution role, and I'll actually print it out to make sure it's the right name. So we have our session, and this role name should look familiar from when we created the notebook. Next, we'll also need a place to store the trained model in an S3 bucket. So in this next cell, I'm creating a default bucket from our SageMaker session with a call to .defaultBucket, and I'm saving the name of that bucket for reference later. If you print out the name of this default bucket, you should get something like this. It says SageMaker, and then it has your region, mine is US West 1, and then some numbers to make it unique. Then I'll start to build a PCA model, and I'll need to do a few things. First, I'm going to specify exactly where in our S3 bucket I'll want to store the trained model artifacts. I'll specify a prefix for a directory where I want to store the data, calling it counties for data about counties in the US. And here I'm creating the entire output path, which is a string that points to the bucket and the prefix directory. Next, it's time to define the PCA model. So this model is built in SageMaker, and I can import it by name, import PCA. Then I'm creating a model down here. I'm saving it as PCA-SM for SageMaker, and I'm calling our PCA constructor here. This takes in several arguments. First, I'm passing in the IAM role, which we defined above. Then I'm specifying the train instance count, which will usually be 1, and the instance type, which I'm setting as a C4x large. Then I'll specify the output path as this one that we defined above. Again, this is the place that the resultant model data will be stored in S3. Then I'm also passing in the SageMaker session that we also just defined. Now there's one last thing I need to specify, and that is a hyperparameter for the PCA model. Basically, this model needs to know how many principal components we want to create. We want to reduce our 34 dimensions of data, but we'll actually want to first generate enough linearly independent principal components to capture the variance in our data, and later select the top components to pass to a clustering model. So I'll define n components as 33. This is the existing feature dimension, 34, minus 1. And this is a good rule of thumb for starting PCA analysis. So again, I'm going to generate 33 of these principal components, but then later I'll select only a few of the top components to use in our final clustering algorithm. And this is going to be in all caps because it's a global variable. That means after defining it, I'll be able to access it in any later cell in the notebook. So let me recap how I create an estimator like this. First, I'm going to import that built-in model from SageMaker, and then this takes in a number of constructor parameters. It takes in the role and SageMaker session, which I got in a cell above here. They're default parameters that are accessible from our notebook. The session and role are variables that you can always get from your notebook instance. I also specified an output path, which is where this model will be saved after it trains in our S3 bucket. Then I had to specify the instance count and type for training, and lastly our hyperparameter for a PCA model, the number of components, 33, that we want to generate. Okay, so I'm running this cell, and then after defining this model, I'll actually want to create a training job and train it on our county's data. A requirement for all of SageMaker's built-in models is that the passed-in training data be a record set. This allows training of models within SageMaker to perform really fast, compared to, say, scikit-learn models, especially for large data sets. So to get a record set format, first I'm going to convert our scaled data frame into a NumPy array, calling values.asType float32. And I'll save this NumPy array as train data NP. Then I can actually call our model.recordSet and pass in this NumPy data to create our formatted training data in a record set format. So going from NumPy to record set, I get our formatted train data. Finally, to train the model, I call pca-sm.fit and pass in this formatted train data. If I run this cell, this should kick off a training job, and I can see the name of that training job here. This job will take a little while to complete, so I can show you a few things while it runs. I'm actually going to go back to my Amazon SageMaker console. Now, in all these buttons on the side, you'll see this one for training jobs. When I click this, I can actually see the PCA job that I just kicked off. It's in progress. And I'll see a list of all these other jobs that I've done in the past. But let's click on this most recent one that's in progress. So in here, I can see the job name and the IAM role that it's attached to. I can see that it's in progress and read a bit about the details about this training job. If I scroll all the way down to monitor, I'll actually be able to click on the logs, which will be really useful if I need to debug a training job, if it's failed, for example. The logs are where any errors and traceback will be recorded. A failed job has happened to me a few times as I've developed, and the key is just to read through the logs and debug. Debugging is part of coding just like any other step, so I just wanted to show you this option of how to explore more information about a unique training job. Back to our notebook, I can also see how the training job is monitored in the notebook itself. I'll see print statements and timestamps that indicate when an instance is being spun up, when input data is being downloaded, and some details about the training in progress. Then, because I was timing this, at the end I can scroll down and see how long this whole process took, a few minutes. Now that this training job is complete, I have a trained model, and next I'll actually want to see the principal components that the model has come up with. I want to see what linear combinations of features make up each component and decide on the number of top components to include as I create new reduced dimensionality training data. We've just trained the PCA model, and now we can access the underlying model parameters. One thing that we'll need is the name of the training job, and I'm going to copy it from here, but you could also get it from the AWS console. Saved model artifacts are stored in S3 as a tar file. This is a compressed file in the output path that we specified in the location output path, and it will also be saved in this output/model.targz extension. We can explore the artifacts that are stored here and use them to deploy a trained model. So in here, I'm going to copy and paste my training job name, and then the model key is going to be the prefix counties that we specified earlier, this job name, and the output extension. Then similar to how we downloaded the CSV file before, we're going to pass in that model key, the bucket name, and call download file on our Boto3 resource. Then I actually have a couple more lines of code that will unzip this compressed file and store it as model_algo-1. This name is consistent across models. So if this cell executed, this should print out the model key and some confirmation code. Now, built-in SageMaker models are built on something called MXNet. So I'm importing this as a library MX, and this gives us certain tools to use. I'm going to load in the parameters of our model by name, which is model_algo-1. And the MX library allows me to load this in as an ND array. I'm saving all of these as the PCA model parameters and printing them out here. I can see that this array holds three main values, S, V, and down here a mean value. And I'll be able to access these arrays by name. And I have some explanations of what each of these is here. The mean is the mean that's subtracted from a component in order to center it. This is part of the PCA calculation. V is the makeup of the principal components, so which linear combinations of original features make up each principal component. And S are the singular values of the components. Now we talked about getting components that will cause the most variance in our dataset. S will not give us the exact percentage data variance, but it can help us calculate a good approximation according to this approximate explained variance formula, which I'll go over in a bit. The important thing to note is that for looking at the principal components and the data variance, we'll be interested in V and S only. And I'm actually going to load these specific parameters, calling them by name, and loading them in as data frames, S and V here. So first let's talk about S and the data variance. I mentioned that from S, we can get an approximation of the data variance that is explained in the first n principal components. The approximate explained variance is given by this formula. This is the sum of S squared for all selected top n components over the sum of S squareds for all components. Why are we interested in variance in the first place? Why is variance so important? Well, the challenging part of doing dimensionality reduction with PCA is deciding on the number of top components we want to get from our data and eventually use in our final clustering model. Basically, we know we want to apply this PCA model to our original training data, which will return 33 principal components. But we only want to use a selection of the top components to create a smaller feature space, which will be better for clustering our population data. So out of our 33 principal components, how might we choose a good number of top components to include when we transform our training data? Do we choose the top 5 components, the top 10, or even more? Well, one thing we know is that PCA will create components in the order of causing the most to least variance. So say we have data in 3 dimensions like this. This is just an illustrative example that's actually taken from a PhD thesis on organizing genetic data. So these 3 dimensions capture 100% of the variance in our data, all of the spread up and down, left to right, and back and forth. In this image, you can see that most of this data is related. All of it falls close to on a 2D plane, and just by looking at the spread of data, we can visualize that these 3 dimensions have some correlation. It turns out that we can create 2 new dimensions that are made up of linear combinations of the original 3 dimensions. These 2 new dimensions are centered in the center of our data and angled according to these PCA component lines here. Now here you can see that we're projecting our 3-dimensional data into this 2-dimensional component space, our PCA transform space. Our axes are now defined by our PCA components 1 and 2. In this case, we're still capturing about 98% of our data variance using just these 2 new dimensions. So in this simple case, dimensionality reduction doesn't hurt our data representation much. Typically, and especially for higher dimensional data, there is a noticeable trade-off between the amount of variance we can capture and the number of component dimensions we use to represent our data. This is pretty intuitive. If you discard a dimension, you're going to lose some complexity in how you can represent your data. PCA basically works with this trade-off, and it's up to us to choose a number of components that both reduces the dimensionality of our data and still captures most of the variance of our data. Depending on your application, this number may vary, but for learning general patterns in a large base of population data, as we're doing here, it's okay to capture around 80% variance. Now, one thing to note is that the largest S values are going to be actually at the end of this S data frame. And so, for example, I can look at the top 5 singular values by looking at a certain starting index in this S data frame and printing those out. Now, to select our top N components and calculate the explained variance, your task will be to complete a function, explained variance. This function will take in the entire S data frame that we just got and a number of top principal components. This will be a value like the top 1 or the top 5 components and so on. Then you should use this approximate formula for summing square values for the top N components and dividing by the sum over all components and return the decimal percentage of the approximate explained variance. When you're done with this code, you can test it out here, and you should be able to answer what is the smallest number of principal components that captures at least 80% of the total variance in our dataset. Try to solve this on your own, and if you want to check your work, I'll go over my solution in the next video. Here's my solution for the explained variance equation. First, I need to know which S values to look at as far as our top components are concerned. Now, these are in reverse order in our passed in S data frame, and so for the top, say, 3 components, I want the last 3 values in the passed in S data frame. And I can get this index by getting our N components, 33, minus the N top components that are passed in here. So 33 minus 3 will result in an index of 30, for example. You could also choose to just iterate through each row of S in reverse, and this is just one solution. Then to calculate the explained approximate variance, I'm going to use this equation from above. This exact equation is for the top 5 components, but I want to generalize for any number of N top components. So to get S squared for my top N components, I'm getting the values from my start index on, and I'm squaring them with NP square and summing those values up. Then I'm dividing by the square values over our entire S array and summing those up. This will return something that holds a value at the index 0, and I'm returning that one value here. Here I'm calling the explained variance function that I just defined. I'm passing an S, our data frame from above, and a number of top components. I'll just try to see what the variance is for the very top component first. For just the top principal component, I get an explained variance of about 32%. Recall that I want to find the number of top N components that cover about 80% of our data variance, and I will use a mix of trial and error and also start with an educated guess here. Now, I know our current data has 34 features listed here, and this is just our feature list from the columns in our scaled counties data frame. But I suspect that many of these are correlated or redundant. In fact, I can basically see a few big genres here. I can see details about the total population, a simple gender and race breakdown, as well as details about income level, profession, transit type, and work employment type. So I'm actually thinking that a good number of top components will be around 7 or 8, and I can test that out. In fact, I can see that the explained variance for our top 7 components is around 80%. I wonder if I can go any lower. It looks like the top 6 correspond to about 76 or 77% of variance, so I do want to capture the top 7. So now I know that the top 7 components cover about 80% of my data variance, and I'll keep this number in mind and use it later to create some new training data. Next, you may be wondering what makes up these 7 components. What linear combinations of features make these components so influential in describing the spread of our data? So next, I'll show you how to take a look at the makeup of each of these top components. Recall that each of our PCA components is made up of a weighted linear combination of our original features here. And after seeing that the top components account for a large percentage of our data variance, it's interesting to see what exactly the makeup of each component is, which features define it. So in this next cell, I have a complete function, display component, that takes in the list of component weights, V, our features list, which will be the column names from our counties data frame, a component number like top 1 or top 2, 3, etc., and a number of top weights to display, which is any number from 1 to 34. By default, I'm going to display the top 10 most important feature weights. Okay, so line by line, similar to what we did for the S data frame, I'm getting the row index of the row that points to our component of interest. So just one row that's close to the bottom of our V data frame, because the components are listed from least to most important, in the reverse order that we saw in S as well. Then I'm getting the list of feature weights for a component, which is that row in our V data frame, and I'm grabbing the list of weight values. So our list of values is stored in V1. Then, using list comprehension, I'm combining these weight values and our list of features into one data frame. So this will give me one row of weight values that correspond to specific feature names. So this gives me a data frame of components, and then I actually want to sort this by weight value. I know I want to display the weights in order of importance. To find the most important weights, I'm going to look at the magnitude of each weight, which is the absolute value of the weight, and then sort those values in order. And here I'm going to be grabbing the top n weights. Finally, using the Seaborn display library, I'm going to display a nice bar plot that displays those weight values, the names of the features, and has a title for the component number that I passed in. So let's actually see what this looks like for our first component. Now we know from before that this first component captures about 32% of the data variance in our training data. And we can see that it's extremely negatively weighted with respect to white people, or people who were counted and identified as white during the census. And it's positively weighted for people who identified as Hispanic or Black, and also positively weighted for levels of poverty and unemployment. We can go back to this function and pass in more weights to display if we want a more granular look. And we can see more detail about public and private work and labor type. One thing to note is that these individual features are not independent, and the discrete nature of these categories means that some data will always be left out. For example, racial dynamics and socioeconomic opportunities are often intertwined, making some of these features more correlated than others. And these racial categories act as umbrella terms that don't always capture the complexities of people's identities. As data scientists and machine learning developers, it's important to think about why this data is collected in the first place and the limitations it has in describing a population. Basically, I encourage you to look at any data source with a critical lens, because that will give you a better idea of what insights you can eventually draw from this data. Let's check out another component. Now for our analysis, looking at the component breakdown will be useful in generally describing how our training data is clustered later. For example, when we create our reduced dimensionality data, if we see that a certain US county has a high value for the component 2, we'll know that it has a mix of these positively and negatively weighted features. So now you can use this function to look at the makeup of any component. Next, we'll actually deploy this PCA model, grab our 7 top components, and create new dimensionality reduced training data. In addition to looking at our trained model attributes, we can also use those to deploy a PCA model and use it to make predictions. To deploy a trained model, we simply call that model by name and call deploy. Then we pass in a few details about the instance count, 1, and instance type, which I'm using a T2 medium, for the endpoint. When I run this code, I can see that two things are automatically created. First, a model with some name, and an endpoint with some name. Now for built-in models, these two are often automatically created together, but for some custom models, as we'll see later, we'll have to separately create a model and then create an endpoint. You could also consider using a different, more powerful instance type, but a T2 medium is going to be fine for our purposes. This will take a few minutes to deploy, but once it does, we can then use it, applying it to our training data and transforming it into PCA components. In SageMaker, you've seen that an endpoint can be made accessible via a web app by attaching it to API Gateway. But in this case, we're just going to want to use this predictor to process our original training data and create dimensionality reduced data. Now that this predictor is deployed, I can use it to modify our original training data. To apply an endpoint to some data, I just have to call .predict and pass in our training data. This function is going to, by default, expect a NumPy array as input, and so I'm passing in the data that we converted before. If you recall, this was just our scaled, normalized, and cleaned data frame converted into a NumPy array. So this predict function is going to look at the features of every data point in this set and convert them into PCA components. So this will hold the PCA component values for each of our original 3,000 or so training points. Let's take a look at the first data point by printing it out by index 0. So this is data for just one of our counties. I can see a key projection and a float32 tensor. This holds our 33 component values. As with the rest of our analyses, the top components are actually going to be at the bottom of this list here. Now, using these names and this information about ordering, I want you to create a transformed data frame. Specifically, I want you to complete the function createTransformedDF. This will take in a list of our PCA training data that we just generated, our original county scale data frame, and a number of top components. I want you to create a data frame that's still indexed by state county, but each column corresponds to one of these top n components. So if this is 7 top components, you'll have 7 columns of data. Your resultant data frame should look something like this. This function essentially creates a data set where each county is described by the top n principal components, and it's exactly what we'll need to move on to k-means clustering. So try to complete this function, and if you do, you can move on to the next steps, which are deleting the PCA model endpoint that we're done using, and moving on to training a k-means model on this new transformed data. To create a new data frame and fill it with our new PCA component data, I wrote this code. The first thing I'm doing is creating a totally new data frame to hold all my new transformed data. And then I'm going to iterate through each data point in our PCA component data. And I'm getting our component values from what I saw before, getting the label, projection, and our float32 tensor values. Then I'm passing this list of components and appending it to our county's transformed data frame. Now this is going to be all 33 of our PCA components for each of our data points. Next, I know I still want to index by state county, just as in our county scaled data frame, so I'm setting our index accordingly. Then I know I only want to keep the top n components. I don't want all 33 of these features. I want, say, the top 7. And I know they're ordered from least to most important. So similar to how we've handled this before, I'm getting a start index, and then I'm getting a selection of data from that start index onwards. Finally, I'll return that truncated data frame in reverse order, so I'll have my top component as the first column in this transformed data frame. Now I can run this code and select top n components to create our new data, and I'll create our 7 top components because I know that captures 80% of our data variance. So I'm calling my createTransformedDataFrame function. I'm passing in my PCA component data for each of my data points and the original county scaled data frame. And finally, I'm passing in 7 top components. And this is the resultant data frame. So I'm still indexing by state county, and I have the values for components 1 through component 7. And I'll actually want to take one more step. Instead of having numerical values for each of these columns, I'm going to create a list of columns that's more descriptive. So component 1, 2, 3, up to 7. And you can change these names to whatever you want. So now I have a list of counties and their component values. Now that I have my transformed data, I no longer need my PCA model endpoint, and I can delete it with a call to our SageMaker session.delete endpoint and passing in the name of our PCA predictor. And you should always make sure to delete your resources when you're no longer using them. Otherwise, you may incur extra processing or storage fees. Okay, so I kind of want to recap all the steps that we've taken. We went from defining a PCA model, to training it on some formatted data. Then we took a look at the trained model attributes by loading in the model zip file with the mxnet library. We looked at the top n components and how much variance they covered in our data, and decided to use the top 7 principal components in our final analysis. We also care about the weights of the features that make up each component. This allows us to better describe the components that make up our transformed training data. Then to finally create our transformed data, we had to deploy our trained PCA model and apply it to our NumPy training data, and just now created a new transformed data frame. So this was a lot of demonstration around training and deploying a SageMaker model, and I left some of the data cleaning and transformation steps to you. Next, I want you to get practice with deploying models on your own, and so I'll give you some exercises around training and deploying a k-means clustering model. This final model will be created in a similar way to the PCA model. You'll define a k-means estimator, passing in appropriate parameters, and train it on this new transformed data. So read through the following exercises and instructions carefully, and see if you can complete all of them, getting all the way to k-means model deployment and even extracting the trained model attributes. If you run into an error, try to debug as usual by looking through the logs and traces. I'll provide instruction, and I'm even linking to some relevant documentation, which can help you in passing in the correct arguments to a k-means model, for example. The end goal will be to assign clusters to each of our data points and see 1, which counties are assigned to each cluster, and 2, what that means as far as component and feature level makeup. This will allow us to describe the demographic similarities and differences between counties generally. In the last video, we trained our PCA model and applied it to our original normalized training data to reduce the dimensionality of that data from 34 dimensions to 7 components. Using this transformed data, we're now ready to implement k-means clustering. The steps to create a k-means estimator and deploy it will look very familiar, so I'll go over the model creation, training, and deployment fairly quickly. Now our first step is to define a k-means model. And if I click on the k-means documentation, I can see exactly what parameters this takes in. I can see I'll have to import this k-means estimator and pass in a role and details about the train instance count and type. I can also see a hyperparameter here, k, and if I look at the documentation below, I can see that this is the number of clusters I want this algorithm to produce. In this notebook, I gave you some advice on choosing a good k. This is based on collected empirical data. Essentially, I gave you some information on looking at how close our data points are to each cluster center for various values for k. A bad value for k would be one so high that only 1 or 2 very close data points are near it. And another bad k would be one so small that data points are really far away from the centers. I wrote a bit about the elbow selection method, basically looking for a distance elbow that indicates that there's enough separation to distinguish the data points in each cluster, but also include enough clusters so that the data points aren't extremely far away from each cluster. The elbow method takes a value for k and looks at the average distance of each of your data points to their cluster centers. It looks at how this value decreases as k increases. And it says if you see an elbow or a place where this stops decreasing at a significant rate, then you should choose that k. I tried out some code for various values of k, and I think 8 is probably a good number of clusters to use here. We can see that the average distance is decreasing up until about this point. Okay, so when I defined a k-means estimator, I passed in a role, details about the instance type, an output path, which I'm just using the same one that I used for our PCA model, and a number of clusters, which I've specified to be 8. After creating this model, and I'm calling it k-means, this now expects to be trained on a particular kind of formatted training data. These are the same steps we took to train our PCA model. I'm taking our counties transformed data frame, and I'm converting it into a NumPy array of float values. Then I'm calling k-means.recordset, passing in this NumPy data, and this returns record set formatted data. Then I can call fit, passing in this formatted data, and creating a training job with this name. This is something you'll be able to refer to later if you want to take a look at the model attributes. After the training job completed, I then deployed this model and created a k-means predictor. Again, I'm using the same arguments as for our PCA model, and I can see that a k-means model and endpoint were created here. Then I can use this predictor to generate cluster labels for all of our data points. Here, I'm getting that predictor by name and calling predict. Then I want to get our NumPy formatted data and pass it into our predictor. So this predictor should take in our component training data and return some information about the clusters. In this next cell, I'm going to print out what that cluster info is for our first data point, the first county in our list. So for our county Alabama Autauga, I can see that its closest cluster is cluster number 3. And we also have the Euclidean distance to that cluster. Now each of our data points is in 7-dimensional component space. And when we talk about distance to a cluster, we're actually looking at distance in 7 dimensions between our data point and the center of its closest cluster. In the next few cells, I'm going to do some quick visualization and look at how many of our data points fall into each cluster. So here I'm looking at the label closest cluster, and I expect this to be a value like 3. I'm getting that cluster label for each point in our cluster info and storing it as cluster labels. Then I'm going to count up how many of our data points fall into each cluster, and I'll print out those counts. So these are in order from basically most popular to least, and I can see that most of our data points fall into cluster number 1. It's important to note that these are also indexed by 0. So there's a cluster 0 up to a cluster 7. And here's just another way to visualize these counts, which is just displaying them as a histogram. If I see that my data is wildly unevenly clustered here, it may be an indicator that my choice of k was not a great separator for the data. But this looks fairly evenly distributed among the clusters. Now I've stored all my cluster labels, and I'm actually done with the model endpoint. And so as a last step here, I'm going to delete my k-means predictor endpoint. Next, I'll challenge you to extract the trained model attributes so you can look at the data and cluster centroids. I've also included some visualization code. The best part of this is really getting to learn something about this data and show how counties are naturally grouped together. So next, try to do this on your own, and if you'd like, you can consult my solution. To really see the details of how counties are grouped into clusters, we have to look at the trained k-means model attributes. To get these attributes, we first have to find where our model is stored in S3, retrieving it by name. Where it's saved is defined by our output path, which is defined by our prefix, our k-means job name, and this extension output/model.tar.gz. And I just copied this from when I called fit above, but you can also find this in your AWS Training Jobs console. Then I'm downloading and unzipping the model file, saving it as model algo1. Then, just as we did with the PCA model, I'm loading in those model details using our MXNet library and loading it in as an array, and I can print out those values. This time I can see that k-means actually just has one set of model parameters, and there are no names associated with it. These values are actually our cluster centroids, the location of each cluster identified by our k-means model. The location is a 70 point in PCA component space, since that's the kind of data we passed into this model for training. So in this next cell, I'm getting those centroids from the model attribute array. I can see I have 8 clusters here and our 7 components. So this is the location of cluster 0 in component space. But this table alone is a bit difficult to translate into meaningful relationships. We can look at values and see which have the highest values and which have the lowest ones, but there's another way to visualize this. 7 dimensions can't be visualized in normal space, but I can look at this data as a heat map. On the x-axis, I have our cluster label, 0 through 7, and on the y, I have our components, C1 through C7. This heat map is basically showing me which of these weights is most important in defining a cluster. One thing that sticks out is our cluster 2. I can see that for this cluster, it has a really high value for component 1. Now, if you've forgotten what these components exactly correspond to, you can use the display component function from above. This takes in our data frame v, a list of features, and a component number, and I'm going to examine our first component again. So now this is telling us what demographic features make up component 1, and when I go back to this heat map, it gives me a little more insight into what exactly defines our cluster 2. Component 4 also looks like an interesting one. It has sort of a low value for cluster 2, but high values for cluster 0 and cluster 7. So let's take a look at that one. So by looking at our component makeup and this heat map, we can really start to tell something about the makeup of each cluster. But now, what does this have to do with our actual county data? You may be wondering which of our counties are clustered together and found to be most similar. So we can also map the cluster labels back to each data point, each county, and see which of them were grouped in the same cluster. So here I'm actually adding a labels column to our transform counties data frame, and I can sort it and see which are clustered in cluster 0, for example. And we can see the variety of counties in cluster 0 just from looking at the first few data points. We can see data points in Georgia, Louisiana, Florida, and Virginia, for example. And I can look at just one cluster at a time by getting a label equal to a certain cluster number that I'm interested in. So if I want to look at counties that are all grouped into cluster 1, I can. And these are still sorted by their original alphabetical order. I think it's interesting to note that these counties have similar characteristics as given by our principal components, even though they're in different states, for example. So this analysis is the end of this notebook. You've successfully completed population segmentation. This type of information is most often used to create localized marketing campaigns that want to target a variety of regions based on demographic similarities. Now, I'd encourage you to play around with the visualizations in this notebook. And as one last step, if you decide you're entirely done, I suggest you take further resource cleaning steps. And I've linked to some relevant documentation here. To do a thorough cleanup, you'll actually want to go to your main Amazon SageMaker console, and you'll want to click on Endpoint Configurations and Models, and manually delete them from the console. You can also go to S3 and delete anything in the S3 bucket. This is a good habit to get into. Now, using all that you've learned in this lesson, you should feel prepared to tackle any unsupervised task. Next, we'll recap what you've learned and then move on to supervised learning.
You've really learned a lot in this lesson, going from approaching unstructured tasks like population segmentation to creating features and deploying a k-means clustering model. Congratulations! The steps you took to deploy a segmentation model are steps you can use when approaching any other task. In our industry, often the most challenging step is the first one, figuring out what business question you want to answer. In this lesson, we gave you an example, which US counties have similar characteristics and what kinds of features define that similarity. Not all questions need machine learning to be answered, but for those that do, you'll need to collect and prepare relevant data. This step can take quite a lot of time and resources. It's also good practice to explore this data and see if there is anything notable about the distribution of the data or the different features. Once you have data that is ready to be fed into a model, you need to host that data somewhere. You can do this on your laptop by creating a notebook and saving your data locally. This is useful when exploring a small portion of your data. But for large data sets, you may want to upload those directly into a cloud storage such as Amazon S3. SageMaker allows you to spin up a notebook instance where you have the option of uploading and managing large data sets using an S3 bucket. In this lesson, you work with two different models. You train and deploy a principal component analysis model to simplify population data. This technique discards some information in the raw data and creates a few meaningful features. Then you use these features to train a k-means clustering model. After training, you were able to evaluate the model by looking at the model attributes. Finally, deployment gave you the ability to assign any data points to a certain cluster. And you could see which US counties were grouped together and what kinds of features they shared in common. And you did all of this from data cleaning to model deployment within a SageMaker notebook instance. In the next few lessons, we'll look at more real-world tasks. You'll be tasked with some supervised learning problems in which you can choose to use built-in algorithms or custom models of your own. So, I hope you're excited to learn even more. In this lesson, we'll look at using SageMaker for classification tasks, including fraud detection. The case study that we'll look at is specific to credit cards and detecting fraudulent transactions. The skills you learn will be applicable to a variety of tasks. So, first, what exactly is fraud detection? And how might we begin to approach this task? When I think of payment fraud, I think about someone finding my credit card information and using it to buy something for themselves. The way that my bank identifies something like this is by looking at my transaction and noting if something is atypical or outside my spending patterns. The challenge here is defining what exactly atypical means. Now, I live in New York, and transactions outside that area might stick out. But I also travel a lot, so location is not the best indicator. If I've only bought groceries in the past few months, maybe it would be suspicious if I go out shopping for lots and lots and lots of clothing. but that depends on things like holidays and my mood too. So you can see that fraud detection is a challenging problem. The task is really to identify the typical patterns found in valid transactions and then flag transactions that are way outside of those patterns. Machine learning works well here because it's designed to find patterns. So we'll use an algorithm that looks at historical spending data, transactions that are labeled as valid or fraudulent, and sees if it can parse out patterns that effectively distinguish those two classes. If we imagine that we are in a bank-like setting, it would be important to make this algorithm scalable and easy to update, and that's where the SageMaker interface becomes especially useful. Next, you get a chance to work with this data and code a solution of your own.
All of the exercises in this lesson are held in the ML Case Studies notebook we created earlier. So I'm going to start this up and just open it in Jupyter. I'll navigate to the Payment Fraud Detection directory and to the Fraud Detection Exercise notebook. To approach the task of fraud detection, we'll be looking at credit card data that was initially taken from Kaggle. This data includes thousands of transactions with anonymized features and class labels, fraudulent or valid. We'll follow a typical machine learning workflow, loading in and exploring our data, then moving on to splitting that data and passing it to a binary classification model. In this notebook, we'll start with training and deploying a built-in linear model using SageMaker's linear learner. We'll also discuss unique challenges that fraud detection has, such as imbalanced training data, that is a history of more valid transactions than fraudulent ones. A lot of this notebook will be about taking a model and improving it based on data or design challenges. As we go, we'll evaluate the models we train by looking at a variety of metrics for success, not just accuracy, but precision and recall as well. All right, so in the first cell, I'm loading in my usual resources. And in the next, I'm just storing my SageMaker variables. So that's the SageMaker session and role, which will help me define how we train our models, and a default bucket. The S3 bucket is where we'll store our training data as well as any saved model parameters. After getting my SageMaker resources, I'm going to actually load in our data from online. This link will get me a creditcardfraud.zip file, which I'll unzip here. You only need to run the cell once, and you'll get a creditcard.csv file. Then I'm going to read that data in as a data frame and print out the shape of our data. I can see I have about 285,000 data points. And if I look at the first few rows, I can see the features that this includes. It includes the time of transaction since the first transaction, and a number of anonymized features, V1 through V28. Then it has the amount of the transaction and a class label at the very end. So overall, I have 30 input features and a single class. 0 indicates valid, which all of these points are, and 1 will indicate a fraudulent transaction. Now, you can't learn much from these anonymized features, but you can look at how the data is distributed over each of our classes. So your first task will be to complete this function, fraudulent percentage. This function takes in the transaction data frame that we just loaded in, and it should return the percentage of the data that's labeled as fraudulent. And below, I've given you a test cell to test out an implementation of this function when you complete it. Now, the next step will be to ingest this data and use it to train our model. With that goal in mind, I'm going to give you this second task, splitting this data into training and test sets. That is completing this function, train test split. This again takes in our transaction data frame and a fraction of that data to withhold for training. The rest should be held for testing. So this default value of 0.7 means that 70% of our data should be kept for training, and then 30% should go to test data. So try to both calculate the percentage of data that's fraudulent and complete this function to split the data. I've left some guidelines in this notebook, but if you get stuck or want to check your solution, I'll go over my solution next. We loaded in our data, and here's my first solution for calculating the percentage of fraudulent data. First, from our transaction data frame, I'm counting up the occurrences of data points in each class using .value counts. This gives me back an array of counts. I can get the fraudulent counts from counts 1 and the valid counts from count 0. Then to get the fraction that I want, I just divide the fraudulent count by the total count here. Then I'm returning that fraudulent percentage and running my test cell below. I can see that out of about 285,000 data points, about 500 are fraudulent, which makes up about 0.17% of the data. So this is not even a whole percent that's labeled as fraudulent. Now, on the one hand, this is good. We don't want this person to have experienced many fraudulent transactions, but it will be challenging data to learn from. Many algorithms assume that we have a relatively even distribution of data among the classes,
and we'll get into ways to manage a class imbalance like this later on. Next, I wanted to split this data into a training set and test set for evaluation later. So here's my solution for splitting the data according to a passed-in train frac. First, I'm grabbing my data frame of transaction data and converting it into a matrix using df.esMatrix. This will make it easier for me to use NumPy functions to shuffle and split this data. Next, according to my passed-in random seed, I'm randomly shuffling all of the data in this matrix. And here I'm getting the train size, the amount of training data that I want to keep. This is going to be the number of rows of data in our matrix times the train fraction that's passed in. Since this fraction is a decimal value, I'll actually want to cast this to be an integer type. So I'm casting to an int because our data is discrete. That is, I can't have half a data point. So this is going to round down any float value, and this is okay behavior for such a division. Now this train size will be the index of the row that I want to split my matrix data at. So here I'm getting my train features up until that index train size. And I know my class labels are in the last column of the data frame, so I'm not including that in the features here with -1, not the last column. Then here I am getting that last value to save as my class labels. Then I'm doing something similar with the test features and labels. I'm getting the remaining rows of data, notice the placement of train size before the colon here and after here, and then here getting the last column of test labels. Finally, I'm just returning all of these in a specified return order, training features and labels and test features and labels in separate tuples. So this completes my function. Now I can call this function in the next cell and test out the shape. I'm leaving a default split of 0.7 for my training data, so 30% of my data should go to test data. Then I have a few tests on here that check that I have the correct shape for each of these features, and that all of my labels are indeed zeros and ones. This cell prints out the number of training points that I generated, about 200,000, the number of test points, and a test first item and label. I should see 30 features in this first item and a single class label. 0 indicates a valid transaction. So now that we have all our train data and test data, these are almost ready to be fed into a model. So next I'll outline how to build and train a binary classification model. So we've loaded in our transaction data and split it into training and test sets. Now it's time to define the model that we want to train. In this exercise, we'll utilize SageMaker's Linear Learner, which has two main applications. One is for regression tasks, in which a linear line is fit to some data points. In this case, you want a model that can produce a predicted output value given some data point, such as predicting the price of a house given its square size. The second use is to do binary classification, in which the linear learner basically learns a line to separate two classes of data. It effectively outputs labels, either the class label 1 for data that falls above the line, or 0 for points that fall on or below the line. And this is a simple two-dimensional case, but you can think of this as a plane or multi-dimensional line for multiple features. In our case, we'll want to use this as a binary classifier, and use it to predict our two transaction classes, valid 0 or fraudulent 1. As with any machine learning method, we'll first train our linear learner on some existing training data, so it can learn a good separation line. Then we'll apply it to some new test data to see how it generalizes and performs. You can instantiate a linear learner in the same way that we've been doing other models, passing in some constructor hyperparameters, the role and output location in addition to specific model hyperparameters. For your next exercise, I've given you a link to the linear learner documentation. This should give you enough information to create a linear learner estimator. When you click on this link, you'll see that there are a lot of parameters you can pass in, but I'd suggest only passing in a few, like the role and training instance types, as well as specifying that we do indeed want a binary classifier. You can leave most of the parameters as the default value. If you complete this step, you're welcome to move on to converting our training data, training an estimator, and even deploying it. In the next video, I'll go over one solution to creating a linear learner model, and then later we'll go over a few specific parameters and improve this model one step at a time. Here's one way to define a linear learner. I've imported the linear learner estimator from SageMaker. Then the first thing I'm doing is specifying where in our S3 bucket I'll want to place the saved model attributes. In this case, specifying a prefix, credit card, and then a full output path in S3, which points to the bucket and to this directory credit card. And this is just good practice to get into, because it helps organize the contents of your S3 bucket and means you can always access a saved model from a known location later.
Okay, then I'm instantiating an estimator called linear and passing in arguments to linear learner. You can see my usual SageMaker parameters. I'm passing in the role, the SageMaker session, and the output path that I just defined. I'm also specifying details about the train instance. I want one instance that's a C4 X large. Then for this linear learner, I need to specify the predictor type. This tells my estimator that I want it to be a binary classifier rather than a regression algorithm. And finally, I'm passing in a number of epochs to train for. It turns out that the default value number of epochs is 15, and this is just the number of times that our algorithm will iterate over our entire training set as it learns. My idea here is that I'll start with the default, and then if it looks like I could use more training, I'll up the number of epochs, but if it looks like my loss decreases really quickly, I can consider decreasing this number. Now that we've instantiated an estimator, I'll want to actually train it on our training data. As for any built-in algorithm, you'll need to format the training data that the split function returned, first into a NumPy float data array, and then into a record set format. So your next task will be to format this data and train the estimator. If you make it past this point, you'll be given some instructions to deploy the trained model. And if you want to check your work, I'll quickly go over a solution in the next video. In the last video, we instantiated a linear learner model, and I want to quickly go over how we formatted the training data. I essentially want to take the train features and labels that were generated from my split data function above and turn them into a record set that my estimator can use for training. So my first step is going to be converting my features and my labels into a float32 type. Then I can use linear.recordSet to create a record set out of this data. I just have to pass in my features and my labels. This may look familiar from when we did this in an unsupervised case. Only in an unsupervised case, we only had to pass in the features. This time, since we're doing a supervised learning task, we also have to pass in labels. So we have X, our features, and Y, our class labels here. This may look familiar from when we created a record set in an unsupervised learning case. Only in that case, we only had to pass in our training features. We didn't have any labels to work with. This time, we have to pass in both X, our training features, and Y, our training labels. And this creates our formatted train data. Then to train a model on this formatted data, I just have to call linear.fit and pass in the formatted data. This cell creates a training job with some name, launches our required instances, and trains our linear estimator. Your next task was to deploy the trained model. So as our estimator trained, you should have seen a lot of data about the epoch that we're on, as well as a few details about how our model was training. And as always, I can check on the status of this job by looking in our SageMaker console. So if I go to my SageMaker console and I click on Training Jobs, I see a lot from my previous work, and this one that's in progress. So I'm going to click on this one that we just kicked off. I should see the job name, its status, and a few details about its creation and type. I can even see some of the hyperparameters that are left as either default values or values that I specified, like the number of epochs and predictor type. And I'm going to monitor this training job by looking at the logs. The log stream may take a moment to generate, but then you should be able to see something like this. When you click on these logs, you should be able to see a lot of data printed out. We can expand one of these metrics to see the binary classification cross-entropy loss. In this case, we can see that we're training a linear learner and we're on epoch 0. If I scroll further down, I can click on the metrics and look at results from later epochs. Finally, if I wait till the end of training, I should see that a best model was found and a checkpoint was saved. If I look a little above this best model line, I can look at metrics during training. Here I have the final training loss, which is a lot lower than when we started. And next, I can see the classification accuracy, which is really high for our training data. There's also scores for our training precision and our training recall, and we'll get into all of these metrics in a bit. And all of this was actually printed out in the notebook. It's just a lot easier to read in the logs, I find. Now, if you've successfully trained your linear estimator, it's time to deploy it and create a linear predictor. Once you deploy this predictor, you'll be able to use it to make predictions, and I suggest you run the next few cells to see how the result looks when you pass in some test data. Next, I'll show you a deployed solution and go over some of my test evaluation results. Now that you've trained your estimator on some formatted train data, the next thing you should have done is deploy your model to create a linear predictor. This just requires that you pass in some information about the instance type you want for deployment. In this case, I'm using a T2 medium instance. This is a good default for these exercises and when working in a development environment in general. Okay, so after about 7 minutes, a call to deploy creates both a model and an endpoint with some name. And now I have a predictor endpoint that I can use to make predictions on my test data. Let's do a simple test first. I took a look at the predictor information here, and I can see that the linear learner predictor requires a NumPy ND array as input and returns a list of record objects, one record for each data point in the input array. So here I'm converting our test features into a NumPy array, and I'm just going to pass in the first row of data and see what our linear predictor returns. I can see that for this one data point, I have a predicted label that's held in value float32 tensor, and I get the label 0, which I know corresponds to a valid transaction. In addition to a predicted label, I also get a score, which gives me a more precise value if I need it. The score is what's rounded to the predicted label, and so the score gives me a better idea of how confident the model is in its predicted label. In this case, a value really close to 0 indicates that it's pretty confident that the passed-in data point is indeed a valid transaction. A higher value here, closer to 0.5, would indicate a lot of uncertainty in the prediction. So using what I know about this record format, I've created a helper function below. Evaluate takes in a deployed predictor, some test features and labels, and then it returns a variety of metrics. The first line of code in here is just me dividing my test data into batches, because there's a lot of it, and getting predictions for each batch, calling predictor.predict over batch. These batches are going to be of 100 data points each. Then, for each batch in my prediction batches, I'm going to get a pointer to each point in that batch and get the predicted label, calling x.label. Then I'm just concatenating all those results to get our test predictions. Finally, I'm doing a series of comparison between our generated test predictions and our true class labels. I'm calculating the number of true positives, true negatives, and false negatives. Then from those, calculating binary classification metrics for our test data, including recall, precision, and total accuracy. I have an argument verbose that is by default set to true, which will print out these three metrics here. So next, I'm running this code and seeing how our linear predictor performs. I'm passing in the predictor, our formatted test features, our test labels, and I'm setting verbose to be true, which means we'll print out the metrics I'm interested in. And when I run this, the first thing I see is that I get a really high accuracy, 99.9%. But let's look at this table of data. So the rows are our true actual labels, 0 for valid and 1 for fraudulent. And our columns are the predicted labels. So the values here indicate the number of test points that I classified correctly as valid. And here, the number I correctly classified as fraudulent. But I can also see that for 33 of my truly valid cases, I misclassified them as fraudulent. And for our fraudulent cases, 32 of them were misclassified as valid. And that's what's making our values for recall and precision much lower than the accuracy value. So even with a high accuracy, there's still room to improve this model. But now I'm done evaluating this model, and it's good practice to always delete the endpoint once you're done with evaluation. So here I have a helper function that accepts a predictor as endpoint and then deletes an endpoint by name. And I'm calling it here, and I should see that my endpoint is deleted. Next, I'll discuss ways we might improve upon this model, including managing class imbalance in the training set and tuning this model according to goals we have as developers. We saw that the default linear learner got a high accuracy, but still misclassified fraudulent and valid data points. In fact, a little over 30 in each class. So let's think about what exactly during training could cause this behavior and how we might improve the model. First, if we imagine that we're designing this model for use in a bank application, we know that users do not want any valid transactions to be categorized as fraudulent. That is, we want to have as few false positives, zeros classified as ones, as possible. On the other hand, if our bank manager asks for an application that will catch almost all cases of fraud, even if it means a higher number of false positives, then we'd want to optimize for as few false negatives as possible. To train according to specific product demands and goals, we do not want to optimize for accuracy only. Instead, we want to optimize for a metric, like precision or recall, that can help us decrease the number of false positives or negatives. Tuning with a specific metric in mind is often referred to as model optimization or model tuning. The second improvement we might make is something we saw at the very start of this notebook. We saw that only about 0.17% of our data was labeled as fraudulent. So even if a model labeled all of our data as valid, it likely would still have a high test accuracy. This may result in some overfitting towards valid data, which accounts for some false negatives, cases in which fraudulent data, ones, are incorrectly characterized as valid, zeros. So let's address these issues in order. First, tuning our model and optimizing for a specific metric during training, and second, accounting for class imbalance in the training set. Optimizing according to a specific metric is called model tuning, and SageMaker provides a number of ways to automatically tune a linear learner. In this example, I'm considering a scenario in which a bank has asked me to build a model that detects cases of fraud with an accuracy of about 85%. In this case, I want to build a model that has as many true positives and as few false negatives as possible. This corresponds to a model with high recall, which is the number of true positives over the number of true positives plus false negatives. So it's going to be highest when the number of false negatives is 0. To aim for a specific metric, Linear Learner offers the hyperparameter binary classifier model selection criteria, which is the model evaluation criteria for the training dataset. If I look at the details of the parameter here, I can see that by default this is set to accuracy, but I want to change this to be recall. A reference to this parameter is in Linear Learner's documentation. If I scroll down, I can see binary classifier model selection criteria, and I have to select a string, accuracy, F1, F beta, or a number of these other targets. In this case, I know I want to set a target value for recall, and so I'll set my model selection criteria to precision at target recall, and I'll also set a value for my target recall. So here I've created my model as usual, passing in a role, some details about the train instance, an output path, and my SageMaker session. I've also set the model selection criteria to precision at target recall, and I've set my target recall to a value of 0.9. In this case, I'm assuming that the performance on a training set will be within about 5% of the performance on a test set. So for a recall of about 85%, I'll aim for a bit higher, 90%. Next, I've done the same steps as before, training our recall model on our formatted train data, and deploying the model. Then I'm evaluating my deployed prediction endpoint, recall predictor, and printing out the metrics. I can see in this case that I have a much higher recall and a much lower precision. Specifically, I can see that I'm only misclassifying 10 of our fraudulent cases, but I am misclassifying a lot more of our valid cases, misclassifying them as fraudulent. So now I'm done evaluating this endpoint, and I'm going to delete my recall predictor. So we have a model that's tuned to get a higher recall, which aims to reduce the number of false negatives. But earlier, we also discussed how class imbalance may actually bias our model towards predicting that all transactions are valid, resulting in a higher number of false negatives. It stands to reason that this model could be further improved if we account for this imbalance. So next, we'll discuss one more way you might improve this model, and your task will be to train and deploy a model that's both tuned and accounts for class imbalance. To account for class imbalance during training of a binary classifier, Linear Learner offers the hyperparameter positive example weight molt. This is the weight assigned to positive or fraudulent examples when training a binary classifier. The weight of negative examples, our valid data, is fixed at 1. From the hyperparameter documentation, it reads, if you want the algorithm to choose a weight so that errors in classifying negative versus positive examples have equal impact on training loss, specify balanced. So in this cell, I've defined a balanced estimator as usual, with the same number of epochs and recall tuning parameters. And I've added just one more hyperparameter, setting positive example weight molt to balanced. Then, as usual, I'm training the balanced estimator and deploying it, creating a balanced predictor. Then I'm running my evaluation code as before, passing in my balanced predictor, my test features, and test labels. In this case, I can see a high recall and a higher precision than last time. In fact, if we look at the metrics from last time, we can see that we misclassified over 3,000 valid examples as fraudulent and had a very low precision. And in this balanced example, we've reduced that number of misclassifications by at least a factor of 3. So now I'm done evaluating this tuned and balanced model, and I'm going to delete the endpoint. Now, one thing to note is that we're training with a fixed recall value of 0.9 or 90%, but this value may vary when it's actually applied to test data as seen here. In real-world tasks, you'll often be given unbalanced training data and a specific metric to define the success of a product. So knowing how to tune a model for a specific metric and balance the class weights for training is a really valuable skill. In fact, next, I'll give you a different scenario for you to practice what you've learned here. I find that experimenting and playing with parameters is a great empirical way to gain intuition and better understanding of modeling techniques. So try experimenting with tuning and balancing parameters of your own design to see the effect.
In this lesson, you built a credit card detection model and improved it over time. Many of the best developers and researchers I know not only look for solutions to problems, but they look for the best solutions. That often means looking at how a machine learning model fits into a larger picture. The best models consider a variety of metrics and the experience of someone using the model. In this fraud detection example, you saw how to train a machine learning model and aim for a certain level of recall. SageMaker gives you a simple way to tune models based on the constraints that you give it during the training process. You also learned one approach to dealing with class imbalance in your data. Real data is messy and often imbalanced. It takes the work of data scientists using tools like augmentation and balancing techniques to make meaning of this kind of data. Take these learnings with you as you get to the next and final lessons in this section.
The field of machine learning and deep learning is changing pretty rapidly. It's like a lot of research, a lot of like applications in industry, and I wonder, SageMaker is part of that. There's new features that are released like pretty often, very often, as a matter of fact. And I wonder, like within an internal team, how do you decide on like what features to work on?
Traditionally at Amazon overall, Amazon Web Services, we aggressively listen to our customers, right? So we work with customers and then essentially work backwards from what they need. And we've done that pretty successfully with different other products. If you think about what we've done with databases, or if you think about what we've done with compute with Amazon EC2, or if you think about what we've done with the Hadoop ecosystem, making Spark available on top of Amazon Elastic MapReduce, the guiding principle behind all of these products was to listen to the market, listen to customers internally and externally, and trying to find out what would customers need or what would add the most value to customers at a specific point in time. And so that's really how the roadmap is identified. 90 to 95% of the roadmap is identified by talking to customers, and that's part of my job, and understanding what they want at a certain point in time, and then bring that back to the product. We also do have some insights from working with internal customers like Alexa or like Amazon.com. So we learn a lot from their needs, and then based on those needs and combining that with our external customers' needs, we can come up with a healthy roadmap. And in the back end, SageMaker has a very, very large team. We do have engineers that are focusing on optimizing TensorFlow, for example. We do have engineers that are focusing on optimizing PyTorch. And then these folks work directly with the open source community, and they contribute back to the code base of TensorFlow or PyTorch or MXNet or all these deep learning machine learning frameworks. So there are large teams with very clear focuses, and some of them are focusing on platform and infrastructure automation, some of them are focusing on deep learning algorithms, some of them are focusing on workflow and integration. So it's a very large ecosystem of people that are aggressively listening to customers and trying to find out what to build to meet the demand.
Is there a feature among all of these that you find the most exciting right now, or maybe something you'd like to see in future?
Yeah, so if you think about the process that we just went through, I think when people talk about machine learning nowadays, one thing that we get to talk a lot about is the algorithm, the Jupyter notebooks, and then training machine learning model, but where's the data coming from? How does the data get ready for a machine learning model?
The very first step, yeah.
Right? So, and I mean, in the industry, there's this joke that goes about where they say data scientists spend 80% of their time cleaning the data and 20% of their time
modeling it, training a model, yeah.
Complaining about cleaning the data.
Complaining about it.
So the idea really is to facilitate. So one of the things that we spent a lot of energy on last year was to facilitate the process of collecting the data and then creating real features or labeled training data out of raw data, right? So if you want to create a computer vision algorithm for object detection or a sentiment analysis like a classification on text algorithm, you probably want to have an initial set of clean data that real humans have looked at. In the case of images, they would put bounding boxes around birds and then label that as birds, around cars and label that as cars. And so that ecosystem could be improved. So we did release a product at the end of last year called Amazon SageMaker Ground Truth that really helps with collecting real data, raw data sets from the real world, and creating a task, a distributed task that goes out to either a public workforce of real humans that can help you create your features, or a private workforce of potentially your staff or people with a specialized skill set like medical doctors that would be able to recognize medical images and then annotate that accurately and really automate that entire ecosystem of targeting real people with raw data, getting their help about with labeling the data, and eventually creating a cleaned up labeled data for the process of machine learning. And that's really the beginning, right? Because before you start looking at the algorithms, the Jupyter Notebook, you really need to have a clean data set. So we innovated towards the end of last year, created Amazon SageMaker Ground Truth, and that's, I mean, I'm not allowed to have a favorite, but that's one of my favorite products as part of that entire ecosystem.
So you could, as a user, like take, I don't know, your personal photos or something and then send them out to your family to label like what is their favorite thing, and then maybe try to learn like where to plan like the next best vacation or something.
Yeah, you could do that.
One thing I really like about SageMaker is, especially with the built-in algorithms that are coming out, there's a really big repository, a GitHub repository that has like a Jupyter Notebook that walks through an example. It has some example data, and it walks through how to train and deploy each of these algorithms. And I was wondering if you could speak to the decision to kind of create this really big repository in addition to documentation.
Right. The idea behind the repository came, we first decided we wanted machine learning, so our mission really is to put machine learning in the hands of every developer, right? So that's our mission. And to do that, we really thought about reorganizing the way we build technology around machine learning. So we built an entire stack that has 3 main layers. At the bottom of the layer, we make machine learning and deep learning frameworks available. Those are the TensorFlow, the MXNet, the PyTorch, Horvath, all these good programming languages of machine learning that deep developers, data scientists, research scientists would be very knowledgeable in, and they'll be able to play around with that naturally. But that's not for everyone, right? So if you know exactly what to do, if you can play with GPUs and recompile GPU libraries, then yes, you'll be very comfortable there. But then at the middle layer, we also built a lot of automation, like I said earlier, for building, training, and deploying machine learning algorithms, and that's really where SageMaker fits in. And at the top layer, there's a bunch of application services for computer vision and all this other stuff. But because we care about, we want to talk about SageMaker for now, I'll focus on that. Now, automating the infrastructure was not the whole job. Like, the job is not done if you just automate the infrastructure, because you still have people that are not particularly very familiar with machine learning algorithms. So what we decided to do is to bring in the most popular, the most common, the most useful machine learning algorithms that exist out there. XGBoost is one of the competitions winning machine learning algorithm nowadays. Some computer vision algorithms, principal component analysis, k-means, k-nearest neighbor, linear regression, logistic regression, multi-class classification. So you're probably familiar with these names if you've played around with machine learning. So what we set up to do as a challenge is to essentially take these algorithms, optimize them for large scale, for large data sets, and then make them available in Amazon SageMaker. The other thing that we decided to do is to go to our internal team at Amazon and say, hey, what are the cool algorithms that you guys are working on at the moment? And so we got some nuggets from there. An algorithm like blazing text, which is an improvement on Word2Vec. That essentially gets you to, we use that internally at Amazon to build word embeddings, right? To build embeddings of products, of items, of user comments, and things like that. And so we got that from that team and then packaged that and put that in SageMaker. So when you embark on a journey of not just making platforms and services, but also algorithms available to people, I think a very natural thing to do is to also put examples around those algorithms to make sure that people can use these algorithms with a lower friction of entry. So then we decided to build a lot of examples around initially these algorithms, but also people got super excited and just started contributing to these examples. So we ended up eventually with more than 30, and it's probably a lot more now, Jupyter notebooks that we open sourced and that are also available within SageMaker. So the idea there was to make sure that if a data scientist and or developer wants to use SageMaker, they can jump on the platform, not just have access to the infrastructure and all the automation, but also have access to essentially an example that can get them through building, training, deploying, hosting, tuning machine learning models end to end. And we wanted to make sure that everything is available there, including some sample data. So that was the entire idea. And it started as a small project, and it grew because people started contributing. And we also enable our external customers to contribute to that library, which is available on GitHub. And it's an ecosystem that is growing pretty large around that. And that's one of the things I'm also very proud of.
Yeah, I think it's an amazing resource, and I was thinking, like, with especially the use of Jupyter Notebooks, it really ties into what we try to do at Udacity with education, right? It's like a question of how do you make this the most accessible by creating a sort of framing that allows people to really focus on whatever machine learning problem they're trying to solve, whether it's something with data or something with an algorithm, sort of reducing any extraneous information there and like allowing them to explore and play around with these, I think is something really powerful.
Yeah, and people learn by doing, right? So if it is possible for you to, after learning about k-means or k-nearest neighbor algorithms, find a way to implement that right away in a matter of, 10, 15 minutes by just following instructions, it becomes real. It becomes real. And then you can eventually deploy that in a web service or something like that and then use the product. So I think the ability to bring that association with an example that guides the learners is very useful. And then, yes, we're seeing a lot of momentum around that capability.
Mm-hmm. So we've been talking a lot about specific products or people that are using SageMaker. I was wondering if you see some group of people that maybe has some hesitance or hasn't been using these tools that you think could really stand to benefit from using SageMaker.
The quick answer is no. Like what I've seen so far is that SageMaker has a use case for everyone, right? So we do work with companies from startups to very large enterprises, and it was built by design. Startups, for example, are very agile, they're very fast, they want to build products really, really rapidly, so they don't care too much about, well, they do care, but they don't worry too much about things like end-to-end encryption or security and all these other regulations that can come around a platform or service. So we do see startups accelerating the process through which they're building and training machine learning models on SageMaker. But we also work with large enterprises that are heavily regulated. We work with people in financial services. The platform needs to be PCI DSS compliant. We work with people in healthcare where the platform needs to be HIPAA compliant. We work with, with GDPR out there nowadays. So SageMaker, we really put a lot of energy into making sure that the platform is flexible enough to fit the needs of everyone in the ecosystem. And now the platform is, ISO, PCI, GDPR, HIPAA, and all these good, compliance, capabilities are injected into the product, which makes, people that are heavily regulated comfortable. But it's also, like I said, very flexible, a lot of examples, a lot of APIs, a lot of automation, and which also makes, entry-level learners or startups to just like jump on it and then accelerate. Now, I would really encourage, also so learners like students, for example, with a machine learning nanodegree or deep learning nanodegree at Udacity, AWS provides, AWS Educate credits, right? So if you think about just jumping on the program and then getting access to some credits and just jumping on SageMaker and then playing with the tool, it's the same Jupyter notebook that you have on your laptop, but then you get a possibility to use GPUs there and solve some deeper computer vision problems. So I don't really see a friction in the type of people that could use the platform. I've seen a lot of excitement from virtually people, everyone around the world.
Yeah, it's something where with the availability of GPUs and the availability of being able to label your own data sets is just really powering the research and the advancement. So I think these things are very tied.
Exactly.
Yeah. If we're sending out all this data to like human labelers, is there something that can sort of speed this process along with this ground truth feature?
What comes to mind? What could help?
Yeah, well, I mean, ideally, the process would be automated, where you could, maybe use some humans, but use something like a machine learning algorithm to label the data. Yeah.
Ding, winner. Yeah. So that's exactly what we thought about as well. And if you have images, and within the images you want to identify birds and dogs and cats and horses. If you have 1,000 images, and then out of the first 100 images, if you have a good shuffling mechanism, then you stand opportunities to have all of these categories of animals that you want to recognize in the first 100 images. So it would be very beneficial to identify these animals within the first 100 images and let a machine learning model learn how to identify them in the future and pass the 900 other images through the machine learning model first, and then see if it's capable of recognizing these animals on your behalf. Of course, it's an ML model, it's automated, it's fast, you don't need to go back to humans, and if it's capable of getting that done, then it feeds that directly into your training data set. And if it's not capable of getting that done, or if it doesn't have a high confidence in having gotten that done correctly, then it passes it back to the human annotators. So that's essentially what we built as part of Amazon SageMaker Ground Truth, where besides the ability to send the data to people that would eventually label the data manually, you can also create what we call an active learning model that would try first to label the data after learning from the first batch. And then, if it is highly confident in its ability to label the data set in the future, pass that directly to the training data. If it's not, it'll pass it back to the humans. So what we see there is that there is a 70% saving that our customers are having now. Autodesk is an example of a customer that is using SageMaker Ground Truth to label their data set, and they are able to save 70% cost and time just by automating the process with machine learning and Ground Truth.
Yeah, it's interesting what you say about confidence as well, because like if you think of the case of medical images, the images presumably that would be sent back to human labelers would be like the most complicated or sort of strange examples. So it's also kind of a way of surfacing interesting images or whatever data points you have, which I think has some like implications for like research outside of academia. I think that's great. If you could like say like a prediction for something like SageMaker in the next like year or two, where do you think like some of your energies will go? Will it be more data security, or what other kinds of features do you think you'll see more of in the future?
Yeah, that's a very good question. So to get back to how we build, right? So we do have two ways of looking at it. One is that we know a thing or two by working with a lot of customers, and then we hear a lot of needs, for example, needs for more automation, needs for more integration. If you think about operationalizing an end-to-end machine learning workflow, now you can have tools for building, you can have tools for training, you can have tools for deploying, but if you have to do that every day, then you probably want to have tools for lifecycle management, integration, experiment management, workflows, and all these other things that really automate the whole thing. So towards the end of last year, we announced a lot of peripheral features around SageMaker. Features for serverless integration, for example, features for GitHub integration to enable collaboration, features for experiment management to be able to compare the results that you have from two different machine learning models and then look at them side by side and see which ones satisfy your metrics. So we're heavily investing into really connecting the dots, in that end-to-end, life cycle. And there's this other thing that is happening where you can, once you have a machine learning model, there's really three ways you can deploy them. You can deploy the model. One is that you can have that behind a real-time, endpoint web application that can serve real traffic. The second thing is that you can use that for batch processing. For example, you want to crunch the sales of the last month or year, and then you can pass the data through a batch scoring exercise. The third one that is becoming more and more popular nowadays is that you really want to get the machine learning models closest to the users as possible. Right, so for example, you want to be able to put a machine learning model in a device like the Echo device, closer to the user, or in a mobile application, or in an IoT device for predictive agriculture, or something like that, or in an internet disconnected area. So you can put the machine learning model in a small tool that you can use to look at a crop and then see if that crop is healthy in an area that is not connected to the internet. And then these ecosystems come with their own challenges, right? Because you have to get the model to be tiny enough to fit into those little devices. So we put a lot of energy around that too, to make sure that after you train a machine learning model on the cloud with a lot of GPUs, you can compile that, get it smaller, but maintain the same amount of accuracy that you could maintain and increase the performance, because the model is a lot smaller but high performance. And then put that in those devices and really bring machine learning models as closest to the users and the data as possible. So you should expect us to put more energy around these kind of challenges that we're seeing on the field, like where do machine learning models really need to be, and find ways to build technology around that. What is the life cycle of automating machine learning models and operationalizing that, and then building technology to connect these dots. And of course, like I said, 90 to 95% of the time we just talk to customers and try to find out what they want, and we build that. So yes, we're building according to what we know, but we're also building according to the needs that are existing out there.
I'm curious to know a bit more about your background. How did you become interested in machine learning and make your way to Amazon?
Sure. I did study physics and computer science, so that's my background. And I did work as a deployment engineer in the past, and I did work as an on-site engineer in payment systems, and eventually into big data and Hadoop type of technology. So I've always been around science and engineering and building systems and deploying systems and trying to integrate them at scale. So when I got into Amazon about 5.5 years ago, I got in as a Hadoop engineering manager, where I built a team of Hadoop and big data engineers, right? So, and then what we were doing there back then really was to play with the Hadoop tools, Spark when it came out, and the other tools in the ecosystem. And essentially, it was a time when big data was, growing, really big as a field, right? It was still nascent, but it was growing really big. And the small analogy that I draw with the times today is machine learning is today a little bit what big data was 5 or 6 years ago, where a lot of people were getting into the field, but the technology wasn't really there yet to help people adopt big data.
It's playing catch up.
Yeah, it was playing catch up. So it was very useful from our perspective, to observe the investments that AWS put into building Amazon Elastic MapReduce, for example, that made Hadoop accessible, and then the other tools on top of the Hadoop ecosystem and made that accessible. So I spent some time in that ecosystem, and then when we started investing into building machine learning platforms, it was basically a repeat of what we've done with big data, and that's how I got into machine learning. But to get myself ready before actually doing machine learning full time, I was taking courses online. I took the Coursera course by the famous Andrew Ng, 6-7 years ago now, 2012, 2011. And so there's this continuous and perpetual, learning aspect that has always been part of my process, where I want to learn new languages, I want to learn new tools, I want to learn new technology, and machine learning was naturally fitting in that mindset, and that's really how I got into it.
There are all these resources out there if you do want to learn something from a language in the world to a programming language. And I wonder if you have any advice for someone who really wants to learn more about say, like deployment or SageMaker, or really building a machine learning product end to end.
Right. I guess the key advice that I have is, stay curious, stay hungry, watch the market, and the cool thing nowadays is that there's a lot of things online. So follow the key players, especially folks that are investing in education like Udacity, because besides getting information about a product or a service or technology, you also get information about market dynamics, about what are the technologies that are cool, what are the people that are at the forefront of these technologies interested in, right? So then you can plan your trajectory of learning and then draw your interest in the different types of products and machine learning techniques that you want to learn. So stay curious and also just hop on the bandwagon of online education, right? Because there's a fire hose out there of information. There is a lot of machine learning algorithms, there's a lot of tools, there's a lot of frameworks, and it gets really confusing when you want to navigate that ecosystem yourself. So it's very useful to work with an online learning tool that can guide you through the learning process and point you towards some beacons that can really help you learn faster and ignore the noise out there. And that's kind of part of the goal, again, that we have with SageMaker, which is to bring machine learning in front of the people that particularly wouldn't have a science or engineering background but could use machine learning, right? So the platform includes examples like we just discussed that can guide people through really making machine learning useful. So ignore the noise for a minute, go through this specific example, and then at the end of going through the example, you would have learned something useful, something practical, and you would have also learned a lot about machine learning theoretically. So guided learning, staying curious, watching the market and the industry, finding the key players in education and product development and product building, getting to know their interests, and then following that interest and trying to draw a roadmap for yourself that you can use for your next learning activities.
I agree. It's something where this field is changing, so are the tools. And so as long as you keep on learning, driven by your own interest and curiosity, I think that's really the route to go. I feel very lucky to work somewhere where I can partner with someone in industry because I really get to learn a lot. So I want to thank you for joining us and just say hello to all our students out there.
I want to thank you for having me. And machine learning for the win.
For the win.
Now, we saw the strengths of using a linear learner to build a payment fraud classification model, but it's often very useful to deploy a custom model of your own design. And so I've created a couple of notebooks that test your ability to create and deploy a custom model. These notebooks require that you change a few files, and so from this notebook instance page, I'm actually going to select Open Jupyter Lab. This should bring you to a launcher page like this, which is a little nicer, I find, for working with multiple files. You'll also see a number of unique buttons on the side and on the top. Jupyter Lab allows you to upload data using this button, for example, and explore a collection of SageMaker sample notebooks here. So let's navigate to the Moon Data directory and open up this exercise notebook here. And I'll close this launcher. I'll also be able to collapse this sidebar by just clicking on this folder icon here. So the first thing to note about this notebook is our kernel. It's Conda PyTorch P36. We've been using MXNet as the default, but if I want to develop a custom PyTorch model, as I will in this example, it's a good idea to use this kernel. Now my plan for this notebook is to generate some data, upload it to S3, and use it to train a custom PyTorch classifier. So the first thing I'm going to do is load in my usual data management libraries. You'll also see a few specific functions that I want to load in, including makeMoons and train-test-split from the sklearn library. These functions are going to be useful for generating my moon data below. Let's click on the makeMoons documentation to read more about this. I can see that makeMoons expects a number of samples to generate as input, and as output it will produce X and Y. X will be generated samples that are two-dimensional, and Y will be the corresponding class labels, 0 or 1 for each of these points. So in this cell I'm saying I want to generate 600 points, and I have a noise parameter that dictates how spread apart and noisy these points will be. The larger this value is, the more noisy our points will be. Then I'm calling makeMoons, passing in the number of points and that noise parameter, and getting back X and Y. And you can play around with these values just to see what kind of data they generate. So x and y are data points that I can then split into training and test sets. And I'm doing that with a call to train test split, passing in my features and my labels and a test size that I want. This is the fraction of the data that I want to make our test data set. So in this case, I'm keeping a quarter of our data for our test set. After generating this data, I'm going to plot it here. I'm plotting my feature data as a scatter plot, plotting one dimension against another, and I'm coloring it based on the label. In this case, any points that are labeled as 0 are going to be purple, and any points with label 1 are yellow. This data is a classic binary classification challenge. We have evenly distributed classes, but a nonlinear separation line that gets a little tricky with the noise we added. So a linear model will actually not perform very well on this data set, and it's beneficial to use a custom model. So in this notebook, I'm going to focus on exercises that will allow you to deploy a custom PyTorch deep learning model. Now, one thing to note is this data is not yet accessible to a SageMaker estimator. An estimator trains on data that's stored in S3. So as my next couple of steps, I'm going to load in my SageMaker specific libraries and get a few variables. First, my SageMaker session and role, and I'm also getting a default bucket, an S3 bucket where we can store our data. Then I'm going to actually want to create a train.csv file that holds all of our features and their labels. Then I'll have a single file to upload to S3. In that vein, I want you to complete this function makeCSV. It should take in some features X, some corresponding labels Y, and a file name and data directory that define where to save this file. It may be helpful to use pandas to smartly concatenate your features and labels into one data frame, and then turn them into a CSV file. And I want you to create a CSV file in a certain format, according to SageMaker's documentation. Specifically, SageMaker requires that a CSV file does not have a header record, and that the target variable, in this case our class label, is in the first column. So in creating a CSV file, we should set the header to false, and we should make the first column equal to our class labels, leaving the rest as features. So try to complete this function, and if you're confident with your code, you can create a train.csv file by executing the cell below. If you want to check your work, I'll go over a solution next. Before training and deploying a model, we'll need to upload our training data to S3. In the last video, I asked you to create a CSV file that held our train features and train labels, with the train labels in the first column of our CSV file. Creating a CSV file out of features X and labels Y can be done in a few lines of code. So first, I'm using pd.concat to concatenate my labels with my features. Setting axis equal to 1 means I'm concatenating these and smushing them together along the column dimension. Then I'm turning this concatenated data frame into a CSV file. I'm passing in where exactly I want this file to be stored, and I'm specifying that I don't want any headers or indices. This ensures that I'm not including anything extraneous, like column or row names, in the CSV file. I'm only including the raw data. So if I run this cell, I can then test it in the next cell. And I should see that I've created a train.csv file in my specified data directory. The next step is to actually upload this data to S3, and I can do this with a call to session.uploadData. I'm going to pass in where this data is stored locally and where I want it to be stored in our S3 bucket. So I'm specifying a different prefix specific to S3, and I'll even print out where that is. Here I can see a location in S3 with our bucket name and our specified prefix. Then, just to be doubly sure, I'm going to iterate through the objects in our S3 bucket and print the contents. And I can see that I have my specified prefix in S3, followed by my expected train.csv file. I should also note here that I've been manually navigating to S3 to empty my bucket after each lesson, so that I'm not accumulating multiple large model files, for example. So if you see multiple files printed out here, that could be a sign that you need to empty your S3 bucket. Okay, now that we have data in S3, where an estimator can use it for training, next let's learn more about actually building a custom PyTorch estimator. So we have our binary moon data, and the next thing we want to do is define and train a custom PyTorch model, specifically a neural network that performs binary classification. Now, aside from this exercise notebook, I've given you a source directory here. Inside here you'll find several files: train.py, predict.py, and model.py. Model.py will be where the layers of a PyTorch model will be explicitly defined. Predict.py is completely provided to you. You won't need to change anything in here. It's complete and just applies a trained model to some data and returns predicted class scores. And finally, we have train.py, which is where I'll be demonstrating how to build and train a custom model. So let's take this piece by piece. Your first task will be to define a simple binary classifier in model.py. In the notebook, I've specified that this model should accept a number of input dim features. It should then process this input through a couple of hidden layers and return a single output value that indicates a class score, close to 0 or close to 1, for our purple and for our yellow points respectively. In fact, this output value should be a sigmoid activated class score. You can even display the model.py contents in the notebook. This is the starting code I've given you for this model.py file. And let me click on that file directly. Alright, so all your tasks are marked as to-dos in this file. In the init function, you should define a 2 or 3 layer model that takes in some number of input features, creates hidden layers according to this hidden dimension, and produces an output dim number of outputs. You'll specify all your layers in this init function, and then define the feed-forward behavior of the network in forward. Don't forget to apply activation functions where necessary. And really think about how you might create a binary classifier that outputs a 0 or 1 label. There are even more details in the notebook, and a link to an example for a 3-layer network. So try to complete this model.py file before moving on to the solution and next files. So I have corresponding solutions to all of the files in this source file. In fact, in source solution, I have a complete model.py file. And this is just one solution for a neural network made of linear layers. So as an example, I've defined a 2-layer linear network. My first linear layer, which I've called FC1 for fully connected 1, accepts a number of inputs and produces a number of hidden dim nodes. Then my second layer accepts this as input and produces a specified number of outputs. In addition to these 2 linear layers, I've also specified a dropout layer with a probability of 0.3, and this will help prevent domination by just a few nodes in the network. And I've also defined a sigmoid layer, which I'll be able to apply to the output of my network to get a class score between 0 and 1. So in init is where I'm defining all these layers, and then in forward, I'm specifying how an input x will actually move through them. I'm basically passing my input x, which is a batch of input features, through my layers in sequence. First, I'm passing it through my first fully connected layer, and I'm applying a ReLU activation function. Then in between my 2 linear layers, I'm applying my dropout layer. And finally, after a transformed output has moved through our final fully connected layer, I'm applying my sigmoid activation function to return a final class score. Now, you might be wondering, where is a model like this, SimpleNet, going to be used? Well, if I look at just the start of this train.py file, I can see that I'm importing the model for use right here. Train.py is where I'm going to instantiate this model and train it. So next, I'll talk about the details in this training script and the steps you'll need to take to complete it. Now that you've defined a neural network in model.py, it's time to instantiate and train that model. And we'll do this in the training script, which is a file that's located in the source directory under train.py. The training script is key for training a custom model. It's the script that will execute when .fit is called on a custom estimator. Now I'll be showing you a PyTorch example, but you can also train and deploy custom scikit-learn models in a very similar way. In fact, it's even easier because you can just import a model instead of defining a custom one, and many sklearn models have built-in predict functions, so the only file you'll need is a train.py file. So a typical training script is responsible for a number of things. First, it loads in your training data, and it will parse any training and model hyperparameters that are passed into your estimator constructor. Then it will instantiate a model with any specified hyperparameters, in our case, things like input dim, hidden dim, and output dim, and it will train that model. Finally, it's also responsible for saving the trained model so that it can be deployed later. So let's take a look at this train.py file. The first thing in here are my imports, any libraries I need, and a line to import the model that we just made, SimpleNet. Then I have a couple of provided functions, including a function that loads a previously trained model. This is helpful if you want to create a SimpleNet from previously saved model parameters. The next thing I have is getTrainLoader, which accepts a batch size and a data directory where our training data is saved. This function will read in a training CSV file, which it assumes is called train.csv, and it will split it into labels and features. Here I'm getting labels from the first column of data and our features from the rest. Then I'm wrapping my features and labels into a tensor dataset, which can be easily batched by a data loader. Next, I have a train function, which takes in a model, our train loader, and some training parameters. This loop is responsible for iterating over all of our training data and updating a model according to some optimization parameters. So here, for example, I'm looking at how my model responds to a batch of data, and I'm looking at how close the output is to some target.
Then I'm performing backpropagation and optimization to improve the model. I also have a line here to print out some stats about training, and I'm actually going to collapse this for better visibility. Finally, at the end of all of our epochs, I'm going to save our trained model to a model directory. And I have some provided saving functions here, saving the state dictionary of a trained model and just saving the model parameters. Now, all of the details about how to actually define a model and train it, how many epochs to train for, and so on, all of that is taken care of in this main if statement, if name equals main. All of the code in here is what will execute when you call .fit and train a custom estimator. So in this main if statement is where I'll want to define all my model and training hyperparameters. These will be arguments like batch size that we'll be able to pass into a constructor when we create an estimator. This will also be where I get my train loader and instantiate a model with some specified parameters. I'll have to define an optimizer and loss function and pass those to my train function above to finally save my trained model. So you have a few to-dos in here, and your first task will be to define the model and training hyperparameters and add them to our known arguments here. You can do this with an argument parser. This argument parser basically allows us to add arguments to our estimator constructor. So we can add things like batch size that we can specify when we actually construct a custom estimator. To add an argument, we just need to call parser.addArgument and pass in -- the name of a variable, and a few other things. Each argument has a type, something like int or string, a default value that it can take if it's not specified in the constructor, a metavar, which is a descriptive string, typically a letter or two, like N for number or S for seed, that may be used in usage messages. And finally, help, which is just a description about what this parameter is. In this first batch of arguments, we have actually SageMaker parameters. These are things like the model directory in the data directory, where we can find training data and place our trained model output. These are things that will be set automatically no matter the estimator. Then I've set some training arguments, things like batch size, the number of epochs to train for, and a learning rate. Your task will be to add new parameters that we need to define our simple net, essentially like we had to pass in k for a k-means model, or a predictor type for training a linear learner. We know that we have 3 model parameters that define the input, hidden, and output dimensions, so you should add 3 new arguments here. I recommend naming them according to the parameters in our simple net, so input dim, hidden dim, and output dim. Your next to do is to actually instantiate the model by passing in those input parameters, so you can call simple net and pass in something like args.inputDim to get the appropriate dimension. Finally, you'll define an optimizer and criterion for training. All of these things will be passed into your train function here, which takes care of training and saving your model. Next, try to complete this training script following the to-dos marked in code. Then I'll show you one possible solution next. So here's my complete solution for the if statement in our train.py file. The first thing I wanted to do was add arguments to our parser for our 3 model parameters. I've specified input dim, hidden dim, and output dim. All of these arguments are going to be integer values, and I've specified default values for each. Input dim is the number of input features to our model, which will default to 2 since we have 2-dimensional data, and hidden dim is the hidden dimension of the model, which I'll set as a default to 10. Finally, output dim is the output dimension of our model, or how many values I want to output, and I'll just want to output 1 class score. The next to do was to instantiate the model by passing in the appropriate parameters. I know to instantiate a simple net, I just have to pass in the appropriate input dimension, hidden dimension, and output dimension. Setting these equal to args.inputDim will allow someone to specify this dimension when they instantiate an estimator. I'm also moving this model to the appropriate device, which will move it to a GPU if it's available. Next, I'm choosing to use an atom optimizer, which is just my go-to because empirically it works pretty well, but you could also use stochastic gradient descent. I'm passing in my model parameters here and the learning rate specified in my parameters. Then for my criterion, I'm specifying BCE loss, which is binary cross-entropy loss. In PyTorch, normal cross-entropy will not work here because our model only returns 1 value, and so it's particularly suited to BCE loss. And that completes this if statement. My complete model, optimizer, and criterion will be passed into this train function, which will save our trained model. Now, if we go back to our notebook, I can use Pigmentize to print out our complete train.py file. The next step is going to be creating and training a PyTorch estimator such that it executes this training script and trains on the training data we stored in S3. A PyTorch estimator is constructed in a very similar way to other estimators. you can see that I'm importing a PyTorch estimator here, and you'll just have to pass in some arguments to the constructor. When a custom model is constructed in SageMaker, an entry point must be specified that points to a training script in this case. The entry point will let it know where the training script is located so that the estimator knows what to do when .fit is called. So I've given you a link to just the documentation for a PyTorch estimator, and I think you'll be able to complete this task and train a custom model by just using this as a resource. Try it out on your own, and in the next video, I'll go over one solution. So here's how I created a custom estimator that utilizes a training script. First, I've imported the PyTorch estimator from sagemaker.pytorch. Then I'm going to specify an output path in S3 where I want my trained model to be saved. And then I'm creating an estimator passing in a number of constructor arguments. Now let's first take a look at the PyTorch estimator documentation. In here I can see that this takes in an entry point, a source directory, and several hyperparameters including a framework version. If I scroll down, I can see that the entry point is a path to the Python source file which will be executed as the entry point to training. The source directory is a directory with any other training source code dependencies. In this case, this will be our source directory where our model.py file is also saved. The hyperparameters are things that we defined in our argument parser, and the framework version is just the PyTorch version you want to use for executing your model. So here I've specified an entry point, my training script, and a source directory where that can be found. Since I'm demonstrating a solution, I'm using the code that's complete in source_solution. But for you, if you've worked on a train.py file of your own, you should be able to use just source and your complete train.py file. Then I'm specifying my usual SageMaker parameters, including role and things about my train instance and SageMaker session. I also am thinking that I want to use the latest version of PyTorch, which at this recording is version 1.0. And here I'm specifying my model and training hyperparameters. I know I have two-dimensional input data, and I'm specifying a number of hidden nodes which will hopefully be complex enough to help me find the patterns in this data. And I want to output one value as output. I've also specified that I want to train this model for 80 epochs. Now, during actual training, I'll note the model loss and see if I could train for longer, that is, if the loss continues to decrease, or if it kind of plateaus, in which case I'll want to decrease this number. So I've created a custom PyTorch estimator, and the next thing I want to do is train that estimator on my training data. If you recall, in the training script, our train data loader explicitly accepted a CSV file as input, with labels in the first column of data and features in the rest of the columns. So we do not need to take any further steps to format the train.csv file that we stored in S3 earlier. Our custom estimator will accept the CSV file just as it is, and instead of passing in only the data, I'll pass in a dictionary that specifies that this data is to be treated as data in the train channel. Okay, then this kicks off a training job with this name. I can see my instance being spun up and details about my model parameters. For example, I should see that my train script is invoked with my specified number of epochs, hidden dimension, input dimension, and output dimension. Then my train loop prints out my average training loss after each epoch, and I should see this decrease. So at epoch 80, I see that it's decreased from about 0.8 to 0.4, and it looks like it's slowly but surely kind of still decreasing, so I could have stood to train for longer. So now we've done a lot, from defining a custom estimator to training that estimator here. Now there's one extra step before I can deploy this and make predictions. You may have noticed that in previous examples, like when I called .deploy on linear learner, two things happened. A linear learner model was created and an endpoint was created. In the case of a custom PyTorch model, I'll need to create a model and an endpoint individually. PyTorch models do not automatically come with .predict functions. And you may have noticed earlier that you were given a predict.py file. This file is responsible for loading in a trained model and applying it to passed-in data to produce predictions. Much like an estimator knew where the train script was, the next task will be to create a PyTorch model that knows where this predict.py file is. A PyTorch model takes in a few constructor arguments, including an entry point, which in this case will be our predict.py file. And it also takes in the trained estimator data, the trained model attributes. This is the zipped model file that we used to explore model attributes earlier, and it's also used to deploy a model. When an estimator is trained, you can get it with a call to estimator.modeldata. So try to create this model on your own and deploy it. If you get this far, you can use your deployed predictor and see how it performs on some test data. And in the next video, I'll show you one possible solution along with some test results. Here's my solution to PyTorch model creation. This takes in a few of the parameters we're familiar with, including a role and framework version. Then I'm passing in the entry point, which is where my predict.py file is. Now, for your code, this will just be in the source directory, but for solution cases, I'm using source_solution. The main thing to note here is I'm passing in some trained model data, which is our model data from our trained estimator that was fit above. So this gives me a PyTorch model that I can then deploy. And that's what I'm doing in this next cell, calling .deploy and passing in some details about my deployment instance. This creates a predictor that I can then use to make predictions on some test data. Now, if we actually take a look at this predict.py file, I can see that it starts off looking the same as the train.py file, lots of imports, including an import for the model, SimpleNet. Then it has code to load a trained model here, and it also has functions for the type of input data it can see and the type of output it produces. In this case, this content type is actually going to be NumPy data. And in the predict function at the bottom, I'm assuming the input data is going to be of a NumPy type. Then I'm turning it into a tensor that can be passed to our SimpleNet model. Finally, I'm getting the result of applying our model to that data, which should be a predicted class score. Okay, so back to this deployed predictor, I should be able to apply this to some test data features and evaluate the model. In fact, I've provided an evaluate function here that's very similar to the function we used in the linear learner example. It takes in a deployed predictor and some test data and returns a lot of granular metrics. The main difference here is that our model actually returns NumPy formatted data as dictated by our predict file, and so we don't need to do much processing of the data here. I'm simply rounding the output class scores to a 1 or 0 predicted label and squeezing this to get rid of any empty dimensions. Then the code is the same as before. I'm comparing the test predictions to the true labels and calculating true positives, true negatives, and false negatives, and some binary classification metrics. And I'll print them out here. Now if I run this code on our predictor, here is what I get. I get an accuracy of about 80%, which is pretty good for our noisy, wiggly data. I'd encourage you to try to improve this model by either increasing the hidden dimension and adding complexity to the layers, or training for a longer time. Then, as always, when you're done with evaluation, you should delete your endpoints. I'd also suggest going to your SageMaker console and cleaning up any models, config files, and data that you no longer need. And that's it! You've learned how to deploy a custom PyTorch model. Being able to deploy a custom deep learning model of your own design is a useful skill for a variety of tasks, especially tasks that evade traditional methods for classification. It's also useful for tasks where you want to employ a different framework than SageMaker's built-in models, basically allowing for greater flexibility in problem solving. So I wanted to say, great job getting this far. I think you're well equipped to start tackling problems of your own.
Now you've gotten a lot of practice with SageMaker. In this last deployment lesson, you'll look at one more application, time series forecasting. An example of a time series is something like the temperature of a place, measured every hour over a day, or the price of stocks as they rise and fall over time. Time series forecasting is all about looking at historical data and using it to try to predict the future. In this lesson, we'll specifically talk about choosing a context length and a prediction length. The context length defines the amount of data recorded in the past that an algorithm will see as input. For example, we could give a model a month's worth of weather data, then ask it to use that data to form a prediction over some length of time, like predicting the weather for the next week. During the training process, we'll actually compare the predicted output to some known real data in that time frame, so we do have a target. Now, as an example, say you know that it's been sunny for an hour today. This is your context. What do you think the weather will be like in the next hour? Well, it might be a good prediction to say that it will still be sunny. But what if I asked you to predict the weather for next week, given only this one sunny hour for context? That becomes much harder. You don't have enough context to know what a typical week of weather looks like. Generally, the more context you're given, the more you'll be able to notice about patterns in data over time. So a longer context length will often result in better predictions. Conversely, your predicted output values become more uncertain over time. Next, you'll learn about different strategies for approaching time series analysis. You'll go from data exploration to model deployment in SageMaker. And by the end of this lesson, you'll be able to employ similar strategies to analyze any time series data that interests you.
For this lesson, I'm navigating to my time series forecasting directory and to my energy consumption exercise notebook. In this notebook, I want to address the task of time series forecasting. A time series is any data collected over time. And time series forecasting is involved in so many applications, from weather forecasting to sales and stock market prediction, and even in predicting traffic congestion patterns in a city over a day. So it's a really good skill to have. Many traditional time series algorithms use a linear regression model to basically fit a series of data in a historical time frame and then extrapolate from that data to predict future points. So even something like a linear learner can be used to do time series analysis. Only the problem is that these models often struggle with accounting for complex patterns. For example, they don't do so well in cases like predicting the rise and fall of the stock market. And they struggle with seasonal or long-term patterns. For example, in weather prediction, in which there are differences in temperature according to the time of year. So in this example, I just want to show you one algorithm that I think is pretty cool and useful for time series analysis. And that's the built-in algorithm DeepAR. DeepAR is a supervised learning algorithm for forecasting time series using recurrent neural networks, or RNNs. RNNs have the potential to improve on traditional models by giving us a way to look at specific windows of data, basically taking in some set of historical points as input and trying to produce the next sequence of points as predicted output. In the case of DeepAR, it trains by looking at a training dataset made of several time series. It trains by randomly sampling training examples from the time series. Each example consists of a pair of adjacent context and prediction windows of fixed, predefined lengths. The context length defines how far in the past the model can see, and the prediction length controls how far in the future predictions can be made. And you can read more about how DeepAR learns in this documentation. Here you can see samples taken over a time series where we get a variety of different contexts and predictions. Since DeepAR trains on several time series, it's well suited for data that exhibit recurring patterns. In any forecasting task, you should choose the context window to provide enough relevant information so that a model can produce accurate predictions. In general, data points closest to the prediction timeframe will contain the information that's most influential in defining that prediction. The data we'll be working with in this notebook is data about global household electric power consumption. The dataset is originally taken from Kaggle and represents power consumption collected over several years, from 2006 through 2010. With such a large dataset, we can aim to predict over long periods of time, over days, weeks, or months of time. Predicting power consumption is useful for predicting power storage and delivery needs for a population, and I've linked to an interesting article here that was recently published that does something kind of similar. Google and DeepMind built a model to predict energy generation by windmills, and it's a pretty cool application. Okay, so our workflow will be pretty typical, going from loading in this data to processing it, formatting it, and uploading it to S3, then training, deploying, and evaluating a model. I'd suggest you follow along in a SageMaker notebook in another tab, and next I'll load in and process the data. I'm starting this notebook by loading in my usual data libraries. Then I'm going to load in and unzip the energy consumption data. This should give me one text file, householdpowerconsumption.txt. I'll read in just the first few lines of the file to see how it's formatted. Looking at the first 10 lines, I can see that every line here is a data point, and that each point has a date and time recorded to the minute here. Then for each data point, I have different features, like global active power and voltage. Each of these values are separated from one another with a semicolon. If you examine this data, you'll also see that there are some missing values. So next, I'm going to pre-process the data and read it in as a data frame. In here, I'm actually importing some helper functions from a file textpreprocessing.py. This gives me a function that creates a data frame given this text file and a separator, and it also has a function for dealing with null values. In fact, let's take a look at the functions in this file. In this first function, I can see the details of how my text file is converted into a data frame. Then, given a data frame, I'm actually going to fill any empty values with the average value in a column. So any empty values in a column will be replaced by the average value for that feature. And this is just an alternate way of dealing with null values as opposed to dropping them, and it will be fine for doing longer-term time analysis. Okay, so this gives me a data frame full of values. I'll print out its shape and print out the first few rows. I can see I have a lot of data points, and here are some examples. The data is indexed by date and time, and in this example, I'll want to predict the global active power, which is the household minute averaged active power in kilowatts measured across the globe. So next, I'm getting that column by name and displaying all of those power values in a plot. Since the data is recorded every minute, this plot contains a lot of values and is pretty hard to read. So I'm also just going to plot a slice of the data as well. In fact, I'll display 1,440 minutes of data, which is the number of minutes in a 24-hour day. So here's my timestamp for midnight and the active power globally recorded by minutes in a day. I can see peaks at around 9 a.m. and a little later on in the evening when it might be darker and people may be turning on more lights. So there's a lot of data collected every minute, and I could basically go one of two ways with my analysis. I could create mini short time series, say a week or so long, in which I record energy consumption every hour and try to predict the energy consumption over the following hours or days. Or I could create fewer, longer time series that I could use to predict usage farther in the future, over weeks or months. I think both tasks are interesting, and with the amount of data I have, I think it would be great to see longer recurring trends that happen over several months or over a year. So I'm going to resample the global active power values, recording daily data points as averages over 24-hour periods. I can resample my data at a specified frequency by utilizing Panda's time series tools, which allow me to sample at specified frequencies like every hour or day, D. So I'm resampling my current power data frame, passing in this frequency, and recording the daily mean. Then I'm displaying the results. This is a lot more readable than our first plot, and I can already see some trends that seem to occur each year. It seems that there are spikes of energy consumption around the end and beginning of each year, which correspond with heat and light usage being higher in winter months. We can also see a dip in usage around August, when global temperatures are typically higher. The data is still not very smooth, but it shows noticeable recurring trends, which makes this a good use case for Deep AR. Next, let's turn this data into a few time series that Deep AR can learn from. Now that we have our daily average energy consumption data, it's time to turn this into time series that Deep AR can use as training data. Looking at this data, I made a couple of design decisions. I've decided to create 3 time series of data for our 3 full years of data, 2007, 2008, and 2009. I'll train a model on this data and then withhold 2010 as a kind of test set, which I can use later to evaluate the model. In a real-world scenario, you'll likely want to use all of your data and not withhold any time series data. So this is strictly for demonstrative purposes. And in general, the methods I use can be modified slightly to create different kinds of time series. I'll also be showing you one other way to evaluate a Deep AR model without withholding data. I've written a function makeSeries, which will make our 3-year-long time series. It takes in our mean power data frame and a passed-in list of years. So let's take a look at this code. A few details. I'm going to set a starting index at 16, which is where my 2007 data starts. I only had a couple of weeks of data from 2006. Then I also know that 2008 was a leap year, and so I'm going to note that here and make sure I calculate the correct number of days to move through the data frame with. Now, all of the time series we create will start at a consistent time point, t-start, or sometimes called t0. Deep AR uses this time point as a frame of reference, taking into account timeframes like weeks or a year since this start point to learn long-term recurrent patterns, like that summer is different than winter. You can change t-start and t-end to define the length of the time series you create. I'm also getting the data from our mean power data frame within this time frame, from t-start to t-end. And here I'm creating a time series by passing in the time indices and the relevant data. And I'm appending this to my list of time series. After this for loop completes, I should have my list of 3 yearly time series. And I can test my results by running my code, passing in my mean power data frame, the number of full years I want to create time series out of, and then displaying the first time series. So here I can see power usage over a year. I see that winter usage hovers around 1.5 and has a lot of volatility, and summer values are a bit lower. Next, we'll split this data into training and test sets. A test set gives us a way to evaluate our model.
For machine learning tasks like classification, we typically create training and test data by randomly splitting examples into different sets. But for forecasting, it's important to do the split in time. In general, we can create training data by taking each of our complete time series and leaving off the last prediction length of data points. And this will be your first task. Complete the function createTrainingSeries, which takes in a list of complete time series like we just created and creates a different list of training time series that have the end prediction length points left off. In this example, I'll want to predict about a month of energy consumption data over time. So in the next cells, you can test out your code by applying it to our time series and a prediction length of 30 days. If you get stuck or want to check your work, you can check out the solution in the next code example. You've seen how to create training data by iterating over all of our complete time series and leaving off the last prediction length number of points. And here you can see one such series displayed. The test set of data is the entire time series that we initially created. Now we're almost ready to train a deep AR estimator. According to the deep AR documentation, deep AR expects to see input training data in a JSON format. Specifically, each of our time series will be on a single line in a JSON file and formatted as a kind of dictionary that looks like these examples. We have a start key, which is a string that defines the starting date of the time series. This is going to be year, month, day, and timestamp. Then a key target, which holds our associated time series data. These will be the values of the mean global active power. There's an optional key, cat, short for category, that's worth mentioning. Cat is a numerical array of categorical features that can be used to encode the groups that your data belongs to. This is useful when you have different items, like stocks or products that you want your model to distinguish between, but we will not be using it in this example. So your next task will be to convert our time series data, both the training and test sets, into JSON formatted lines. You should complete this function series to JSON obj. This takes in a single time series and returns a dictionary of values in the desired format with start and target keys. Once you've completed this function, you can run the next few cells to write the training and test data to JSON files locally. After uploading your data locally, you'll see one more task, which is actually uploading the data to S3 to make it accessible to a deep AR estimator. If you complete these tasks, you'll be ready to instantiate and train an estimator on this data. To convert any time series into my desired JSON format, I created a dictionary with start and target keys. The index of the time series holds the start time, and the target is just the actual time series data, which I'm getting as a list here. Running the next couple of cells, I got my train and test JSON files stored in a local directory. I stored both files in a directory that I specified, JSON Energy Data. Then to upload my data, I first got my SageMaker resources, including an S3 bucket. Then I specified unique prefixes for my training and test data, first creating a general prefix and then adding /train and /test to that. Then I called upload data for my train JSON file and test JSON file and got the path. Great, so now I'm in good shape and I just need to instantiate an estimator to train it. Some built-in estimators have specific SageMaker constructors, but not all. Instead, you can create a base estimator and pass in a specific image or container that essentially holds a specific model, sort of like a mini library. So in this cell, I'm getting the image for the deep AR forecasting algorithm. Next, you can create a generic estimator and pass in the specific image name to make it a deep AR estimator. You've gotten a lot of practice creating estimators, and I've also linked to some source code if you want to check out the specific constructor parameters. So try to create this estimator, then next I'll discuss estimator hyperparameters and training. Here's my complete estimator. I passed in the usual role, SageMaker session, and train instance details. I also created an output path in S3 where I can save the trained model attributes. And I passed in the image name specific to deep AR, so this estimator knows what model to train. Now, this only gives me a pretty basic estimator, and I'm going to want to define hyperparameters for the deep AR model. I want to define parameters like the number of epochs to train for, and the prediction and context length that I want the model to sample from the training data. I also have to let it know that my time series and lengths are measured in days. These are just the required parameters. There are a lot more optional parameters that can define the underlying recurrent neural network
and the training behavior. So here I've provided a good starting list for those parameters, and a link here to read more about each one. Basically, the number of cells and layers define the size of the underlying RNN, and a bigger size is able to capture more complex relationships in the data. Then batch size and learning rate define how this model trains and improves. Then in this cell, I'm passing in those hyperparameters and setting them to my estimator. Finally, I can pass in my training and test data and fit this estimator. Now, I could only provide training data, but we've created both training and test data. And a test dataset means that Deep AR can calculate accuracy metrics for the model during training on this test dataset. The computed error metrics will be included as part of the log output that we can monitor for a training job. So next, I'll call fit, and I'll deploy this trained model. After creating a prediction endpoint, next I'll show you how we can make some predictions and evaluate this trained model. So we've trained our model on training and test channels of data. Then deployed this to create a predictor that should be able to predict the future, or rather produce predictions of prediction length, 30 days, given a historical time series as input. Now, we can't pass a time series object to our predictor directly. We have to format the input in a specific way. It's going to be a JSON format once again. The predictor expects to see input data in a JSON format with instances and configuration keys. Here's an example of what this looks like. The instances are just a list of JSON formatted time series that should be forecast by the model. And we know how to create these already with the function series to JSON obj we wrote. You may also note that the target can be a list of values of varying length. Then configuration holds a dictionary of configuration information that defines the type of response we want from the predictor. Now, our predictor will output some samples with an element of randomness and uncertainty, and so we'll want quantile predictions back as output. Quantiles basically look at the ranges that these samples fall into. So we can get an upper and lower bound for our prediction range, as well as an average over all samples, for example. And this will become clearer when we can actually visualize this data. But know that we'll have a configuration with some number of samples to generate, an output type, which is going to be quantiles, and the list of exact quantiles that we want. So this function is provided, and it's written to take in a list of input time series and produce a JSON formatted input that we can then pass to our predictor. And here's exactly how that JSON request is constructed. First getting our JSON formatted input series, and then specifying the configuration. In the next cell, I'm getting all the input training and full test time series, which I'll use only for evaluation. Then I'm passing the list of input training time series into our function to get a JSON formatted output. This holds instances for all three of our input series. Then I'm passing this formatted input to the predictor, calling predictor.predict and passing in this input. This print line is here in case you need to debug or want to see what this looks like. Looking at the documentation, I can see that if I pass in an input with this instances and configuration format, I should get a response in this format, where we have a dictionary of predictions organized by quantiles. So in our notebook, I've written code to decode the predictor output as well, just getting my quantile predictions for each time series that was passed in. And this should return a list of predictions. So this has been a lot of formatting and unformatting. But now if I decode my JSON prediction, I'm going to be left with a list that looks like this, or at least this for the first time series. It's a list of 30 predictions for each quantile. And the 30 comes from our prediction length. And I can finally use this data to display the results. This display quantiles function takes in a list of quantile predictions, like we just generated, and a list of target time series, if there are some. It will display the known last 30 values in a target time series. It will also print the average prediction over all samples. The target and prediction median should be comparable. This also fills in an area with lower and upper bounds for the majority of the produced samples, those samples that fall in between quantile 0.1 and 0.9. And when I run this code, I get these three plots. I can see that the results are actually pretty good. The predictions seem to generally follow the waves and trend of the target data. They also seem like they might get a little less certain and accurate at the end of a prediction window. Next, I have one last thing to show you, which is predicting the 2010 data that we withheld. Recall that we did not give our model any data about 2010 when it trained. So if we ask it to predict data in 2010, we're asking it to look into its future. To ask it for such a prediction, I'm going to have to create a formatted input. In this case, I'll aim to predict the first 30 days of 2010, starting on January 1st, so I'm setting my start date accordingly. The request data is going to be a dictionary of instances and configuration. In this case, there's only one instance defined by my start time and an empty target. This data has no complete associated time series. We specifically withheld that information from our model, and the configuration details will be the same as before. Then I can pass this JSON input to our predictor and get a prediction back. Then in the next line, I'm just decoding that prediction to get a list of quantile predictions. Next, I have a few details in here about creating a 2010 time series. We didn't do that at the start of this notebook, so I'm just grabbing the data at the end of my mean power data frame and creating a 2010 time series that's a few months long. From this time series data, I can get the actual target consumption values from 2010 for comparison. Then I'm using my same display quantiles code to compare the predicted values with the target values. So this looks really good. The predictions for January of 2010 closely line up with the actual data, even though DeepAR has never seen this data before and was given no target. As a last step here, I want to make sure to delete the predictor endpoint after I'm done with all my predictions. And I want to congratulate you for making it through this lesson. Now you've seen one complex but far-reaching method for time series forecasting, and you should have the skills you need to apply the DeepAR model to time series data that interests you. Great job!